2 times 2 times 2, written 5 times. And similarly, x to the n is just x multiplied by itself n times. When we write these expressions, the number on the bottom that's being multiplied by itself is called the base. And the number at the top, telling us how many times we're multiplying the base by itself, is called the exponent. Sometimes the exponent is also called the power. The product rule says that if I have x to the power of n times x to the power of m, that's the same thing as x to the n plus m power. In other words, when I multiply two expressions with the same base, then I can add their exponents. For example, if I have 2 cubed times 2 to the 4th, that's equal to 2 to the 7th. And that makes sense because 2 cubed times 2 to the 4th means I multiply 2 by itself 3 times, and then I multiply that by 2 multiplied by itself 4 times, and in the end I have 2 multiplied by itself 7 times, which is 2 to the 7th. I'm just adding up the number of times as multiplied in each piece to get the number of times as multiplied total. The quotient rule says that if I have x to the n power divided by x to the m power, that's equal to x to the n minus m power. In other words, if I divide two expressions with the same base, then I can subtract their exponents. For example, 3 to the 6th divided by 3 squared is going to be 3 to the 6 minus 2, or 3 to the 4th. And this makes sense because 3 to the 6th means I multiply 3 by itself 6 times, and then I divide that by 3 multiplied by itself twice. So when I cancel out 3's, I have 4 3's left. Notice that I have to subtract the number of 3's on the bottom from the number of 3's at the top to get my number of 3's remaining. That's why I subtract my exponents. The power rule tells us if I have x to the n power raised to the m power, that's the same thing as x to the n times m power. In other words, when I raise a power to a power, I get to multiply the exponents. For example, 5 to the 4th cubed is equal to 5 to the 4 times 3, or 5 to the 12th. And this makes sense because 5 to the 4th cubed can be thought of as 5 to the 4th times 5 to the 4th times 5 to the 4th. Expanding this out some more, that's 5 times 5 times 5 times 5 times the same thing times the same thing again. So I have 3 groups of 4 5's, which is a total of 3 times 4, or 12 5's. The next rule involves what happens when I raise a number or a variable to the 0th power. It turns out that anything to the 0th power is equal to 1. Usually this is just taken as a definition, but here's why it makes sense to me. If you have something like 2 cubed divided by 2 cubed, well, certainly that has to equal 1. Anything divided by itself is just 1. But using the quotient rule, we know that this is the same thing as 2 to the 3 minus 3, because when we divide two things with the same base, we get to subtract their exponents. Therefore, this is the same thing as 2 to the 0. So 2 to the 0 has to equal 1 in order to make it work with the quotient rule. And the same argument shows that anything to the 0 power has to be equal to 1. What happens when we take something to a negative power? X to the n is equal to 1 over x to the n. Again, most people just take this as a definition of a negative exponent, but here's why it makes sense. If I take something like 5 to the 7th times 5 to the negative 7th, then by the product rule, This has to equal 5 to the 7 plus negative 7, which is 5 to the 0, and we just said that that is equal to 1. Now I have the equation 5 to the 7th times 5 to the negative 7th equals 1. If I divide both sides by 5 to the 7th, I get that 5 to the negative 7th has to equal 1 over 5 to the 7th. So that's where this rule about negative exponents comes from. It has to be true in order to be consistent with the product rule. Finally, let's look at fractional exponents. What does an expression like x to the 1 over n really mean? Well, it means the nth root of x. For example, 64 to the 1/3 power means the cube root of 64, which happens to be 4. And 9 to the 1/2 means the square root of 9, which is usually written without that little superscript up there. Now the square root of 9 is just 3. Fractional exponents also make sense. For example, if I have 5 to the 1/3 and I cube that, then by the power rule, that's equal to 5 to the 1/3 times 3, which is just 5 to the 1, or 5. So in other words, 5 to the 1/3 is the number that when you cube it, you get 5. And that's exactly what's meant by the cube root of 5. The cube root of 5 is also a number that when you cube it, you get 5. The next rule tells us we can distribute an exponent over a product. In other words, if we have a product, x times y, all raised to the nth power, that's equal to x to the n times y to the n. For example, 5 times 7, all raised to the 3rd power, is equal to 5 cubed times 7 cubed. And this makes sense, because 5 times 7, all raised to the cube power, can be expanded as 5 times 7 times 5 times 7 times 5 times 7. But if I rearrange the order of multiplication, this is the same thing as 5 times 5 times 5 times 7 times 7 times 7, or 5 cubed times 7 cubed. Similarly, we could distribute an exponent over a quotient. If we have the quotient x over y, all raised to the n power, that's the same as x to the n over y to the n. For example, 2/7 raised to the 5th power is the same thing as 2 to the 5th over 7 to the 5th. This makes sense because 2/7 to the 5th can be expanded as 2/7 multiplied by itself 5 times, which can be rewritten as 2 multiplied by itself 5 times divided by 7 multiplied by itself 5 times. And that's 2 to the 5th over 7 to the 5th as wanted. We've seen that we can distribute an exponent over multiplication and division. But be careful, because we cannot distribute an exponent over addition or subtraction. For example, a plus b to the n is not generally equal to a to the n plus b to the n. A minus b to the n is not generally equal to a to the n minus b to the n. And if you're not sure, just try an example with numbers. For example, 2 plus 3 squared is not the same thing as 2 squared plus 3 squared. And 2 minus 3 squared is definitely not equal to 2 squared minus 3 squared. In this video, I gave 8 exponent rules, which I'll list again here. There's the product rule, the quotient rule, the power rule, the zero exponent, the negative exponent, the fractional exponent, and they're the 2 rules involving distributing exponents across multiplication and division. In another video, I'll use these exponent rules to rewrite and simplify expressions involving exponents.
In this video, I'll work out some examples of simplifying expressions using exponent rules. I'll start by reviewing the exponent rules. The product rule says that when you multiply two expressions with the same base, you add the exponents. The quotient rule says that when you divide two expressions with the same base, you subtract the exponents. The power rule says that when you take a power to a power, you multiply the exponents. The power of zero rule says that anything to the zero power is 1 as long as the base is not 0. Since 0 to the 0 is undefined, it doesn't make sense. Negative exponents. To evaluate x to the minus n, we take the reciprocal 1 over x to the n. To evaluate a fractional exponent, like x to the 1 over n, we take the nth root of x. We can distribute an exponent over a product. A times b to the n is equal to a to the n times b to the n. And we can distribute an exponent over a quotient. A over b to the n is a to the n over b to the n. In the rest of this video, we'll use these exponent rules to simplify expressions. For our first example, we want to simplify 3 times x to the minus 2 divided by x to the 4th. There are several possible ways to proceed. For example, we could use the negative exponent rule to write x to the minus 2 as 1 over x squared. All that gets divided by x to the 4th still. Notice that we only take the reciprocal of the x squared. The 3 stays where it is, and that's because the exponent of negative 2 only applies to the x, not to the 3. Now, if we think of 3 as 3 over 1, we have a product of two fractions in our numerator, and so we evaluate that by taking the product of the numerators times the product of the denominators, which is 3 over x squared, all divided by x to the 4th. I can think of x to the 4th as x to the 4th over 1, so now I have a fraction over a fraction, which I can evaluate by multiplying by the reciprocal. That simplifies to 3 times 1 divided by x squared times x to the 4th, which is 3 over x to the 6th, using the product rule, since x squared times x to the 4th is equal to x to the 2 plus 4, or x to the 6th. An alternate way of solving this problem is to start by using the quotient rule. I can rewrite this as 3 times x to the minus 2 over x to the 4th, and by the quotient rule, that's 3 times x to the minus 2 minus 4, or 3 times x to the minus 6. Now using the negative exponent rule, x to the minus 6 is 1 over x to the 6th, and this product of fractions simplifies to 3 over x to the 6th. The same answer I got before. The second problem can be solved in similar ways. Please pause the video and try it before going on. One way to simplify would be to use the negative exponent rule first and rewrite y to the minus 5 as 1 over y to the 5th. Thinking of this as a fraction divided by a fraction, I can multiply by the reciprocal and get 4y cubed y to the 5th over 1. By the product rule, the numerator here is 4y to the 8th, and so my final answer is just 4y to the 8th. Alternatively, I could decide to use the quotient rule first. As in the previous problem, I can write this as 4y cubed minus negative 5 by the quotient rule, and so that's 4y to the 8th, as before. I'd like to show you one more method to solve these two problems, kind of a shortcut method, before we go on. That shortcut relies on the principle that a negative exponent in the numerator corresponds to a positive exponent in the denominator. For example, the x to the negative 2 in the numerator here, after some manipulations, became an x to the positive 2 in the denominator. Furthermore, a negative exponent in the denominator is equivalent to a positive exponent in the numerator. That's what happened when we had the y to the negative 5 in the denominator and translated into a y to the positive 5 in the numerator. Sometimes people like to talk about this principle by saying that you can pass a factor across the fraction bar by switching the sign of the exponent. That is, making a positive exponent negative or a negative exponent positive. Let's see how this principle gives us a shortcut for solving these two problems. In the first problem, 3x to the minus 2 over x to the 4, we can move the negative exponent in the numerator and make it a positive exponent in the denominator. So we get 3 over x to the 4 plus 2, or x to the 6th. In the second example, for y cubed over y to the minus 5, we can change the y to the minus 5 in the denominator into a y to the 5 in the numerator and get our final answer of 4y to the 3 plus 5, or 8. We'll use this principle again in the next problems. In this example, notice that I have y's in the numerator and in the denominator, and also z's in the numerator and in the denominator. In order to simplify, I'm going to try to get all my y's either in the numerator or the denominator, and similarly for the z's. Since I have more y's in the denominator, let me move this y to the 3 downstairs and make it a y to the negative 3. I'm using the principle here that a positive exponent in the numerator corresponds to a negative exponent in the denominator. Now, since I have a positive exponent on z in the numerator and a negative exponent in the denominator, and I want to get rid of negative exponents, I'm going to pass the z's to the numerator. A z to the minus 2 in the denominator becomes a z to the plus 2 in the numerator. Notice that my number 7 doesn't move and when I do any of these manipulations because it doesn't have an exponent. And the exponent of negative 2, for example, only applies to the z, not to the 7. Now that I've got all my z's in the numerator and all my y's in the denominator, it's easy to clean this up using the product rule. And I have my simplified expression. In this last example, we have a complicated expression raised to a fractional power. I'm going to start by simplifying the expression inside the parentheses. I can bring all my y's downstairs and all my x's upstairs and get rid of negative exponents at the same time. In other words, I can rewrite this as 25x to the 4th. I'll bring the y to the minus 5 downstairs and make it y to the 5th on the denominator. Bring the x to the minus 6 upstairs and make it x to the 6th in the numerator, and then I still have the y cubed on the denominator. All that's raised to the 3/2 power. Using the product rule, I can rewrite the expression on the inside of the parentheses as 25x to the 10th over y to the 8th. Recall that we're allowed to distribute an exponent across a product or across a quotient. When I distribute my 3/2 power, I get 25 to the 3/2 times x to the 10th to the 3/2 divided by y to the 8th to the 3/2. Now the power rule tells me when I have a power to a power, I get to multiply the exponents. So I can rewrite this as 25 to the 3/2 times x to the 10 times 3/2 over y to the 8 times 3/2. In other words, 25 to the 3/2 times x to the 15th over y to the 12th. Finally, I need to rewrite 25 to the 3/2. Since 3/2 can be thought of as 3 times 1/2 or as 1/2 times 3, I can write 25 to the 3/2 as 25 to the 3 times 1/2 or as 25 to the 1/2 times 3. Well, using the power rule in reverse, I can think of this as 25 cubed to the 1/2, or as 25 to the 1/2 cubed, since when I take a power to a power, I multiply the exponents. 25 cubed to the 1/2 might be hard to evaluate, since 25 cubed is a huge number. But 25 to the 1/2 is just the square root of 25. So I have the square root of 25 cubed, or 5 cubed, which is 125. Therefore, my original expression is going to be 125 x to the 15 over y to the 12th. In this video, we use the exponent rules to simplify complicated expressions.
This video goes through a few tricks for simplifying expressions with radicals in them. Recall that this notation means the nth root of x. So this notation here means the cube root of 8, the number that when you cube it, you get 8. That number would be 2. When we write the root sign without a little number, that just means the square root, so the 2 is implied. In this case, the square root of 25 is 5, since 5 squared is 25. Let's start by reviewing some rules for radical expressions. First, if we have the radical of a product, we can rewrite that as the product of two radicals. For example, the square root of 9 times 16 is the same thing as the square root of 9 times the square root of 16. You can check that both of these evaluate to 12. Similarly, it's possible to distribute a radical sign across division. The radical of a divided by b is the same thing as the radical of a divided by the radical of b. For example, the cube root of 64 over 8 is the same thing as the cube root of 64 over the cube root of 8, and you can check that both of these evaluate to 2. You have to be a little bit careful, though, because it's not okay to distribute a radical sign across addition. In general, the nth root of a plus b is not equal to the nth root of a plus the nth root of b. And similarly, it's not okay to distribute a radical across subtraction. If you're ever in doubt, you can always check with simple examples. For example, the square root of 1 plus 1 is not the same thing as the square root of 1 plus the square root of 1. The right side evaluates to 1 plus 1, or 2, and the left side is square root of 2, an irrational number. The second expression, to show that that fails, I don't think it'll work to use the square root of 1 minus 1. It'll actually hold in that case, but I can show it's false by using, say, the square root of 2 minus 1, which does not equal the square root of 2 minus the square root of 1. You might notice that these rules for radicals, the ones that hold and the ones that don't hold, remind you of rules for exponents, and that's no coincidence, because radicals can be written in terms of exponents. For example, if we look at the first rule, we could rewrite this. The nth root of a times b is the same thing as the 1 over nth power. And by exponent rules, I can distribute an exponent across multiplication. And so this radical rule can be restated completely in terms of an exponent rule. Similarly, the second rule can be restated in terms of exponents as a over b to the 1 over n is equal to a to the 1 over n divided by b to the 1 over n. We can use the relationship between radicals and exponents to rewrite a to the m over n. A to the m over n is the same thing as a to the m with the nth root taken. It's also the same thing as the nth root of a, all taken to the mth power. To see why that's true, think about exponent rules. So a to the m over n is the same thing as a to the m taken to the 1 over nth power. That's because when we take a power to a power, we multiply exponents, and m times 1 over n is equal to m over n. But a 1 over nth power is the same thing as an nth root, and therefore this expression is the same thing as this expression. And that proves the first equivalence. The second equivalence can be proved similarly by writing a to the m over n as a to the 1 over n times m. Again, this works because when I take the power to the power, I multiply exponents. 1 over n times m is the same thing as m over n. But now, these two expressions are the same because the 1 over nth power is the same as the nth root. One mnemonic for remembering these relationships is flower over root. So flower is like power and root is like root. So that tells us we can write a fractional exponent. The m becomes the power and the n becomes the root in either of these two orders. Now let's use these rules in some examples. If we want to compute 25 to the negative 3/2 power, well, first I'll use my exponent rule to rewrite that negative exponent as 1 over 25 to the 3/2 power. Next, I'll use the power over root mnemonic to rewrite this as 25 to the 3rd power square rooted, or as 25 square rooted to the 3rd power. I wrote the 2's there for the square root for emphasis, but most of the time people will omit this and just write the square root without a little number there. Now I could use either of these two equivalent expressions to continue, but I'd rather use this one because it's easier to compute without a calculator. The square root of 25 is just 5. 5 cubed is 125. So my answer is 1 over 125. If I tried to compute the cube of 25 first, I'd get a huge number. In general, it's usually easier to compute the root before the power when you're working without a calculator. Now let's do an example simplifying a more complicated expression with exponents in it. I want to take the square root of all this stuff, and since I don't really like negative exponents, I'm first going to rewrite this as the square root of 60x squared y to the 6th over z to the 11th. So I'll change that negative exponent to a positive exponent by moving this factor to the denominator. Now, when you're asked to simplify a radical expression, that generally means to pull as much as possible out of the radical sign. To pull things out of the square root sign, I'm going to factor my numbers and try to rewrite everything in terms of squares as much as possible. Since the square root of a square, those two operations undo each other. So I'll show you what I mean. First, I'll factor 60. So 60 is going to be 2 squared times 3 times 5. And I'll just copy everything over for now. Now I'll break things up into squares as much as possible. So I've got a 2 squared times 3 times 5. I've already got an x squared. I'll write the y to the 6th as y squared times y squared times y squared. And I'll write the z to the 11th as z squared times z squared, I guess 5 times, 1, 2, 3, 4, 5, times 1 extra z. That should add up to z to the 11th if I add all those exponents together. Now I know that I can distribute my radical sign across multiplication and division, so I'll write this with a zillion different radicals here. And every time I see the square root of something squared, I can just cancel those square roots and the squares out and get what's left here. So after doing that cancellation, I get 2 times the square root of 3 times 5 times x times y times y times y over z times itself, I guess 5 times the square root of z. And now I can clean that up with exponents. I'll write that as the square root of 15, I guess 2 times the square root of 15 times x times y cubed over z to the 5th, the square root of z. I'm going to leave this example as is, but sometimes people prefer to rewrite radical expressions without radical signs in the denominator That's called rationalizing the denominator. I won't do it here, but I'll show you how to do it in the next example. This example asks us to rationalize the denominator. That means to rewrite as an equivalent expression without radical signs in the denominator. To get rid of the radical sign in the denominator, I want to multiply my denominator by square root of x. But I can't just multiply the denominator willy-nilly by something unless I multiply the numerator by the same thing, so that I'm just multiplying my expression by 1 in a fancy form and I don't change the value of my expression. Now if I just multiply together numerators, 3x squared of x, and multiply denominators, square root of x times square root of x is the square root of x squared. Square root of x squared is just x. Now I can cancel my x's from the numerator and denominator, and my final answer is 3 times the square root of x. I rationalized my denominator, and in the process, got a nicer looking expression. In this video, we went over the rules for radicals, and we simplified some radical expressions by working with fractional exponents, pulling things out of the radical sign, and rationalizing the denominator. This video goes over some common methods of factoring. Recall that factoring an expression means to write it as a product. So we could factor the number 30 by writing it as 6 times 5. Or we could factor it more completely by writing it as 2 times 3 times 5. As another example, we could factor the expression x squared plus 5x plus 6 by writing it as x plus 2 times x plus 3. In this video, I'll go over how I get from here to here, how I know how to do the factoring. But for right now, I just want to review how I can go backwards, how I can check that the factoring is correct. And that's just by multiplying out or distributing. If I distribute x plus 2 times x plus 3, then I multiply x by x, that gives me x squared. X times 3 gives me 3x. 2 times x gives me 2x, and 2 times 3 gives me 6. So that simplifies to x squared plus 5x plus 6, which checks out with what I started with. So you can think of factoring as the opposite of distributing out, and you can always check your factoring by distributing or multiplying out. A bit of terminology: when I think of an expression as a sum of a bunch of things, then the things I sum up are called the terms. But if I think of the same expression as a product of things, then the things that I multiply together are called factors. Now let's get started on techniques of factoring. When I have to factor something, I always like to start by pulling out the greatest common factor. The greatest common factor means the largest thing that divides each of the terms. In this first example, the largest thing that divides both 15 and 25x is 5. So the GCF is 5. So I pull the 5 out, and then I divide each of the terms by that number, and so I get 3 plus 5x. Pause the video for a moment and see if you can find the greatest common factor of x squared y and y squared x cubed. The biggest thing that divides both x squared y and y squared x cubed is going to be x squared times y. One way to find this is to look for the power of x that's smallest in each of these terms. So that's x squared. And the power of y that's smallest in each of these terms is just y to the 1, or y. Now if I factor out the x squared y from each of the terms, that's like dividing each term by x squared y. If I divide the first term by x squared y, I just get 1. If I divide the second term by x squared y, I'm going to be left with an x and a y. I'll write this out on the side just to make it more clear. Y squared x cubed over x squared y, that's like 2 y's and 3 x's on the top and 2 x's and a y on the bottom. So I'm left with just an x and a y. So I'll write the xy here, and I factored my expression. As always, I can check my answer by multiplying out. So if I multiply out my factored expression, I get x squared y as the first term, and the second term, I get x, they're now, let's see, 3 x's multiplied together and 2 y's multiplied together, and that checks out with what I started with. The next technique of factoring I'd like to go over is factoring by grouping. In this example, notice that we have 4 terms. Factoring by grouping is a handy method to look at if you have 4 terms in your expression you need to factor. In order to factor by grouping, I'm first going to factor out the greatest common factor of the first 2 terms, and then separately factor out the greatest common factor of the last 2 terms. The greatest common factor of x cubed and 3x squared is x squared. So I factor out the x squared and I get x plus 3. And now the greatest common factor of 4x and 12 is just 4. So I factor out the 4 from those 2 terms. Notice that the factor of x plus 3 now appears in both pieces. So I can factor out the greatest common factor of x plus 3. I think I'll factor it out on the left side instead of the right. And now I have an x squared from this first piece, and I have a 4 from this second piece, and that completes my factoring by grouping. You might wonder if we could factor further by factoring the expression x squared plus 4. But in fact, as we'll see later, this expression, which is a sum of 2 squares, x squared plus 2 squared, does not factor any further over the integers. Next, we'll do some factoring of quadratics. A quadratic is an expression with a squared term, just a term with x in it, and a constant term with no x's in it. I'd like to factor this expression as a product of x plus or minus some number times x plus or minus some other number. The key idea is that if I can find those 2 numbers, then if I were to distribute out this expression, those 2 numbers would have to multiply to give me my constant term of 8. And these 2 numbers would end up having to add to give me my -6, because when I multiply out, this number will be a coefficient of x, and this number will be also another coefficient of x. They'll add together to the -6. So if I look at all the pairs of numbers that multiply together to give me 8, so that could be 1 and 8, 2 and 4, 4 and 2, but that's really the same things I had before, and that's sort of the same thing I had before. I shouldn't forget the negatives. I could have -1, -8, or I could have -2, -4. Those also multiply together to give me 8. Now I just have to see if there's a pair of these numbers that add to -6, and it's not hard to see that these ones will work. So now I can write out my factoring as that would be x minus 2 times x minus 4. And it's always a good idea to check by multiplying out. I'm going to get x squared minus 4x minus 2x plus 8, and that works out to just what I want. Now this second example is a bit more complicated because now my leading coefficient, my coefficient of x squared, is not just 1, it's the number 10. Now there are lots of different methods for approaching a problem like this, and I'm just going to show you one method, my favorite method, that uses factoring by grouping. But to start out, I'm going to multiply my coefficient of x squared by my constant term. So I'm multiplying 10 by -6. That gives me -60. And I'll also take my coefficient of x, the number 11, and write that down here. Now I'm going to look for 2 numbers that multiply to give me -60 and add to give me 11. You might notice that this is exactly what we were doing in the previous problem. It's just here we didn't have to multiply the coefficient of x squared by 8 because the coefficient of x squared was just 1. So to find the 2 numbers that multiply to -60 and add to 11, you might just be able to come up with them in your head thinking about it, but if not, you can figure it out pretty systematically by writing out all the factors, pairs of factors, that multiply to -60. So I can start with -1 and 60, -2 and 30, -3 and 20, and keep going like this until I have found factors that actually add together to give me the number 11. And now that I look at it, I've already found them. 15 minus 4 gives me 11, so I don't have to continue with my chart of factors. Now, once I've found those factors, I write out my expression, 10x squared, but instead of writing 11x, I write negative 4x plus 15x. Now I copy down the negative 6. Notice that negative 4x plus 15x equals 11x. That's how I chose those numbers. And so this expression evaluates as the same as this expression. I haven't changed my expression. But I have turned it into something that I can apply factoring by grouping on. Look, I've got 4 terms here. And so if I factor out my greatest common factor of my first 2 terms, that's, let's see, I think it's 2x. So I factor out the 2x, I get 5x minus 2. And then I factor out the greatest common factor of 15x and negative 6. That would be 3. And I get a 5x minus 2 again. This is working beautifully. So I have a 5x minus 2 in each part, and so I put the 5x minus 2 on the right, and I put what's left from these terms in here, so that's 2x plus 3, and I have factored my expression. There are a couple special kinds of expressions that appear frequently that it's handy to just memorize the formula for. So the first one is the difference of squares. If you see something of the form a squared minus b squared, then you can factor that as a plus b times a minus b. And let's just check that that works. If I do a plus b times a minus b and multiply that out, I get a squared minus ab plus ba minus b squared, and those middle 2 terms cancel out, so it gives me back the difference of squares just like I want it. So for this first example, if I think of x squared minus 16 as x squared minus 4 squared, then I can see that's a difference of squares, and I can immediately write it as x plus 4 times x minus 4. And the second example, 9p squared minus 1, that's the same thing as 3p squared minus 1 squared. So that's 3p plus 1 times 3p minus 1. Notice that if I have a sum of squares, for example, x squared plus 4, which is x squared plus 2 squared, then that does not factor. The difference of squares formula doesn't apply, and there is no formula that applies for a sum of squares. There is, however, a formula for both a difference of cubes and a sum of cubes. The difference of cubes formula, a cubed minus b cubed, is a minus b times a squared plus ab plus b squared. The formula for the sum of cubes is pretty much the same. You just switch the negative and positive sign here and here. So that gives us a plus b times a squared minus ab plus b squared. As usual, you can check these formulas by multiplying out. Let's look at one example of using these formulas. Y cubed plus 27 is actually a sum of 2 cubes because it's y cubed plus 3 cubed. So I can factor it using the sum of cubes formula by plugging in y for a and 3 for b. That gives me y plus 3 times y squared minus y times 3 plus 3 squared, and I can clean that up a little bit to read y plus 3 times y squared minus 3y plus 9. So in this video we went over several methods of factoring. We did factoring out the greatest common factor. We did factoring by grouping. We did factoring quadratics, and we did a difference of squares, and we did a difference and a sum of cubes. In more complicated problems, you may need to apply several of these techniques in order to get through a single problem. For example, you might need to start by pulling out a greatest common factor and then do a factoring of quadratics or something similar. Now go forth and factor. This video gives some additional examples of factoring. Please pause the video and decide which of these first 5 expressions factor and which one does not. The first expression can be factored by pulling out a common factor of x from each term. So that becomes x times x plus 1. The second example can be factored as a difference of two squares, since x squared minus 25 is something squared minus something else squared. And we know that anytime we have something like a squared minus b squared, that's a plus b times a minus b. So we can factor this as x plus 5 times x minus 5. The third one is a sum of two squares. There's no way to factor a sum of two squares over real numbers. So this is the one that does not factor. Just for completeness, let's look at the next two. This next one does factor by grouping. When we factor by grouping, we pull the biggest common factor out of the first two terms. That would be an x squared. That becomes x squared times x plus 2. And then we factor as much as we can out of the next two terms. That would be a 3 times x plus 2. Notice that the x plus 2 factor now occurs in both of the resulting terms, so we can pull that x plus 2 out and get x plus 2 times x squared plus 3. We can't factor any further because x squared plus 3 doesn't factor. Finally, we have a quadratic. This also factors, and I like to factor these also using a factoring by grouping trick. So first, what I do is I multiply the coefficient of x squared and the constant term. 5 times 8 is 40. I'll write that on the top of my x. Now I take the coefficient of the x term, that's negative 14, and I write that on the bottom part of the x. Now I'm looking for two numbers that multiply to 40 and add to negative 14. Sometimes I can just guess numbers like this, but if not, I start writing out factors of 40. So factors of 40, I could do 1 times 40. Well, now I just noticed I'm trying to add to a negative number. So if I use two positive factors, there's no way there's going to add to a negative number. It's better for me to use negative numbers that factor 40. A negative times a negative still multiplies to 40, but they have a chance of adding to a negative number. So, but negative 1 and negative 40, of course, don't work. They don't add to negative 14, they add to negative 41. So let me try some other factors. The next biggest number that divides 40 besides 1 is 2. So I'll try negative 2 and negative 20. Those add to negative 22. That doesn't work. Next one that divides 40 would be 4. So I'll try negative 4 and negative 10. Aha, we have a winner. So negative 4 plus negative 10 is negative 14. Negative 4 times negative 10 is positive 40. We've got it. All right, so the next step is to use factoring by grouping. We're going to first split up this negative 14x as negative 4x minus 10x and carry down the 8 and the 5x squared. Notice that this works because I picked negative 4 and negative 10 to add up to negative 14. So negative 4x minus 10x will add up to negative 14x. So I've got the same expression, just expanded out a little bit. Now I have four terms. I can do factoring by grouping. So I can group the first two terms and factor out the biggest thing I can. That would be an x times 5x minus 4. And now I'll factor the biggest thing I can out of these two numbers, including the negative. So that becomes, let's see, I can factor out a negative 2, and that becomes 5x minus 4, since negative 2 times minus 4 is 8. All right, I've got the same 5x plus 4 in both my terms, so factoring by grouping is going swimmingly. I can factor out the 5x minus 4 from both those terms, and I get the x minus 2. And I've factored this quadratic. If I want to, of course, I can always check my work by distributing out, by multiplying out. So a check here would be multiplying 5x times x is 5x squared. 5x times minus 2 is minus 10x. Minus 4 times x is minus 4x. And minus 4 times minus 2 is plus 8. So let's see, this does check out to exactly what it should be. So that was the method of factoring a quadratic. And all of these factor except for the sum of squares. So we saw that factoring by grouping is handy for factoring this expression here. It was also handy for factoring the quadratic indirectly after splitting up the middle term into two terms. So how can you tell when an expression is appropriate to factor by grouping? There's an easy way to tell that it might be a candidate, and that's that it has four terms. So if you see four terms, or in the case of the quadratic, you can split it up into four terms, then that's a good candidate for factoring by grouping, because you can group the first two terms, group the second two terms. Factoring by grouping won't always work on expressions with four terms, but that's like the first thing to look for. So let's just review what are the same main techniques of factoring. We saw these on the previous page. We saw there was pull out common factors. There's difference of squares. There's factoring by grouping. There's factoring quadratics. And one more that I didn't mention is factoring sums and differences of cubes. That uses the formulas a cubed minus b cubed is a minus b times a squared plus ab plus b squared, and a cubed plus b cubed is a plus b times a squared minus ab plus b squared. One important tip when factoring, I always recommend doing this first. Pull out the common factors first. That'll simplify things and making the rest of factoring easier. One more tip is that you might need to do several of these factoring techniques in one problem. For example, you might have to first pull out a common factor, then factor a difference of squares, and then you might notice that one of your factors is itself a difference of squares, and you have to apply a difference of squares again. So don't stop when you factor a little bit. Keep factoring as far as you can go. Here are some extra examples of factoring quadratics for you to practice. Please pause the video and give these a try. For the first one, let's multiply 2 times negative 14. That gives us negative 28, and then we'll bring the 3 down in the bottom of the x. Now we're looking for two numbers that multiply to negative 28 and add to 3. Well, to multiply two numbers to get a negative 28, we'll need one of them to be negative and one of them to be positive. So, let's see, 1, negative 1, 28, or 1, negative 28, those don't work. Let's see, negative 2, 14, or 2, negative 14, those don't work. Hey, I just noticed the positive number had better be bigger than the negative number so that they add to a positive number. Let's see what comes next. How about negative 4 times 7, 4 times negative 7? I think negative 4 times 7 will work. So I'll write those here, negative 4, 7. I'll copy down the 2z squared, and I'll split up the 3z into negative 4z plus 7z, and then minus 14. Now factoring by grouping, pull out a 2z, that becomes z minus 2. Pull out a 7, and that becomes z minus 2 again, looking good. I've got 2z plus 7 times z minus 2 as my factored expression. My second expression, I could work it the same way, drawing my x and factoring by grouping, that kind of thing. But it's actually going to be easier if I notice first that I can pull out a common factor from all of my terms. That'll make things a lot simpler to deal with. So notice that a 5 divides each of these terms. And in fact, I'm going to go ahead and pull out the negative 5 because I don't like having negatives in front of my squared term. So I'm going to pull out a common factor of negative 5. Again, it would work if I forgot to do this, but it would be a lot more complicated. So negative 5 v squared, this becomes plus 9v, since 9 times negative 5 is negative 45, and this becomes minus 10, since negative 10 times negative 5 is positive 50. Now I can start my x and my factoring by grouping, or I can use kind of a shortcut method, which you may have seen before. So I can just put v's here, and then I know that whatever numbers go here, they're going to have to multiply to the negative 10, and they're going to have to add to the 9. So that would be plus 10 and a minus 1 will do the trick. Those are all my factoring examples for today. I hope you enjoy your snow morning and have a chance to spend some time working in ALEX. Bye. This video is about working with rational expressions. A rational expression is a fraction, usually with variables in it. Something like x plus 2 over x squared minus 3 is a rational expression. In this video, we'll practice adding, subtracting, multiplying, and dividing rational expressions, and simplifying them to lowest terms. We'll start with simplifying to lowest terms. Recall that if you have a fraction with just numbers in it, something like 21 over 45, we can reduce it to lowest terms by factoring the numerator and factoring the denominator, and then canceling common factors. So in this example, the 3's cancel, and our fraction reduces to 7 over 15. If we want to reduce a rational expression with variables in it to lowest terms, we proceed the same way. First, we'll factor the numerator, that's 3 times x plus 2, and then factor the denominator. In this case, it factors to x plus 2 times x plus 2. We could also write that as x plus 2 squared. Now we cancel the common factors, and we're left with 3 over x plus 2. Definitely a simpler way of writing that rational expression. Next, let's practice multiplying and dividing. Recall that if we multiply two fractions with just numbers in them, we simply multiply the numerators and multiply the denominators. So in this case, we would get 4 times 2 over 3 times 5, or 8/15. If we want to divide two fractions, like in the second example, then we can rewrite it as multiplying by the reciprocal of the fraction on the denominator. So here we get 4/5 times 3/2, and that gives us 12/10, but actually we could reduce that fraction to 6/5. We use the same rules when we compute the product or quotient of two rational expressions with variables in them. Here we're trying to divide two rational expressions, so instead we can multiply by the reciprocal. I call this flipping and multiplying. And now we just multiply the numerators and multiply the denominators. It might be tempting at this point to multiply out, to distribute out the numerator and the denominator, but actually it's better to leave it in this factored form and factor it even more completely. That way we'll be able to reduce the rational expression to cancel the common factors. So let's factor it even more. The x squared plus x factors as x times x plus 1, and x squared minus 16, that's a difference of two squares. That's x plus 4 times x minus 4. The denominator is already fully factored, so we'll just copy it over, and now we can cancel common factors here, and we're left with x times x minus 4. This is our final answer. Adding and subtracting fractions is a little more complicated because we first have to find a common denominator. A common denominator is an expression that both denominators divide into. It's usually best in the long run to use the least common denominator, which is the smallest expression that both denominators divide into. In this example, if we just want a common denominator, we could use 6 times 15, which is 90, because both 6 and 15 divide evenly into 90. But if we want the least common denominator, the best way to do that is to factor the two denominators. So 6 is 2 times 3, 15 is 3 times 5, and then put together only the factors we need for both 6 and 15 to divide our number. So if we just use 2 times 3 times 5, which is 30, we know that 2 times 3 will divide it, and 3 times 5 will also divide it. And we won't be able to get a denominator any smaller because we need the factors 2, 3, and 5 in order to ensure both these numbers divide it. Once we have our least common denominator, we can rewrite each of our fractions in terms of that denominator. So 7/6, I need to get a 30 in the denominator, so I'm going to multiply that by 5 over 5. I multiply by the factors that are missing from the current denominator in order to get my least common denominator of 30. For the second fraction, 4/15, 15 times 2 is 30, so I'm going to multiply by 2 over 2. Now I can rewrite this as 35/30ths minus 8/30ths, and now that I have a common denominator, I can just subtract my two numerators, and I get 27/30ths. If I factor, I can reduce this to 3 squared over 2 times 5, which is 9/10. The process for finding the sum of two rational expressions with variables in them follows the exact same process. First, we have to find the least common denominator. I'll do that by factoring the two denominators. So 2x plus 2 factors as 2 times x plus 1. X squared minus 1, that's a difference of 2 squares, so that's x plus 1 times x minus 1. Now for the least common denominator, I'm going to take all the factors I need to get an expression that each of these divides into. So I need the factor 2, I need the factor x plus 1, and I need the factor x minus 1. I don't have to repeat the factor x plus 1, I just need to have it one time. And so I will get my least common denominator 2 times x plus 1 times x minus 1. I'm not going to bother multiplying this out. It's actually better to leave it in factored form to help me simplify later. Now I can rewrite each of my two rational expressions by multiplying by whatever's missing from the denominator in terms of the least common denominator. So what I mean is I can rewrite 3 over 2x plus 2. I'll write the 2x plus 2 as 2 times x plus 1. I'll write it in factored form. And then I notice that compared to the least common denominator, I'm missing the factor of x minus 1. So I multiply the numerator and the denominator by x minus 1. I just need it in the denominator, but I can't get away with just multiplying by the denominator without changing my expression. I have to multiply by it on the numerator and the denominator, so I'm just multiplying by 1 in a fancy form and not changing the value here. So now I do the same thing for the second rational expression. I'll write the denominator in factored form to make it easier to see what's missing from the denominator. What's missing in this denominator compared to my least common denominator is just the factor 2. So I'll multiply the numerator and the denominator by 2. Now I can rewrite everything. So the first rational expression becomes 3 times x minus 1 over 2 times x plus 1, x minus 1. And the second one becomes 5 times 2 over 2 times x plus 1, x minus 1. Notice that I now have a common denominator, so I can just add together my numerators. So I get 3 times x minus 1 plus 10 over 2 times x plus 1, x minus 1. I'd like to simplify this, and the best way to do that is to leave the denominator in factored form, but I do have to multiply out the numerator so that I can add things together. So I get 3x minus 3 plus 10 over 2 times x plus 1, x minus 1, or 3x plus 7 over 2 times x plus 1, x minus 1. Now 3x plus 7 doesn't factor, and there's therefore no factors that I can cancel out. So this is already reduced as much as it can be. This is my final answer. In this video, we saw how to simplify rational expressions to lowest terms by factoring and canceling common factors. We also saw how to multiply rational expressions by multiplying the numerator and multiplying the denominator, how to divide rational expressions by flipping and multiplying, and how to add and subtract rational expressions by writing them in terms of the least common denominator. This video is about solving quadratic equations. A quadratic equation is an equation that contains the square of the variable. say x squared, but no higher powers of x. The standard form for a quadratic equation is the form ax squared plus bx plus c equals 0, where a, b, and c represent real numbers. And a is not 0, so that we actually have an x squared term. Let me give you an example. 3x squared plus 7x minus 2 equals 0 is a quadratic equation in standard form. Here a is 3, b is 7, and c is minus 2. The equation 3x squared equals minus 7x plus 2 is also a quadratic equation. It's just not in standard form. The key steps to solving quadratic equations are usually to write the equation in standard form and then either factor it or use the quadratic formula, which I'll show you later in this video. Let's start with the example y squared equals 18 minus 7y. Here our variable is y, and we need to rewrite this quadratic equation in standard form. We can do this by subtracting 18 from both sides and adding 7y to both sides. That gives us the equation y squared minus 18 plus 7y equals 0. And I can rearrange a little bit to get y squared plus 7y minus 18 equals 0. Now I've got my equation in standard form. Next, I'm going to try to factor it. So I need to look for two numbers that multiply to negative 18 and add to 7. Two numbers that work are 9 and negative 2, so I can factor my expression on the left as y plus 9 times y minus 2 equals 0. Now, anytime you have two quantities that multiply together to give you 0, either the first quantity has to be 0 or the second quantity has to be 0, or I suppose they both could be 0 in some situations. This is really handy because that means that I know that either y plus 9 equals 0 or y minus 2 equals 0. So I can, as my next step, set my factors equal to 0. So y plus 9 equals 0 or y minus 2 equals 0, which means that y equals negative 9 or y equals 2. It's not a bad idea to check that those answers actually work by plugging them into the original equation. Negative 9 squared, does that equal 18 minus 7 times negative 9? And you can work out that it does. And similarly, 2 squared equals 18 minus 7 times 2. In the next example, let's find solutions of the equation w squared equals 121. This is a quadratic equation because it's got a square of my variable w. I can rewrite it in standard form by subtracting 121 from both sides. Notice that a is equal to 1, b is equal to 0 because there's no w term, and c is equal to negative 121 in the standard form aw squared plus bw plus c equals 0. Next step, I'm going to try to factor this expression. So since 121 is 11 squared, this is a difference of two squares, and it factors as w plus 11 times w minus 11 is equal to 0. If I set the factors equal to 0, I get w plus 11 equals 0 or w minus 11 equals 0, so w equals minus 11 or w equals 11. In this example, I could have solved the equation more simply. I could have instead said that if w squared is 121, then w has to equal plus or minus the square root of 121. In other words, w is plus or minus 11. If you solve the equation this way, it's important to remember the plus or minus, since minus 11 squared equals 121, just like 11 squared does. Now let's find the solutions for the equation x times x plus 2 equals 7. Some people might be tempted to say that, oh, if two numbers multiply to equal 7, then one of them better equal 1 and the other equals 7, or maybe negative 1 and negative 7. But that's faulty reasoning in this case, because x and x plus 2 don't have to be whole numbers. They could be crazy fractions or even irrational numbers. So instead, let's rewrite this equation in standard form. To do that, I'm first going to multiply out. So x times x is x squared, x times 2 is 2x, that equals 7, and I'll subtract the 7 from both sides to get x squared plus 2x minus 7 is 0. Now I'm looking to factor it, so I need two numbers that multiply to negative 7 and add to 2. Since the only way to factor negative 7 is as negative 1 times 7 or 7 times negative 1, it's easy to see that there are no whole numbers that will work. So there's no way to factor this expression over the integers. Instead, let's use the quadratic equation. So we have our leading coefficient of x squared is 1. So a is 1, b is 2, and c is minus 7. And we're going to plug that into the quadratic equation, which goes x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Different people have different ways of remembering this formula. I'd like to remember it by singing it. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. But you can use any mnemonic you like. Anyway, plugging in here, we have x equals negative 2 plus or minus the square root of 2 squared minus 4 times 1 times negative 7. It's important to remember the negative 7 there. All over 2 times 1. Now 2 squared is 4, and 4 times 1 times negative 7 is negative 28. So this whole quantity under the square root sign becomes 4 minus negative 28, or 32. So I can rewrite this as x equals negative 2 plus or minus the square root of 32 all over 2. Since 32 is 16 times 2, and 16 is a perfect square, I can rewrite this as negative 2 plus or minus the square root of 16 times the square root of 2 over 2, which is negative 2 plus or minus 4 times the square root of 2 over 2. Next, I'm going to split out my fraction as negative 2 over 2 plus or minus 4 square root of 2 over 2, and then simplify those fractions. This becomes negative 1 plus or minus 2 square root of 2. So my answers are negative 1 plus 2 square root of 2 and negative 1 minus 2 square root of 2. And if I need a decimal answer for any reason, I could work those out on my calculator. As our final example, let's find all real solutions for the equation 1/2 y squared equals 1/3 y minus 2. I'll start as usual by putting it in standard form. So that gives me 1/2 y squared minus 1/3 y plus 2 equals 0. I could go ahead and start trying to factor or use the quadratic formula right now, but I find fractional coefficients kind of annoying, so I'd like to get rid of them by doing what I call clearing the denominator. That means I'm going to multiply the whole entire equation by the least common denominator. In this case, the least common denominator is 2 times 3, or 6. So I'll multiply the whole equation by 6. I have to make sure I multiply both sides of the equation, but in this case, 6 times 0 is just 0. And when I distribute the 6, I get 3y squared minus 2y plus 12 equals 0. Now I could try to factor this, but I think it's easier probably just to plunge in and use the quadratic formula. So I get x equals negative b, that's negative negative 2, or 2, plus or minus the square root of b squared, minus 4 times a times c, all over 2a. Working out the stuff under the square root sign, negative 2 squared is 4, and here we have, let's see, 144. So this simplifies to x equals 2 plus or minus the square root of 4 minus 144, that's negative 140 all over 6. Well, if you're concerned about the negative number under the square root sign, you should be. We can't take the square root of a negative number and get a real number as our answer. There's no real number whose square is a negative number. And therefore, our conclusion is we have no real solutions to this quadratic equation. In this video, we solved some quadratic equations by first writing them in standard form and then either factoring or using the quadratic formula. In some examples, factoring doesn't work. It's not possible to factor the equation. But in fact, using the quadratic formula will always work, even if it's also possible to solve it by factoring. So you can't really lose by using the quadratic formula. It's just sometimes it'll be faster to factor instead. This video is about solving rational equations. A rational equation, like this one, is an equation that has rational expressions in it. In other words, an equation that has some variables in the denominator. There are several different approaches for solving a rational equation, but they all start by finding the least common denominator. In this example, the denominators are x plus 3 and x. We can think of 1 as just having a denominator of 1. Since the denominators don't have any factors in common, I can find the least common denominator just by multiplying them together. My next step is going to be clearing the denominator. By this, I mean that I multiply both sides of my equation by this least common denominator, x plus 3 times x. So I multiply it on the left side of the equation, and I multiply by the same thing on the right side of the equation. Since I'm doing the same thing to both sides of the equation, I don't change the value of the equation. Multiplying the least common denominator on both sides of the equation is equivalent to multiplying it by all three terms in the equation. I can see this when I multiply out. I'll rewrite the left side the same as before pretty much, and then I'll distribute the right side to get x plus 3 times x times 1 plus x plus 3 times x times 1 over x. So I've actually multiplied the least common denominator by all three terms of my equation. Now I can have a blast canceling things. The x plus 3 cancels with the x plus 3 on the denominator. Here nothing cancels out because there's no denominator, and here the x in the numerator cancels with the x in the denominator. So I can rewrite my expression as x squared equals x plus 3 times x times 1 plus x plus 3. Now I'm going to simplify. So I'll leave the x squared alone. On this side I'll distribute out x squared plus 3x plus x plus 3. Hey, look, the x squareds cancel on both sides, and so I get 0 equals 4x plus 3. So 4x is negative 3 and x is negative 3/4. Finally, I'm going to plug in my answer to check. This is a good idea for any kind of equation, but it's especially important for a rational equation because occasionally for rational equations you'll get what's called extraneous solutions, solutions that don't actually work in your original equation because they make the denominator 0. Now in this example, I don't think we're going to get any extraneous equations because negative 3/4 is not going to make any of these denominators 0. So it should work out fine when I plug in. If I plug in, I get this. I can simplify the denominator here. Negative 3/4 plus 3. 3 is 12/4, so that becomes 9/4. And this is 1. I'll flip and multiply to get minus 4/3. So here I can simplify my complex fraction. It ends up being negative 3/9, and 1 minus 4/3 is negative 1/3, so that all seems to check out. And so my final answer is x equals negative 3/4. This next example looks a little trickier, and it is, but the same approach will work. First, I'll find the least common denominator. So here my denominators are c minus 5, c plus 1, and c squared minus 4c minus 5. I'm going to factor that as c minus 5 times c plus 1. Now my least common denominator needs to have just enough factors that each of these denominators divide into it. So I need the factor c minus 5, I need the factor c plus 1, and now I've already got all the factors I need for this denominator. So here is my least common denominator. Next step is to clear the denominators. So I do this by multiplying both sides of the equation by my least common denominator. In fact, I can just multiply each of the three terms by this least common denominator. I went ahead and wrote my third denominator in factored form to make it easier to see what cancels. Now canceling time, that dies, this dies, and both of those factors die. Canceling out the denominator is the whole point of multiplying by the least common denominator. You're multiplying by something that's big enough to kill every single denominator, so you don't have to deal with denominators anymore. Now I'm going to simplify by multiplying out. So I get, let's see, c plus 1 times 4c, that's 4c squared plus 4c. Now I get minus, just c minus 5. And then over here I get 3c squared plus 3. I can rewrite the minus quantity c minus 5 as minus c plus 5. And now I can subtract the 3c squared from both sides to get just a c squared over here. And the 4c minus c, that becomes a 3c. And finally, I can subtract the 3 from both sides to get c squared plus 3c plus 2 equals 0. I've got myself a quadratic equation, and it looks like a nice one that factors. So this factors to c plus 1 times c plus 2 equals 0. So either c plus 1 is 0 or c plus 2 is 0. So c equals negative 1 or c equals negative 2. Now let's see, we need to still check our answers. Without even going to the trouble of calculating anything, I can see that c equals negative 1 is not going to work. Because if I plug it in to this denominator here, I get a denominator of 0, which doesn't make sense. So c equals minus 1 is an extraneous solution. It doesn't actually satisfy my original equation. And so I can just cross it right out. C equals negative 2. I can go, if I go ahead, and that doesn't make any of my denominators 0, so if I haven't made any mistakes, it should satisfy my original equation. But I'll just plug it in to be sure. And after some simplifying, I get a true statement. So my final answer is C equals negative 2. In this video, we solved a couple of rational equations using the method of finding the least common denominator and then clearing the denominator. We cleared the denominator by multiplying both sides of the equation by the least common denominator, or equivalently, multiplying each of the terms by that denominator. There's another equivalent method that some people prefer. It still starts out the same. We find the least common denominator, but then we write all the fractions over that least common denominator. So in this example, we'd still use the least common denominator of x plus 3 times x, but our next step would be to write each of these rational expressions over that common denominator by multiplying the top and the bottom by the appropriate things. So 1, in order to get the common denominator of x plus 3x, I need to multiply the top and the bottom by x plus 3 times x. 1 over x, I need to multiply the top and the bottom just by x plus 3, since that's what's missing from the denominator x. Now if I simplify a little bit, let's see, this is x squared over that common denominator, and here I have just x plus 3 times x over that denominator, and here I have x plus 3 over that common denominator. Now I'll add together my fractions on the right side, so they have a common denominator. So this is x plus 3 times x plus x plus 3. And now I have two fractions that are equal, that have the same denominator, therefore their numerators have to be equal also. So the next step is to set the numerators equal. So I get x squared is x plus 3 times x plus x plus 3. And if you look back at the previous way we solved this equation, you'll recognize this equation. And so from here on, we just continue as before. When choosing between these two methods, I personally tend to prefer the clear the denominators method because it's a little bit less writing. You get rid of those denominators earlier. You don't have to write them as many times. But some people find this one a little bit easier to remember, a little easier to understand. Either of these methods is fine. One last caution, don't forget at the end to check your solutions and eliminate any extraneous solutions. These will be solutions that make the denominators of your original equations go to 0. This video is about solving radical equations, that is, equations like this one that have square root signs in them, or cube roots, or any other kind of radical. When I see an equation with a square root in it, I really want to get rid of the square root. But it'll be easiest to get rid of the square root if I first isolate the square root. In other words, I want to get the term with the square root in it on one side of the equation by itself and everything else on the other side of the equation. If I start with my original equation, x plus the square root of x equals 12, and I subtract x from both sides, then that does isolate the square root term on the left side with everything else on the right. Once I've isolated the term with the square root, I'm going to get rid of the square root. And I'll do that by squaring both sides of my equation. So I'll take the square root of x equals 12 minus x and square both sides. Now the square root of x squared is just x. Taking the square root and then squaring, those operations undo each other. To work out 12 minus x squared, I'll write it out and distribute. 12 times 12 is 144. 12 times minus x is minus 12x. I get another minus 12x from here. And finally, minus x times minus x is positive x squared. So I can combine my minus 12x's, that's minus 24x. And now I can subtract x from both sides to get 0 equals 144 minus 25x plus x squared. That's a quadratic equation. I'll rewrite it in a little bit more standard form here. So now I've got a familiar quadratic equation with no radical signs left in my equation. I'll just proceed to solve it like I usually do for a quadratic. I'll try to factor it. So I'm going to look for two numbers that multiply to 144 and add to minus 25. Well, I know I'm going to need negative numbers to get to negative 25, and in fact I'll need two negative numbers so they still multiply to a positive number. So I'll start listing some factors of 144. I could have negative 1 and a negative 144, negative 2 and negative 72, negative 4, negative 36, and so on. Once I've listed out the possible factors, it's not hard to find the two that add to negative 25, so that's negative 9 and negative 16. So now I can factor my quadratic equation as x minus 9 times x minus 16 equals 0. That means that x minus 9 is 0 or x minus 16 is 0, so x equals 9 or x equals 16. I'm almost done, but there's one last very important step, and that's to check the solutions so that we can eliminate any extraneous solutions. An extraneous solution is a solution that we get that does not actually satisfy our original equation, and extraneous solutions can happen when you're solving equations with radicals in them. So let's first check x equals 9. If we plug in to our original equation, we get 9 plus the square root of 9, and we want that to equal 12. Well, the square root of 9 is 3, and 9 plus 3 does indeed equal 12, so that solution checks out. Now let's try x equals 16. Plugging in, we get 16 plus the square root of 16, and that's supposed to equal 12. Well, that says 16 plus 4 is supposed to equal 12, but that most definitely is not true. And so x equals 16 turns out to be an extraneous solution, and our only solution is x equals 9. This next equation might not look like an equation involving radicals, but in fact, we can think of a fractional exponent as being a radical in disguise. Let's start by doing the same thing we did on the previous problem by isolating. This time, we'll isolate the part of the equation that involves the fractional exponent. So I'll start with the original equation. 2 times p to the 4/5 equals 1/8, and I'll divide both sides by 2, or equivalently, I can multiply both sides by 1/2. That gives me p to the 4/5 equals 1/16, and I've effectively isolated the part of the equation with the fractional exponent as much as possible. Now, in the previous example, the next step was to get rid of the radical. In this example, we're going to get rid of the fractional exponent. And I'm going to actually do this in 2 stages. First, I'm going to raise both sides to the 5th power. That's because when I take an exponent to an exponent, I multiply my exponents, and so that becomes just p to the 4th equals 1/16 to the 5th power. Now I'm going to get rid of the 4th power by raising both sides to the 1/4 power, or by taking the 4th root. There's something that you need to be careful about, though. When taking an even root, or the 1 over an even number power, you always have to consider plus or minus your answer. It's kind of like when you write x squared equals 4 and you take the square root of both sides. X could equal plus or minus the square root of 4, right? X could equal plus or minus 2, since minus 2 squared is 4 just as well as 2 squared. So that's why when you take an even root, or a 1 over an even power of both sides, you always need to include the plus or minus sign. When it's an odd root, or 1 over an odd power, you don't need to do that. If you had something like x cubed equals -8, then x equals the cube root of -8, which is -2, would be your only solution. You don't need to do the plus or minus because +2 wouldn't work. So that aside explains why we need this plus or minus power. And now p to the 4 to the 1/4, when I raise a power to a power, I multiply by exponents. So that's just p to the 1, which is equal to plus or minus 1/16 to the 5th power to the 1/4 power. Now I just need to simplify this expression. I don't really want to raise 1/16 to the 5th power, because 16 to the 5th power is like a really huge number. So I think I'm actually going to rewrite this first as p equals plus or minus 1/16. I'll write it back as the 5/4 power again. And as I continue to solve using my exponent rules, I'm going to prefer to write this as 1/16 to the 4th root to the 5th power, because it's going to be easier to take the 4th root. Let's see, the 4th root of 1/16 is the same thing as the 4th root of 1 over the 4th root of 16. Raise all that to the 5th power. 4th root of 1 is just 1, and the 4th root of 16 is 2. Raise that to the 5th power. That's just going to be 1 to the 5th over 2 to the 5th, which is plus or minus 1/32. The last step is to check answers. So I have the two answers, p equals 1/32 and p equals minus 1/32. And if I plug those both in, 1/32 to the 4/5 power, that gives me 2 times 1 to the 4/5 power over 32 to the 4/5 power, which is 2 times 1 over 32 5th rooted to the 4th power. 5th root of 32 is 2. Raise that to the 4th power, I get 16. So this is 2 times 1/16, which is 1/8, just as we wanted in the original equation up here. Similarly, we can check that the p equals negative 1/32 actually does satisfy the equation. I'll leave that step to the viewer. So our two solutions are p equals 1 over 32 and p equals minus 1 over 32. I do want to point out an alternate approach to getting rid of the fractional exponent. We could have gotten rid of it all in one fell swoop by raising both sides of our equation to the 5/4 power. 5/4 is the reciprocal of 4/5. So when I use my exponent rules and say that when I raise the power to the power, I multiply my exponents, that gives me p to the 4/5 times 5/4 is plus or minus 1/16 to the 5/4. In other words, p to the 1 power, which is just p, is plus or minus 1/16 to the 5/4. So that's an alternate and possibly faster way to get to the solution. Once again, the plus or minus comes from the fact that when we take the 5/4 power, we're really taking an even root, a fourth root, and so we need to consider both positive and negative answers. This video is about solving radical equations, that is, equations like this one that have square root signs in them, or cube roots, or any other kind of radical. In this video, we solved radical equations by first isolating the radical sign or the fractional exponent, and then removing the radical sign or the fractional exponent by either squaring both sides or taking the reciprocal power of both sides. This video is about solving equations with absolute values in them. Recall that the absolute value of a positive number is just the number, but the absolute value of a negative number is its opposite. In general, I think of the absolute value of a number as representing its distance from 0 on the number line. The number 4 and the number -4 are both at distance 4 from 0, and so the absolute value of both of them is 4. Similarly, if I write the equation the absolute value of x is 3, that means that x has to be 3 units away from 0 on the number line. And so x would have to be either -3 or 3. Let's start with the equation 3 times the absolute value of x plus 2 equals 4. I'd like to isolate the absolute value part of the equation. I can do this by starting with my original equation, subtracting 2 from both sides, and dividing both sides by 3. Now I'll think in terms of distance. On a number line, the absolute value of x is 2/3, means that x is 2/3 away from 0. So x could be here or here, at -2/3 or at 2/3. And the answer to my equation is x is -2/3 or 2/3. I can check my answers by plugging in. 3 times the absolute value of -2/3 plus 2, I need to check if that equals 4. Well, the absolute value of -2/3 is just 2/3, so this is 3 times 2/3 plus 2, which works out to 4. Similarly, if I plug in positive 2/3, it also works out to give me a correct answer. This second example is a little different because the absolute value sign is around a more complicated expression, not just around the x. I would start by isolating the absolute value part, but it's already isolated. So I'll just go ahead and jump to thinking about distance on the number line. So on my number line, the whole expression 3x plus 2 is supposed to be at a distance of 4 from 0. So that means that 3x plus 2 is here at 4, or 3x plus 2 is at -4. I'll write those as equations. 3x plus 2 equals 4, or 3x plus 2 is -4, and then I can solve. So this becomes 3x equals 2, or x equals 2/3, and over here I get 3x equals -6, or x equals minus 2. Finally, I'll check my answers. I'll leave it to you to verify that they both work. A common mistake on absolute value equations is to get rid of the absolute value signs, like we did here, and then just solve for one answer instead of solving for both answers. Another mistake sometimes people make is once they get the first answer, they just assume that the negative of that works also. But that doesn't always work. In the first example, our two answers were both the negatives of each other, but in our second examples, our two answers were not just the opposites of each other. One was 2/3 and the other was -2. In this third example, let's again isolate the absolute value part of the equation. So starting with our original equation, we can subtract 16 from both sides and divide both sides by 5, or equivalently multiply by 1/5. Now let's think about distance on the number line. We have an absolute value needs to equal -3. So that means whatever is inside the absolute value sign needs to be at distance -3 from 0. Well, you can't be at distance -3 from 0. Another way of thinking about this is you can't have the absolute value of something and end up with a negative number. Absolute value is always positive or 0. So this equation doesn't actually make sense, and there are no solutions to this equation. In this video, we solved absolute value equations. In many cases, an absolute value equation will have two solutions. But in some cases, it'll have no solutions. And occasionally, it'll have just one solution.
This video is about interval notation, an easy and well-known way to record inequalities. Before dealing with interval notation, it is important to know how to deal with inequalities. Our first example of an inequality is written here, all numbers between 1 and 3, not including 1 and 3. First, we need to write down our variable, x. Then it is important to locate the key values. For this problem, that is 1 and 3. Now, here we see that x is between these two numbers, meaning we will have one inequality statement on each side of the variable. Here it says not including 1 and 3, which means that we do not have an or equal to sign beneath each inequality. Here we will put 1, the lowest key value, and here we will put 3, the highest key value. Next, we are going to graph this inequality on a number line. Here we write our key values, 1 and 3. Because it is not including 1 and 3, we have an empty circle around each number. Because it is the numbers between, we have a line connecting them. The last step of this problem is writing this inequality in interval notation. Writing things in interval notation is kind of like writing an ordered pair. Here we would put 1, and then here we would put 3. Next, we need to put brackets around these numbers. For this problem, it is not including 1 and 3, which means we will use soft brackets. However, if it were including 1 and 3, we would use hard brackets. It is important to note for interval notation that the smallest value always goes on the left and the biggest value always goes on the right. You also include a comma between your two key values. Now let's work on problem B. Once again, we write our variable x. Again, it is between -4 and 2, but this time it is including -4 and 2. This requires us to have the or equal to sign below the inequality. Then we put our lowest key value here and our highest here. The number line graph for this problem is slightly different. We still have our key values, -4 and 2, but instead of an open circle, like we have right here, we instead use a closed circle, representing that it is including -4 and 2. We complete this with a line in between. Last, we write this in interval notation. In the last problem, I said that for numbers including the outside values, we would use these hard brackets. Now we are actually using this. So we have our hard bracket on each side because it's including 4 and 2. Then we put our smallest value on the left and our highest value on the right with the comma in between. You now know how to correctly write these two types of intervals. Now we are going to practice transforming these from inequality notation to interval notation, and vice versa. This is slightly more difficult than our previous examples. Instead of having two soft brackets or two hard brackets, we'll have two different types. Now on the left side, we'll have a hard bracket because it is including the 3. However, on the right side, it is a soft bracket because it is not including the 1. Then we put our comma in the middle, a lower key value, and our higher key value. For the next problem, we are taking an equation already written in interval notation and putting it back into inequality notation. For the second problem, we can see our key values as being 5 and negative infinity. Now this sounds a little bit weird, but let's just set up our inequality. We have our variable x, which is less than, because of the soft bracket, 5, and greater than, without the or equal to, because it has a soft bracket there too, infinity. But because x is always greater than negative infinity, we can take out this part, leaving us with x is less than 5. It is important to note that a soft bracket always accompanies infinity. This is because infinity is not a real number, so we cannot include it, just go as far up to it as we can. The next problem is a little tricky because we don't see another key value over here, but let's just start off the equation. It has a soft bracket on this side due to the absence of an or equal to sign, and negative 15 is the lower key value. On the other side, we put the highest possible number, infinity, and then close it off with a soft bracket. We can see the relation of this to the previous problem and how it goes into this problem when x is greater than a key value instead of less than a key value. Once again, we have our soft bracket for infinity, which is always true. Part D brings up an important point about which number goes on the left. For all of our other problems, we have had the inequalities pointing left instead of right. When seeing part D, you might think, oh, 4 is on the left, so it would go here, and 0 is on the right, so it would go here. But that is not true. When writing inequalities, you must always have the lower value on the left, which for this problem is 0. To fix this, we can simply flip this inequality so it reads like this. It is still identical, just written in an easier form to transform it into interval notation. Then we can see that 0 has a soft bracket because it is not including 0. Put our comma, 4, our other key value, and a hard bracket because it is or equal to 4. For interval notation, you must always have the smaller number on the left side. This was our video on interval notation, an alternative way to write inequalities.
This video is about solving inequalities that have absolute value signs in them. Let's look at the inequality absolute value of x is less than 5 on the number line. Thinking of absolute value as distance, this means that the distance between x and 0 is less than 5 units. So x has to live somewhere in between negative 5 and 5. We can express this as an inequality without absolute value signs by saying negative 5 is less than x, which is less than 5. Or we can use interval notation, soft bracket, negative 5, 5, soft bracket. Both of these formulations are equivalent to the original one, but don't involve the absolute value signs. In the second example, we're looking for the values of x for which the absolute value of x is greater than or equal to 5. On the number line, this means that the distance of x from the 0 is got to be bigger than or equal to 5 units. A distance bigger than 5 units means that x has to live somewhere over here or somewhere over here, where it's farther than 5 units away from 0. Of course, x could also have a distance equal to 5 units, so I'll fill in that dot and shade in the other parts of the number line that satisfy my inequality. Now I can rewrite the inequality without the absolute value symbols by saying that x is less than or equal to -5 or x is greater than or equal to 5. I could also write this in interval notation, soft bracket -infinity -5 hard bracket, and the second part is hard bracket 5 infinity soft bracket. I combine these with a U for union because I'm trying to describe all these points on the number line together with all these other points. Let's take this analysis a step further with a slightly more complicated problem. Now I want the absolute value of 3 minus 2t to be less than 4. An absolute value less than 4 means a distance less than 4 on the number line. But it's not the variable t that lives in here at a distance of less than 4 from 0. It's the whole expression 3 minus 2t. So 3 minus 2t lives somewhere in here. And I can rewrite this as an inequality without absolute value signs by saying -4 is less than 3 minus 2t is less than 4. Now I have a compound inequality that I can solve the usual way. First I'll subtract 3 from all three sides to get -7 is less than -2t is less than 1. And now I'll divide all three sides by -2. Since -2 is a negative number, this reverses the directions of the inequalities. Simplifying, I get 7/2 is greater than t is greater than -1/2. So my final answer on the number line looks like all the stuff between -1/2 and 7/2, but not including the endpoints. And in interval notation, I can write this soft bracket -1/2, 7/2 soft bracket. Please pause the video and try the next problem on your own. Thinking in terms of distance, this inequality says that the distance between the expression 3 minus 2t and 0 is always bigger than 4. Let me draw this on the number line. If 3 minus 2t has a distance bigger than 4 from 0, then it can't be in this region that's near 0. It has to be on the outside, in one of these two regions. That is, 3 minus 2t is either less than -4 or 3 minus 2t is bigger than 4. I'll solve these two inequalities separately. The first one, subtracting 3 from both sides, I get -2t is less than -7. Dividing by -2, I get t is bigger than 7/2. And then on the other side, I get -2t is greater than 1, so t is less than -1/2. I had to flip inequalities in the last step due to dividing by a negative number. So let's check this out on the number line again. The first piece says that t is greater than 7/2. So I'll draw that over here. And the second piece says that t is less than -1/2. I'll draw that down here. Because these two statements are joined with an or, I'm looking for the t values that are in this one or in this one. That is, I want both of these regions put together. So in interval notation, this reads -infinity to -1/2, soft bracket, union, soft bracket, 7/2 to infinity. This last example looks more complicated, but if I simplify first and isolate the absolute value part, it looks pretty much like the previous ones. So I'll start by subtracting 7 from both sides, and then I'll divide both sides by 2. Now I'll draw my number line, and I'm looking for this expression, 4x plus 5, to always have distance greater than or equal to -3 from 0. Wait a second. Distance greater than or equal to -3? Well, distance is always greater than or equal to -3. It's always greater than or equal to 0. So this, in fact, is always true. And so the answer to my inequality is all numbers between -infinity and infinity. In other words, all real numbers. When solving absolute value inequalities, it's good to think about distance. An absolute value of something that's less than a number means that whatever's inside the absolute value signs is close to 0. On the other hand, an absolute value of something being greater than a number means that whatever's inside the absolute value sign is far away from 0, because its distance from 0 is bigger than a certain number. Drawing these pictures on the number line is a helpful way to rewrite the absolute value inequality as an inequality that doesn't contain an absolute value sign. In this case, it would be -3 is less than x plus 2 is less than 3, and in the other case, it would be either x plus 2 is less than -3 or x plus 2 is greater than 3. This video is about solving linear inequalities. Those are inequalities like this one that involve a variable, here x, but don't involve any x squared or other higher power terms. The good news is we can solve linear inequalities just like we'd solve linear equations, by distributing, adding and subtracting terms to both sides, and multiplying and dividing by numbers on both sides. The only thing that's different is that if you multiply or divide by a negative number, then you need to reverse the direction of the inequality. For example, if we had the inequality -x is less than -5, and we wanted to multiply both sides by -1 to get rid of the negative signs, we'd have to also switch or reverse the inequality. With this caution in mind, let's look at our first example. Since our variable x is trapped in parentheses, I'll distribute the -5 to free it from the parentheses. That gives me -5x minus 10 plus 3 is greater than 8. -10 plus 3 is -7, so I'll rewrite this as -5x minus 7 is greater than 8. Now I'll add 7 to both sides to get -5x is greater than 15. Now I'd like to divide both sides by -5. Since -5 is a negative number, that reverses the inequality. So I get x is less than 15 divided by -5. In other words, x is less than -3. If I wanted to graph this on a number line, I just need to put down a -3, an open circle around it, and shade in to the left. I use an open circle because x is strictly less than -3 and can't equal -3. If I wanted to write this in interval notation, I write it as soft bracket, -infinity, -3, soft bracket. Again, the soft bracket is because the -3 is not included. This next example is an example of a compound inequality. It has two parts. Either this statement is true or this statement is true. I want to find the values of x that satisfy either one. I'll solve this by working out each part separately and then combining them at the end. For the inequality on the left, I'll copy it over here, I'm going to add 4 to both sides, then subtract x from both sides, and then divide both sides by 2. I didn't have to reverse the inequality sign because I divided by a positive number. On the right side, I'll copy the equation over, subtract 1 from both sides, and divide both sides by 6. 9/6 is the same as 3/2. Now I'm looking for the x values that make this statement true or make this statement true. Let me graph this on a number line. X is less than or equal to -2 means I put a filled in circle there and graph everything to the left. x is greater than 3/2 means I put an empty circle here and shade in everything to the right. My final answer includes both of these pieces, which I'll reshade in green because x is allowed to be in either one or the other. Finally, I can write this in interval notation. The first piece on the number line can be described as soft bracket -infinity, -2, hard bracket, and the second piece can be described as soft bracket 3/2, infinity, soft bracket. To indicate that x can be in either one of these pieces, I use the union sign, which is a U. That means that my answer includes all x values in here together with all x values in here. This next example is also a compound inequality, this time joined by an and. The and means I'm looking for all y values that satisfy both this and this at the same time. Again, I can solve each piece separately. On the left, to isolate the y, I need to multiply by -3/2 on both sides. So that gives me y is less than -12 times -3/2. The greater than flipped to a less than because I was multiplying by -3/2, which is a negative number. If I clean up the right side, I get y is less than 18. On the right side, I'll start by subtracting 2 from both sides. And now I'll divide by -4. Again, a negative number, so that flips the inequality. So that's y is less than 3 over -4. In other words, y is less than -3/4. Again, I'm looking for the y values that make both of these statements true at the same time. Let me graph this on the number line. The y is less than 18. I can graph that by drawing the number 18. I don't want to include it, so I use an empty circle and I shade in everything to the left. The statement y is less than -3/4, I need to draw in -3/4, and again I don't include it, but I do include everything on the left. Since I want the y values for which both of these statements are true, I need the y values that are in both colored blue and colored red, and so that would be this part right here. I'll just draw it above so you can see it easily. So that would be all the numbers from -3/4 and lower, not including -3/4, since those are the parts of the number line that have both red and blue colors on them. In interval notation, my final answer will be soft bracket -infinity to -3/4 soft bracket. As my final example, I have an inequality that has two inequality signs in it. -3 is less than or equal to 6x minus 2 is less than 10. I can think of this as being a compound inequality with two parts. -3x is less than or equal to 6x minus 2, and at the same time, 6x minus 2 is less than 10. I could solve this in two pieces as before, but instead it's a little more efficient to just solve it all at once by doing the same thing to all three sides. So as a first step, I'll add 2 to all three sides. That gives me -1 is less than or equal to 6x is less than 12. And now I'm going to divide all three sides by 6 to isolate the x. So that gives me -1/6 is less than or equal to x is less than 2. If we'd solved it instead in two pieces above, we'd end up with the same thing, because we'd get -1/6 is less than or equal to x from this piece, and we'd get x is less than 2 on this piece, and because of the and statement, that's the same thing as saying -1/6 is less than or equal to x, which is less than 2. Either way we do it, let's see what it looks like on the number line. So on the number line, we're looking for things that are between 2 and -1/6, including the -1/6, but not including the 2. In interval notation, we can write this as hard bracket, -1/6, 2, soft bracket. In this video, we solved linear inequalities, including some compound inequalities, joined by the conjunctions and and or. Remember, when we're working with and, we're looking for places on the number line where both statements are true. That is, we're looking for the overlap on the number line. In this case, the points on the number line that are colored both red and blue at the same time. When we're working with or statements, we're looking for places where either one or the other statement is true, or both. On the number line, this corresponds to points that are colored either red or blue, or both, and in this picture, that would actually correspond to the entire number line. In this video, we'll solve inequalities involving polynomials, like this one, and inequalities involving rational expressions, like this one. Let's start with a simple example, maybe a deceptively simple example. If you see the inequality x squared is less than 4, you might be very tempted to take the square root of both sides and get something like x is less than 2 as your answer. But in fact, that doesn't work. To see why it's not correct, consider the x value of -10. -10 satisfies the inequality x is less than 2, since -10 is less than 2, but it doesn't satisfy the inequality x squared is less than 4, since -10 squared is 100, which is not less than 4. So these two inequalities are not the same, and it doesn't work to solve a quadratic inequality just to take the square root of both sides. You might be thinking part of why this reasoning is wrong is we've ignored the -2 option, right? If we had the equation x squared equals 4, then x equals 2 would just be one option, x equals -2 would be another solution. So somehow our solution to this inequality should take this into account. In fact, a good way to solve an inequality involving x squareds or higher power terms is to solve the associated equation first. But before we even do that, I like to pull everything over to one side so that my inequality has 0 on the other side. So for our equation, I'll subtract 4 from both sides to get x squared minus 4 is less than 0. Now, I'm going to actually solve the associated equation. X squared minus 4 is equal to 0. I can do this by factoring to x minus 2 times x plus 2 is equal to 0. And I'll set my factors equal to 0, and I get x equals 2 and x equals minus 2. Now, I'm going to plot the solutions to my equation on the number line. So I write down -2 and 2. Those are the places where my expression x squared minus 4 is equal to 0. Since I want to find where x squared minus 4 is less than 0, I want to know where this expression x squared minus 4 is positive or negative. A good way to find that out is to plug in test values. So first I'll plug in a test value in this area of the number line, something less than -2, say x equals -3. If I plug in -3 into x squared minus 4, I get -3 squared minus 4, which is 9 minus 4, which is 5. That's a positive number. So at -3, the expression x squared minus 4 is positive. And in fact, everywhere on this region of the number line, my expression is going to be positive, because it can't jump from positive to negative without going through a place where it's 0. I can figure out whether x squared minus 4 is positive or negative on this region and on this region of the number line by plugging in test values similarly. A value to plug in between -2 and 2, a nice value is x equals 0. 0 squared minus 4, that's -4, a negative number. So I know that my expression x squared minus 4 is negative on this whole interval. Finally, I can plug in something like x equals 10, something bigger than 2, and I get 10 squared minus 4. Without even computing that, I can tell that that's going to be a positive number, and that's all that's important. Again, since I want x squared minus 4 to be less than 0, I'm looking for the places on this number line where I'm getting negatives. So I'll shade that in on my number line. It's in here, not including the endpoints, because the endpoints are where my expression x squared minus 4 is equal to 0, and I want it strictly less than 0. I can write my answer as an inequality negative 2 is less than x is less than 2, or in interval notation as soft bracket negative 2 to soft bracket. Our next example we can solve similarly. First, we'll move everything to one side so that our inequality is x cubed minus 5x squared minus 6x is greater than or equal to 0. Next, we'll solve the associated equation by factoring. So first I'll write down the equation. Now I'll factor out an x, and now I'll factor the quadratic. So the solutions to my equation are x equals 0, x equals 6, and x equals negative 1. I'll write the solutions to the equation on the number line. So that's negative 1, 0, and 6. That's where my expression x times x minus 6 times x plus 1 is equal to 0. But I want to find where it's greater than or equal to 0, so again I can use test values. I can plug in, for example, x equals negative 2, either to this version of the expression or to this factored version. Since I only care whether my answer is positive or negative, it's sometimes easier to use the factored version. For example, when x is negative 2, this factor is negative. But this factor, x minus 6, is also negative when I plug in negative 2 for x. Finally, x plus 1, when I plug in negative 2 for x, that's negative 1, that's also negative, and a negative times a negative times a negative gives me a negative number. If I plug in something between negative 1 and 0, say x equals negative 1/2, then I'm going to get a negative for this factor, a negative for this factor, but a positive for this third factor. Negative times positive gives me a positive. For a test value between 0 and 6, let's try x equals 1. Now I'll get a positive for this factor, a negative for this factor, and a positive for this factor. A positive times a positive gives me a negative. Finally, for a test value bigger than 6, we could use, say, x equals 100. That's going to give me positive, positive, positive. So my product will be positive. Since I want values where my expression is greater than or equal to 0, I want the places where it equals 0 and the places where it's positive. So my final answer will be close bracket negative 1 to 0, close bracket, union, close bracket, 6 to infinity. As our final example, let's consider the rational inequality, x squared plus 6x plus 9 divided by x minus 1 is less than or equal to 0. Although it might be tempting to clear the denominator and multiply both sides by x minus 1, it's dangerous to do that because x minus 1 could be a positive number, but it could also be a negative number. And when you multiply both sides by a negative number, you have to reverse the inequality. Although it's possible to solve the inequality this way by thinking of cases where x minus 1 is less than 0 or bigger than 0, I think it's much easier just to solve the same way as we did before. So we'll start by rewriting so that we move all terms to the left and have 0 on the right. Well, that's already true. So the next step would be to solve the associated equation. That is, x squared plus 6x plus 9 over x minus 1 is equal to 0. That would be where the numerator is 0. X squared plus 6x plus 9 is equal to 0, so where x plus 3 squared is 0, or x equals negative 3. There's one extra step we have to do for rational expressions, and that's we need to find where the expression does not exist. That is, let's find where the denominator is 0, and that's at x equals 1. I'll put all those numbers on the number line, the places where my rational expression is equal to 0, and the place where my rational expression doesn't exist. Then I can start in with test values. For example, x equals minus 4, 0, and 2 work. if I plug those values into this expression here, I get a negative answer, and a positive answer. The reason I need to include the values on my number line where my denominator is 0 is because my expression can switch from negative to positive by passing through a place where my rational expression doesn't exist, as well as by passing through a place where my rational expression is equal to 0. Now I'm looking for where my original expression was less than or equal to 0, so that means I want the places on the number line where my expression is equal to 0, and also the places where it's negative. So my final answer is x is less than 1, or in interval notation, -infinity to 1. In this video, we solved polynomial and rational inequalities by making a number line and using test values to make a sign chart. The distance formula can be used to find the distance between 2 points if we know their coordinates. If this first point has coordinates x1, y1, and the second point has coordinates x2, y2, then the distance between them is given by the formula the square root of x2 minus x1 squared plus y2 minus y1 squared. This formula actually comes from the Pythagorean theorem. Let me draw a right triangle with these 2 points as 2 of its vertices. Then the length of this side is the difference between the 2 x-coordinates. Similarly, the length of this vertical side is the difference between the 2 y-coordinates. Now the Pythagorean theorem says that for any right triangle with sides labeled a and b and hypotenuse labeled c, we have that a squared plus b squared equals c squared. Well, if we apply that to this triangle here, this hypotenuse is the distance between the 2 points that we're looking for. So Pythagorean theorem says the square of this side length, that is x2 minus x1 squared, plus the square of this side length, which is y2 minus y1 squared, has to equal the square of the hypotenuse, that is d squared. Taking the square root of both sides of this equation, we get the square root of x2 minus x1 squared plus y2 minus y1 squared is equal to d. We don't have to worry about using plus or minus signs when we take the square root because distance is always positive. So we've derived our distance formula. Now let's use it in an example. Let's find the distance between the 2 points, -1, 5, so -1, 5, maybe over here, and 4, 2. This notation just means that P is the point with coordinates -1, 5, and Q is the point with coordinates 4, 2. We have the distance formula. Let's think of P being the point with coordinates x1, y1, and Q being the point with coordinates x2, y2. But as we'll see, it really doesn't matter which one is which. Plugging into our formula, we get d is the square root of x2 minus x1. So that's 4 minus -1 squared. And then we add y2 minus y1. So that's 2 minus 5 squared. Working out the arithmetic a little bit, 4 minus -1, that's 4 plus 1, or 5 squared, plus -3 squared. So that's the square root of 25 plus 9, or the square root of 34. Let's see what would have happened if we'd called this first point x2, y2 instead, and the second point x1, y1. Then we would have gotten the same distance formula, but we would have taken -1 minus 4 and added the difference of y's squared, so that's y2 5 minus 2 squared. So that gives us the square root of negative 5 squared plus 3 squared, which works out to the same thing. In this video, we use the distance formula to find the distance between 2 points. When writing down the distance formula, sometimes students forget whether this is a plus or a minus and whether these are pluses or minuses. One way to remember is to think that the distance formula comes from the Pythagorean theorem. That's why there's a plus in here and then a minus in here because we're finding the difference between the coordinates to find the lengths of the sides. The midpoint formula helps us find the coordinates of the midpoint of a line segment, as long as we know the coordinates of the endpoints. So let's call the coordinates of this endpoint x1, y1, and the coordinates of this other endpoint x2, y2. The x-coordinate of the midpoint is going to be exactly halfway in between the x-coordinates of the endpoints. To get a number halfway in between two other numbers, we just take the average. Similarly, the y-coordinate of this midpoint is going to be exactly halfway in between the y-coordinates of the endpoints. So the y-coordinate of the midpoint is going to be the average of those y-coordinates. So we see that the coordinates of the midpoint are x1 plus x2 over 2, y1 plus y2 over 2. Let's use this midpoint formula in an example. We want to find the midpoint of the segment between the points -1, 5 and 4, 2. Let me draw the line segment between them. So visually the midpoint is going to be somewhere around here. But to find its exact coordinates, we're going to use x1 plus x2 over 2 and y1 plus y2 over 2, where this first point is coordinates x1, y1, and the second point has coordinates x2, y2. It doesn't actually matter which point you decide is x1, y1 and which one is x2, y2. The formula will still give you the same answer for the midpoint. So let's see, I take my average of my x-coordinates, so that's -1 plus 4 over 2, and the average of my y-coordinates, so that's 5 plus 2 over 2, and I get 3/2, 7/2 as the coordinates of my midpoint. In this video, we use the midpoint formula to find the midpoint of a line segment just by taking the average of the x-coordinates and the average of the y-coordinates. This video is about graphs and equations of circles. Suppose we want to find the equation of a circle of radius 5 centered at the point 3, 2. It'll look something like this. For any point x, y on the circle, we know that the distance of that point x, y from the center is equal to the radius, that is 5. From the distance formula, that distance of 5 is equal to the square root of the difference of the x-coordinates, that's x minus 3 squared, plus the difference of the y-coordinates, that's y minus 2 squared. And if I square both sides of that equation, I get 5 squared is this square root squared. In other words, 25 is equal to x minus 3 squared plus y minus 2 squared, since the square root and the squared undo each other. A lot of times people will write the x minus 3 squared plus y minus 2 squared on the left side of the equation and the 25 on the right side of the equation. This is the standard form for the equation of this circle. This same reasoning can be generalized to find a general equation for a circle with radius r centered at a point hk. For any point with coordinates x, y on the circle, the distance between the point with coordinates xy and the point with coordinates hk is equal to the radius, r. So we have that the distance is equal to r, but by the distance formula, that's the square root of the difference between the x-coordinates, x minus h squared, plus the difference in the y-coordinates, y minus k squared. Squaring both sides as before, we get r squared is the square root squared. Canceling the square root and the squared and rearranging the equation, that gives us x minus h squared plus y minus k squared equals r squared. That's the general formula for a circle with radius r and center hk. Notice that the coordinates h and k are subtracted here. The two squares are added because they are in the distance formula, and the radius is squared on the other side. If you remember this general formula, that makes it easy to write down the equation for a circle. For example, if we want the equation for a circle of radius 6 and center at 0, -3, then we have r equals 6 and hk is our 0, -3. So plugging into the formula, we get x minus 0 squared plus y minus -3 squared equals 6 squared. Or simplified, this is x squared plus y plus 3 squared equals 36. Suppose we're given an equation like this one, and we want to decide if it's the equation of a circle, and if so, what's the center and what's the radius? Well, this equation matches the form for a circle, x minus h squared plus y minus k squared equals r squared, if we let h be 5, y be -6, since that way subtracting a -6 is like adding a 6. 5 must be our r squared, so that means that r is the square root of 5. So this is our radius, and our center is the point 5, -6. And this is indeed the equation for a circle, which we could then graph by putting down the center and estimating the radius, which is a little bit more than 2. This equation might not look like the equation of a circle, but it actually can be transformed to look like the equation of a circle. We're trying to make it look like something of the form x minus h squared plus y minus k squared equals r squared. First, I'd like to get rid of the coefficients in front of the x squared and the y squared, so I'm going to divide everything by 9. This gives me x squared plus y squared plus 8x minus 2y plus 4 equals 0. Next, I'm going to group the x terms together, the x squared and the 8x. So I'll write x squared plus 8x. I'll group the y terms together, the y squared minus 2y. And I'll subtract the 4 over to the other side. This still doesn't look much like the equation of a circle, but as the next step, I'm going to do something called completing the square. I'm going to take this coefficient of x, 8, divide it by 2, and then square it. In other words, 8 over 2 squared, that's 4 squared, which is 16. I'm going to add 16 to both sides of my equation. So I'll add the 16 here and on the other side. Now I'm going to do the same thing to the coefficient of y. -2 divided by 2 is -1. Square that and I get 1. So now I'm going to add a 1 to both sides, but I'll put it near the y terms. So add a 1 there, and then to keep things balanced, I have to add it to the other side. On the right side, I have the number 13. On the left side, I can wrap up this expression x squared plus 8x plus 16 into x plus 4 squared. To convince you that's correct, if we multiply out x plus 4 times x plus 4, we get x squared plus 4x plus 4x plus 16. or x squared plus 8x plus 16. The same thing we have right here. Similarly, we can wrap up y squared minus 2y plus 1 as y minus 1 squared. Again, I'll work out the distribution down here. That's y squared minus y plus 1, or y squared minus 2y plus 1, just like we have up here. If you're wondering how I knew to use 4 and minus 1, the 4 came from taking half of 8, and the minus 1 came from taking half the negative 2. Now we have an equation for a circle in standard form, and we can read off the center, which is negative 4, negative 1, and the radius, which is the square root of 13. It might seem like magic that this trick of taking half of this coefficient and squaring it and adding it to both sides lets us wrap up this expression into this expression, a perfect square. But to see why that works, let's take a look at what happens if we expand out x minus h squared, the thing that we're trying to get to. So if we expand that out, x minus h squared, which is x minus h times x minus h, which multiplies out to x squared minus hx plus h squared, or x squared minus 2hx plus h squared. Now if we start out with this part with some x squared term and some coefficient of x, and we're trying to decide what to add on in order to wrap it up into x minus h squared, the thing to add on is h squared here, which comes from half of this coefficient squared, right? Because half of negative 2h is negative h. Square that, you get the h squared. And then when we do wrap it up, it's half of this coefficient of x that appears right here. This trick of completing the square is really handy for turning an equation for a circle in disguise into the standard equation for the circle. In this video, we found the standard equation for a circle, x minus h squared plus y minus k squared equals r squared, where r is the radius and hk is the center. We also showed a method of completing the square. When you have an equation for a circle in disguise, completing the square will help you rewrite it into the standard form. This video is about graphs and equations of lines. Here we're given the graph of a line. We want to find the equation. One standard format for the equation of a line is y equals mx plus b. Here m represents the slope and b represents the y-intercept, the y value where the line crosses the y-axis. The slope is equal to the rise over the run, or sometimes this is written as the change in y values over the change in x values. Or in other words, y2 minus y1 over x2 minus x1, where x1, y1 and x2, y2 are points on the line. While we could use any 2 points on the line to find the slope, it's convenient to use points where the x and y coordinates are integers. That is, points where the line passes through grid points. So here would be one convenient point to use, and here's another convenient point to use. The coordinates of the first point are 1, 2, and the next point, this is, let's see, 5, negative 1. Now I can find the slope by looking at the rise over the run. So as I go through a run of this distance, I go through a rise of that distance. It's actually going to be a negative rise or a fall because my line is pointing down. So let's see, counting off squares, this is a run of 1, 2, 3, 4 squares and a rise of 1, 2, 3, so negative 3. So my slope is going to be negative 3 over 4. I got that answer by counting squares, but I could have also gotten it by looking at the difference in my y values over the difference in my x values. That is, I could have done negative 1 minus 2 that's from my difference in y values, and divide that by my difference in x values, which is 5 minus 1, that gives me negative 3 over 4 as before. So my m is negative 3/4. Now I need to figure out the value of b, my y-intercept. Well, I could just read it off the graph. It looks like approximately 2.75, but if I want to be more accurate, I can again use a point that has integer coordinates that I know its exact coordinates. So either this point or that point. Let's try this point. And I can start off with my equation y equals mx plus b, that is y equals negative 3/4 x plus b, and I can plug in the point 1, 2 for my x and y. So that gives me 2 equals negative 3/4 times 1 plus b. Solving for b, let's see, that's 2 equals negative 3/4 plus b. So add 3/4 to both sides. That's 2 plus 3/4 equals b. So b is 8/4 plus 3/4, which is 11/4, which is actually just what I eyeballed it to be. So now I can write out my final equation for my line, y equals negative 3/4 x plus 11/4, by plugging in for m and b. Next, let's find the equation for this horizontal line. A horizontal line has slope 0, so if we think of it as y equals mx plus b, m is going to be 0. In other words, it's just y equals b. Y is some constant. So if we can figure out what that constant y value is, it looks like it's 2, let's see, that's 3, 3.5. We can just write down the equation directly. Y equals 3.5. For a vertical line, like this one, it doesn't really have a slope. I mean, if you tried to do the rise over the run, there's no run. So I guess you'd be dividing by 0 and get an infinite slope. But instead, we just think of it as an equation of the form x equals something. And in this case, x equals negative 2. Notice that all of the points on our line have the same x-coordinate of negative 2, and the y-coordinate can be anything. So this is how we write the equation for a vertical line. In this example, we're not shown a graph of the line. We're just told that it goes through 2 points. But knowing that it goes through 2 points is enough to find the equation for the line. First, we can find the slope by taking the difference in y values over the difference in x values. So that's negative 3 minus 2 over 4 minus 1, which is negative 5/3. So we can use the standard equation for the line. This is called the slope-intercept form. And we can plug in negative 5/3, and we can use 1 point. Either one will do. We'll still get the same final answer. So let's use 1, 2 and plug that in to get 2 equals negative 5/3 times 1 plus b. And so b is 2 plus 5/3, which is 6/3, plus 5/3, which is 11/3. So our equation is y equals negative 5/3 x plus 11/3. This is method 1. Method 2 uses a slightly different form of the equation. It's called the point-slope form, and it goes y minus y naught is equal to m times x minus x naught, where x naught, y naught is a point on the line, and m, again, is the slope. So we calculate the slope the same way, by taking a difference in y values over a difference in x values, but then we can simply plug in any point. For example, the point 1, 2 will work. We can plug 1 in for x naught and 2 in for y naught in this point-slope form. That gives us y minus 2 is equal to minus 5/3 x minus 1. Notice that these two equations, while they may look different, are actually equivalent. because if I distribute the negative 5/3 and then add the 2 to both sides, I get the same equation as above. So we've seen two ways of finding the equation for the line, using the slope-intercept form and using the point-slope form. In this video, we saw that you can find the equation for a line if you know the slope and you know one point. You can also find the equation for the line if you know 2 points, because you can use the 2 points to get the slope and then plug in one of those points to figure out the rest of the equation. We saw two standard forms for the equation of a line. The slope-intercept form, y equals mx plus b, where m is the slope and b is the y-intercept, and the point-slope form, y minus y naught equals m times x minus x naught, where m again is the slope and x naught, y naught is a point on the line. This video is about finding parallel and perpendicular lines. Suppose we have a line of slope 3/4. In other words, the rise over the run is 3/4. Then any other line that's parallel to this line will have the same slope, the same rise over run. So that's our first fact to keep in mind. Parallel lines have the same slopes. Suppose, on the other hand, we want to find a line perpendicular to our original line with its original slope of 3/4. A perpendicular line, in other words, a line at a 90-degree angle to our original line, will have a slope that's the negative reciprocal, or the opposite reciprocal of our original slope. So we take the reciprocal of 3/4, that's 4/3, and we make it its opposite by changing it from positive to negative. So I'll write this as a principle that perpendicular lines have opposite reciprocal slopes. To get the hang of what it means to be an opposite reciprocal, let's look at a few examples. So here's the original slope, and this will be the opposite reciprocal, which would represent the slope of our perpendicular line. So for example, if m1 was 2, then the opposite reciprocal of 2 is 1/2. Opposite means I change the sign. If the first slope turned out to be, say, negative 1/3, the reciprocal of 1/3 is 3/1, or just 3, and the opposite means I change it from a negative to a positive. So my perpendicular slope would be 3. One more example, if I started off with the slope of, say, 7/2, then the reciprocal of that would be 2/7, and I change it to an opposite reciprocal by changing the positive to a negative. Let's use these two principles in some examples. In our first example, we need to find the equation of a line that's parallel to this one and goes through the point -3, 2. Well, in order to get started, I need to figure out the slope of this line. So let me put this line into a more standard form, the slope-intercept form. So I'll start with 3y minus 4x plus 6 equals 0. I'm going to solve for y to put it in this more standard form. So I'll say 3y equals 4x minus 6, and then divide by 3 to get y equals 4/3 x minus 6/3. I've divided all my terms by 3. I can simplify that a little bit. Y equals 4/3 x minus 2. Now I can read off the slope of my original line, and 1 is 4/3. That means my slope of my new line, my parallel line, will also be 4/3. So my new line will have the equation y equals 4/3 x plus b for some b. Of course, b will probably not be -2 like it was for the first line. It'll be something else determined by the fact that it goes through this point -3, 2. To figure out what b is, I'll plug in the point -3, 2 for negative 3 for x and 2 for y. So that gives me 2 equals 4/3 times negative 3 plus b, and I'll solve for b. So let's see, first let me just simplify. So 2 equals, this is negative 12/3 plus b, or in other words, 2 is negative 4 plus b, so that means that b is going to be 6. And my parallel line will have the equation y equals 4/3 x plus 6. Next, let's find the equation of a line that's perpendicular to a given line and go through a given point. Again, in order to get started, I need to find what the slope of this given line is. So I'll rewrite it. Well, first I'll just copy it over. 6x plus 3y equals 4. And then I can put it in the standard slope-intercept form by solving for y. So 3y is negative 6x plus 4. Divide everything by 3, I get y equals negative 6/3 x plus 4/3. So y is negative 2x plus 4/3. So on my original slope of my original line is negative 2, which means my perpendicular slope is the opposite reciprocal. So I take the reciprocal of negative 2, that's negative 1/2, and I change the sign, so that gives me 1/2 as the slope of my perpendicular line. Now my new line, I know it's going to be y equals 1/2 x plus b for some b, and I can plug in my point on my new line, so 1 for y and 4 for x, and solve for b. So I get 1 equals 2 plus b, so b is negative 1, and so my new line has equation 1/2 x minus 1. These next two examples are a little bit different because now we're looking at a line parallel to a completely horizontal line. Let me draw this line, y equals 3. So the y coordinate is always 3, which means that my line will be a horizontal line through at height y equals 3. If I want something parallel to this line, it will also be a horizontal line. Since it goes through the point negative 2, 1, let's see, negative 2, 1, it has to go through that point there. It's going to always have a y-coordinate of 1, the same as the y-coordinate of the point it goes through. So my answer will just be y equals 1. In the next example, we want a line that's perpendicular to the line y equals 4, another horizontal line, y equals 4. But perpendicular means I'm going to need a vertical line. So I need a vertical line that goes through the point 3, 4. Okay, and so I'm going to draw a vertical line there. Now vertical lines have the form x equals something for their equation. And to find what x equals, I just need to look at the x-coordinate of the point I'm going through. That's point 3, 4. So that x-coordinate is 3, and all the points on this perpendicular and vertical line have x-coordinate 3, so my answer is x equals 3. In this video, we use the fact that parallel lines have the same slope and perpendicular lines have opposite reciprocal slopes to find the equations of parallel and perpendicular lines. This video introduces functions and their domains and ranges. A function is a correspondence between input numbers, usually the x values, and output numbers, usually the y values, that sends each input number to exactly one output number. Sometimes a function is thought of as a rule or machine in which you can feed in x values as input and get out y values as output. So a non-mathematical example of a function might be the biological mother function, which takes as input any person and gives as output their biological mother. This function satisfies the condition that each input number, object, person in this case, gets sent to exactly one output person, because if you take any person, they just have one biological mother. So that rule does give you a function, But if I change things around and just use the mother function, which sends to each person their mother, that's no longer going to be a function, because there are some people who have more than one mother, right? They could have a biological mother and adopted mother, or a mother and a stepmother, or any number of situations. So since there's at least some people who you would put it as input and then you'd get like more than one possible output, that violates this rule of functions. It would not be a function. Now, most of the time, we'll work with functions that are described with equations, not in terms of mothers. So, for example, we could have the function y equals x squared plus 1. This can also be written as f of x equals x squared plus 1. Here, f of x is function notation that stands for the output value of y. Notice that this notation is not representing multiplication. We're not multiplying f by x. Instead, we're going to be putting in a value for x as input and getting out a value of f of x or y. For example, if we want to evaluate f of 2, we're plugging in 2 as input for x, either in this equation or in that equation, since f of 2 means 2 squared plus 1, f of 2 is going to equal 5. Similarly, f of 5 means I plug in 5 for x, so that's going to be 5 squared plus 1, or 26. Sometimes it's useful to evaluate a function on a more complicated expression involving other variables. In this case, remember, the function's value on any expression is just what you get when you plug in that whole expression for x. So f of a plus 3 is going to be the quantity a plus 3 squared plus 1. We could rewrite that as a squared plus 6a plus 9 plus 1, or a squared plus 6a plus 10. When evaluating a function on a complex expression, it's important to keep the parentheses when you plug in for x. That way, you evaluate the function on the whole expression. For example, it would be wrong to write f of a plus 3 equals a plus 3 squared plus 1 without the parentheses, because that would imply we were just squaring the 3 and not the whole expression a plus 3. Sometimes a function is described with a graph instead of an equation. In this example, this graph is supposed to represent the function g of x. Not all graphs actually represent functions. For example, the graph of a circle doesn't represent a function. That's because the graph of a circle violates the vertical line test. You can draw a vertical line and it'll intersect the graph in more than one point. But our graph at left satisfies the vertical line test. Any vertical line intersects the graph in at most one point. That means it's a function because every x value will have at most one y value that corresponds to it. Let's evaluate g of 2. Note that 2 is an x value, and we'll use the graph to find the corresponding y value. So I look for 2 on the x-axis and find the point on the graph that has that x value. It's right here. Now I can look at the y value of that point, looks like 3, and therefore g of 2 is equal to 3. If I try to do the same thing to evaluate g of 5, I run into trouble. 5 is an x value. I look for it on the x-axis, but there's no point on the graph that has that x value. Therefore, g of 5 is undefined, or we can say it does not exist. The question of what x values and y values make sense for a function leads us to a discussion of domain and range. The domain of a function is all possible x values that make sense for that function. The range is the y values that make sense for the function. In this example, we saw that the x value of 5 didn't have a corresponding y value for this function. So the x value of 5 is not in the domain of our function g. To find the x values in the domain, we have to look at the x values that correspond to points on the graph. One way to do that is to take the shadow or projection of the graph onto the x-axis and see what x values are hit. It looks like we're hitting all x values starting at -8 and continuing up to 4. So our domain is the x's between -8 and 4, including those endpoints, or we can write this in interval notation as -8, 4 with square brackets. To find the range of the function, we look for the y values corresponding to points on this graph. We can do that by taking the shadow or projection of the graph onto the y-axis. We seem to be hitting all y values from -5 up through 3. So our range is y's between -5 and 3, or in interval notation, -5, 3 with square brackets. If we meet a function that's described as an equation instead of a graph, one way to find the domain and range are to graph the function. But it's often possible to find the domain, at least, more quickly by using algebraic considerations. We think about what x values it makes sense to plug into this expression and what x values need to be excluded because they make the algebraic expression impossible to evaluate. Specifically, to find the domain of a function, we need to exclude x values that make the denominator 0, since we can't divide by 0. We also need to exclude x values that make an expression inside a square root sign negative, since we can't take the square root of a negative number. In fact, we need to exclude values that make an expression inside any even root negative, because we can't take an even root of a negative number, even though we can take an odd root, like a cube root of a negative number. Later, when we look at logarithmic functions, we'll have some additional exclusions that we have to make. But for now, these two principles should handle all functions we'll see. So let's apply them to a couple examples. For the function in part A, we don't have any square root signs, but we do have a denominator. So we need to exclude x values that make the denominator 0. In other words, we need x squared minus 4x plus 3 to not be equal to 0. If we solve x squared minus 4x plus 3 equal to 0, we can do that by factoring, and that gives us x equals 3 or x equals 1, so we need to exclude these values. All other x values should be fine, so if I draw the number line, I can put on 1 and 3 and just dig out a hole at both of those, and my domain includes everything else on the number line. In interval notation, this means my domain is everything from -infinity to 1 together with everything from 1 to 3 together with everything from 3 to infinity. In this second example, we don't have any denominators to worry about, but we do have a square root sign. So we need to exclude any x values that make 3 minus 2x less than 0. In other words, we can include all x values for which 3 minus 2x is greater than or equal to 0. Solving that inequality gives us 3 is greater than or equal to 2x. In other words, x is less than or equal to 3/2. I can draw this on the number line or write it in interval notation. Notice that 3/2 is included, and that's because 3 minus 2x is allowed to be 0. I can take the square root of 0. It's just 0, and that's not a problem. Finally, let's look at a more complicated function that involves both a square root and a denominator. Now there are two things I need to worry about. I need the denominator to not be equal to 0, and I need the stuff inside the square root sign to be greater than or equal to 0. From our earlier work, we know that the first condition means that x is not equal to 3 and x is not equal to 1, and the second condition means that x is less than or equal to 3/2. Let's draw both of those conditions on the number line. X is not equal to 3 and x is not equal to 1 means we've got everything except those two dug out points. And the other condition, x is less than or equal to 3/2, means we can have 3/2 and everything to the left of it. Now, to be in our domain and to be legit for our function, we need both of these conditions to be true. So I'm going to connect these conditions with an AND. And that means we're looking for numbers on the number line that are colored both red and blue. So I'll draw that above in purple. So that's everything from 3/2 to 1. I have to dig out 1 because 1 was a problem for the denominator. And then I can continue for all the things that are colored both colors, red and blue. So my final domain is going to be, let's see, negative infinity up to but not including 1 together with 1 but not including it to 3/2, and I include 3/2 since that was colored both red and blue also. In this video, we talked about functions, how to evaluate them, and how to find domains and ranges. This video gives the graphs of some commonly used functions that I call the toolkit functions. The first function is the function y equals x. Let's plot a few points on the graph of this function. If x is 0, y is 0. If x is 1, y is 1. And so on, y is always equal to x. It doesn't have to just be an integer, it can be any real number. And connecting the dots, we get a straight line through the origin. Let's look at the graph of y equals x squared. If x is 0, y is 0, so we go through the origin again. If x is 1, y is 1. And if x is negative 1, y is also 1. The x value of 2 gives a y value of 4, and the x value of negative 2 gives a y value of 4 also. Connecting the dots, we get a parabola. Notice this function is an even function. That means it has mirror symmetry across the y-axis. The left side looks exactly like the mirror image of the right side. That happens because when you square a positive number like 2, you get the exact same y value as when you square its mirror image x value of negative 2. The next function, y equals x cubed, I'll call that a cubic. Let's plot a few points. When x is 0, y is 0. When x is 1, y is 1. When x is negative 1, y is negative 1. 2 goes with the point 8 way up here, and an x value of negative 2 is going to give us negative 8. If I connect the dots, I get something that looks kind of like this. This function is what's called an odd function because it has 180-degree rotational symmetry around the origin. If I rotate this whole graph by 180 degrees, or in other words, turn the paper upside down, I'll get exactly the same shape. The reason this function has this odd symmetry is because when I cube a positive number and get its y value, and cube the corresponding negative number to get its y value, the negative number cubed gives us exactly the negative of the y value we'd get with cubing the positive number. Let's look at the next example, y equals the square root of x. Notice that the domain of this function is just x values bigger than or equal to 0 because we can't take the square root of a negative number. Let's plug in a few x values. X is 0 gives y is 0. X is 1, square root of 1 is 1. Square root of 4 is 2. And connecting the dots, I get a function that looks like this. The absolute value function is next. Again, if we plug in a few points, x is 0 goes with y equals 0. X is 1 gives us 1. The absolute value of negative 1 is 1. 2 is on the graph, and the absolute value of negative 2 is 2. I'm ending up getting a V-shaped graph. It also has even or mirror symmetry. Y equals 2 to the x is what's known as an exponential function. That's because the variable x is in the exponent. If I plot a few points, 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 to the minus 1 is 1/2. I'll plot these on my graph. Let me fill in a few more points. So let's see, 2 cubed is 8, that's way up here, and negative 2 gives me 1/4, 1/8. Connecting the dots, I get something that's shaped like this. You might have heard the expression exponential growth when talking about, for example, population growth. This function represents exponential growth. It grows very, very steeply. Every time we increase the x-coordinate by 1, we double the y-coordinate. We could also look at a function like y equals 3 to the x, or sometimes y equals e to the x, where e is just a number about 2.7. These functions look very similar. It's just the bigger base makes us rise a little more steeply. Now let's look at the function y equals 1 over x. It's not defined when x is 0, but I can plug in x equals 1/2. 1 over 1/2 is 2. 1 over 1 is 1, and 1 over 2 is 1/2. If I connect the dots, I get this shape in the first quadrant, but I haven't looked at negative values of x. When x is negative, 1 over negative 1 is negative 1. 1 over negative 1/2 is negative 2, and I get a similar looking piece in the third quadrant. This is an example of a hyperbola, and it's also an odd function because it has that 180-degree rotational symmetry. If I turn the page upside down, it'll look exactly the same. Finally, let's look at y equals 1 over x squared. Again, it's not defined when x is 0, but I can plug in points like 1/2 for x. Let's see, 1 over 1/2 squared is 1 over 1/4, which is 4. And 1 over 1 squared, 1 over 2 squared is 1/4. It looks pretty much like the previous function. It's just a little bit more extreme, rises a little more steeply, falls a little more dramatically. But for negative values of x, something a little bit different goes on. For example, 1 over negative 2 squared is just 1 over 4, which is 1/4. So I can plot that point there. And 1 over negative 1 squared, that's just 1. So my curve for negative values of x is going to lie in the second quadrant, not the third quadrant. This is an example of an even function because it has perfect mirror symmetry across the y-axis. These are the toolkit functions, and I recommend you memorize the shape of each of them. That way you can draw at least a rough sketch very quickly without having to plug in points. That's all for the graphs of the toolkit functions. If we change the equation of a function, then the graph of the function changes or transforms in predictable ways. This video gives some rules and examples for transformations of functions. To get the most out of this video, it's helpful if you're already familiar with the graph of some typical functions. I call them toolkit functions, like y equals square root of x, y equals x squared, y equals the absolute value of x, and so on. If you're not familiar with those graphs, I encourage you to watch my video called Toolkit Functions first before watching this one. I want to start by reviewing function notation. If g of x represents the function the square root of x, then we can rewrite these expressions in terms of square roots. For example, g of x minus 2 is the same thing as the square root of x minus 2. G of quantity x minus 2 means we plug in x minus 2 everywhere we see an x. So that would be the same thing as the square root of quantity x minus 2. In this second example, I say that we're subtracting 2 on the inside of the function, because we're subtracting 2 before we apply the square root function. Whereas on the first example, I say that the minus 2 is on the outside of the function. We're doing the square root function first and then subtracting 2. In this third example, g of 3x, we're multiplying by 3 on the inside of the function. To evaluate this in terms of square root, we plug in the entire 3x for x in the square root function. That gives us the square root of 3x. In the next example, we're multiplying by 3 on the outside of the function. This is just 3 times the square root of x. Finally, g of minus x means the square root of minus x. This might look a little odd because we're not used to taking the square root of a negative number, but remember that if x itself is negative, like negative 2, then negative x will be negative negative 2 or positive 2, so we'll really be taking the square root of a positive number in that case. Let me record which of these are inside and which of these are outside of my function. In this next set of examples, we're using the same function, g of x is square root of x, but this time we're starting with an expression with square roots in it and trying to write it in terms of g of x. So the first example, the plus 17 is on the outside of my function because I'm taking the square root of x first and then adding 17. So I can write this as g of x plus 17. In the second example, I'm taking x and adding 12 first, then I take the square root of the whole thing. Since I'm adding the 12 to x first, that's on the inside of my function. So I write that as g of the quantity x plus 12. Remember that this notation means I plug in the entire x plus 12 into the square root sign, which gives me exactly square root of x plus 12. In this next example, I'm doing the square root first and then multiplying by negative 36. So my minus 36 multiplication is outside my function. I can rewrite this as minus 36 times g of x. Finally, in this last example, I take x, multiply by a fourth, and then apply the square root of x. So that's the same thing as g of 1/4 x. My 1/4 x is on the inside of my function. In other words, it's inside the parentheses when I use function notation. Let's graph the square root of x and two transformations of this function. Y equals the square root of x goes through the points 0, 0, 1, 1, and 4, 2, since the square root of 4 is 2, and looks something like this. In order to graph y equals the square root of x minus 2, notice that the minus 2 is on the outside of the function. That means we're going to take the square root of x first and then subtract 2. So for example, if we start with the x value of 0 and compute the square root of 0, that's 0, then we subtract 2 to give us a y value of negative 2. An x value of 1, which under the square root function had a y value of 1, now has a y value that's decreased by 2. 1 minus 2 is negative 1. And finally, an x value of 4, which under the square root function had a y value of 2, now has a y value of 2 minus 2, or 0. Its y value is also decreased by 2. If I plot these new points, 0 goes with negative 2, 1 goes with negative 1, and 4 goes with 0, I have my transformed graph. Because I subtracted 2 on the outside of my function, my y values were decreased by 2, which brought my graph down by 2 units. Next, let's look at y equals the square root of quantity x minus 2. Now we're subtracting 2 on the inside of our function, which means we subtract 2 from x first and then take the square root. In order to get the same y value of 0 as we had in our blue graph, we need our x minus 2 to be 0, so we need our original x to be 2. In order to get the y value of 1 that we had in our blue graph, we need to be taking the square root of 1. So we need x minus 2 to be 1, which means that we need to start with an x value of 3. And in order to reproduce our y value of 2 from our original graph, we need the square root of x minus 2 to be 2, which means we need to start out by taking the square root of 4, which means our x minus 2 is 4, so our x should be up there at 6. If I plot my x values with my corresponding y values of square root of x minus 2, I get the following graph. Notice that the graph has moved horizontally to the right by 2 units. To me, moving down by 2 units makes sense because we're subtracting 2, so we're decreasing y's by 2 units. But the minus 2 on the inside, that kind of does the opposite of what I expect. I might expect it to move the graph left. I might expect the x values to be going down by 2 units, but instead it moves the graph to the right, because the x units have to go up by 2 units in order to get the right square root when I then subtract 2 units again. The observations we made for these transformations of functions hold in general, according to the following rules. First of all, numbers on the outside of the function, like in our example y equals the square root of x minus 2, those numbers affect the y values and result in vertical motions, like we saw. These motions are in the direction you expect, so subtracting 2 moves us down by 2. If we were adding 2 instead, that would move us up by 2. Numbers on the inside of the function, that's like our example y equals the square root of quantity x minus 2, those affect the x values and result in a horizontal motion. These motions go in the opposite direction from what you expect. Remember, the minus 2 on the inside actually shifted our graph to the right. If it had had a plus 2 on the inside, that would actually shift our graph to the left. Adding results in a shift, those are called translations, but multiplying, like something like y equals 3 times the square root of x, that would result in a stretch or shrink. In other words, if I start with the square root of x and then want to graph y equals 3 times the square root of x, that stretches my graph vertically by a factor of 3. Like this. If I want to graph y equals 1/3 times the square root of x, that shrinks my graph vertically by a factor of 1/3. Finally, a negative sign results in reflection. For example, if I start with a graph of y equals the square root of x, and then want to graph y equals the square root of negative x, that's going to do a reflection in the horizontal direction because the negative is on the inside of the square root sign. A reflection in the horizontal direction means a reflection across the y-axis. If instead I want to graph y equals negative the square root of x, that negative sign on the outside means a vertical reflection, a reflection across the x-axis. Pause the video for a moment and see if you can describe what happens in these 4 transformations. In the first example, we're subtracting 4 on the outside of the function. Adding and subtracting means a translation or shift, and since we're on the outside of the function, it affects the y value, so that's moving us vertically. So this transformation should take the square root of graph and move it down by 4 units. That would look something like this. In the next example, we're adding 12 on the inside. That's still a translation, but now we're moving horizontally, and so since we go the opposite direction we expect, we are going to go to the left by 12 units. That's going to look something like this. In the next example, we're multiplying by 3 and introducing a negative sign, both on the outside of our function. Outside our function means we're affecting the y values. And multiplication means we're stretching by a factor of 3. The negative sign means we reflect in the vertical direction. Here's stretching by a factor of 3 vertically before I apply the minus sign, and now the minus sign reflects in the vertical direction. Finally, in this last example, we're multiplying by 1/4 on the inside of our function. We know that multiplication means stretch or shrink, and since we're on the inside, it's a horizontal motion, and it does the opposite of what we expect. So instead of shrinking by a factor of 1/4 horizontally, it's actually going to stretch by the reciprocal, a factor of 4 horizontally. That'll look something like this. Notice that stretching horizontally by a factor of 4 looks kind of like shrinking vertically by a factor of 1/2. And that's actually borne out by the algebra, because the square root of 1/4 x is the same thing as the square root of 1/4 times the square root of x, which is the same thing as 1/2 times the square root of x. And so now we can see algebraically that a vertical shrink by a factor of 1/2 is the same as a horizontal stretch by a factor of 4, at least for this function, the square root function. This video gave some rules for transformations of functions, which I'll repeat below. Numbers on the outside correspond to changes in the y values, or vertical motions. Numbers on the inside of the function affect the x values and result in horizontal motions. Adding and subtracting corresponds to translations, or shifts. Multiplying and dividing by numbers corresponds to stretches and shrinks. and putting in a negative sign corresponds to a reflection. A horizontal reflection if the negative sign is on the inside, and a vertical reflection if the negative sign is on the outside. Knowing these basic rules about transformations empowers you to be able to sketch graphs of much more complicated functions, like y equals 3 times the square root of x plus 2, by simply considering the transformations one at a time. A quadratic function is a function that can be written in the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers, and a is not equal to 0. The reason we require that a is not equal to 0 is because if a were equal to 0, we'd have f of x is equal to bx plus c, which is called a linear function. So by making sure that a is not 0, we make sure there's really an x squared term, which is the hallmark of a quadratic function. Please pause the video for a moment and decide which of these equations represent quadratic functions. The first function can definitely be written in the form g of x equals ax squared plus bx plus c. In fact, it's already written in that form, where a is -5, b is 10, and c is 3. The second equation is also a quadratic function because we can think of it as f of x equals 1 times x squared plus 0 times x plus 0. So it is in the right form, where a is 1, b is 0, and c is 0. It's perfectly fine for the coefficient of x and the constant term to be 0 for a quadratic function. We just need the coefficient of x squared to be non-zero, so that the x squared term is preserved. The third equation is not a quadratic function. It's a linear function, because there's no x squared term. The fourth function might not look like a quadratic function, but if we rewrite it by expanding out the x minus 3 squared, let's see what happens. We get y equals 2 times x minus 3 times x minus 3 plus 4. So that's 2 times x squared minus 3x plus 9 plus 4. Continuing, I get 2x squared minus 12x's plus 18 plus 4. In other words, y equals 2x squared minus 12x plus 22. So in fact, our function can be written in the right form, and it is a quadratic function. A function that is already written in the form y equals ax squared plus bx plus c is said to be in standard form. So our first example, g of x, is in standard form. A function that's written in the format of the last function, that is, in the form of y equals a times x minus h squared plus k for some numbers a, h, and k, that's said to be in vertex form. I'll talk more about standard form and vertex form in another video. In this video, we identified some quadratic functions and talked about the difference between standard form and vertex form. This video is about graphing quadratic functions. A quadratic function, which is typically written in standard form, like this, or sometimes in vertex form, like this, always has the graph that looks like a parabola. This video will show how to tell whether the parabola is pointing up or down, how to find its x-intercepts, and how to find its vertex. The bare-bones basic quadratic function is f of x equals x squared. It goes to the origin, since f of 0 is 0 squared, which is 0, and it is a parabola pointing upwards, like this. The vertex of a parabola is its lowest point if it's pointing upwards, and its highest point if it's pointing downwards. So in this case, the vertex is at 0, 0. The x-intercepts are where the graph crosses the x-axis. In other words, where y is 0. And in this function, y equals 0 means that x squared is 0, which happens only when x is 0. So the x-intercept, there's only one of them, is also 0. This second function, y equals negative 3x squared, also goes through the origin, since the function's value when x is 0 is y equals 0. But in this case, the parabola is pointing downwards. That's because, thinking about transformations of functions, a negative sign on the outside reflects the function vertically over the x-axis, making the parabola, instead of pointing upwards, reflecting to point downwards. The number 3 on the outside stretches the graph vertically by a factor of 3, so it makes it kind of long and skinny, like this. In general, a negative coefficient to the x squared term means the parabola will be pointing down, whereas a positive coefficient, like here the coefficient's 1, means the parabola is pointing up. I'll write that rule over here. So if a is bigger than 0, the parabola opens up, and if the value of the coefficient a is less than 0, then the parabola opens down. In this second example, we can see again that the vertex is at 0, 0, and the x-intercept is x equals 0. Let's look at this third example. If we multiplied our expression out, we'd see that the coefficient of x squared would be 2, a positive number. So that means our parabola is going to be opening up. But the vertex of this parabola will no longer be at the origin. In fact, we can find the parabola's vertex by thinking about transformations of functions. Our function is related to the function y equals 2x squared by moving it to the right by 3 and up by 4. Since y equals 2x squared has a vertex at 0, 0, if we move that whole parabola, including the vertex, right by 3 and up by 4, the vertex will end up at the point 3, 4. So our parabola will look something like this. Notice how easy it was to just read off the vertex when our quadratic function is written in this form. In fact, any quadratic function written in the form a times x minus h squared plus k has a vertex at hk by the same reasoning. We're moving the parabola with a vertex at the origin to the right by h and up by k. That's why this form of a quadratic function is called the vertex form. Notice that this parabola has no x-intercepts because it does not cross the x-axis. For our final function, we have g of x equals 5x squared plus 10x plus 3. We know the graph of this function will be a parabola pointing upwards because the coefficient of x squared is positive. To find the x-intercepts, we can set y equals 0, since the x-intercepts is where our graph crosses the x-axis, and that's where the y value is 0. So 0 equals 5x squared plus 10x plus 3. I'm going to use the quadratic formula to solve that. So x is negative 10 plus or minus the square root of 10 squared minus 4 times 5 times 3 all over 2 times 5. That simplifies to x equals negative 10 plus or minus the square root of 40 over 10, which simplifies further to x equals negative 10 over 10 plus or minus the square root of 40 over 10, which is negative 1 plus or minus 2 square root of 10 over 10, or negative 1 plus or minus square root of 10 over 5. Since the square root of 10 is just a little bit bigger than 3, this works out to approximately about negative 2/5 and negative 8/5, so somewhere around right here. So our parabola is going to look something like this. Notice that it crosses the x-axis at y equals 3. That's because when we plug in x equals 0 into here, we get y equal 3. So the y-intercept is at 3. Finally, we can find the vertex. Since this function is written in standard form, the y equals ax squared plus bx plus c form, and not in vertex form, we can't just read off the vertex like we could before. But there's a trick called the vertex formula, which says that whenever you have a quadratic function in standard form, the vertex has an x-coordinate of negative b over 2a. So in this case, that's an x-coordinate of negative 10 over 2 times 5, or negative 1, which is kind of like where I put it on the graph. To find the y-coordinate of that vertex, I can just plug in negative 1 into my equation for x, which gives me y equals 5 times negative 1 squared plus 10 times negative 1 plus 3, which is negative 2. So I think I better redraw my graph a little bit to put that vertex down at a y-coordinate of negative 2, where it's supposed to be. Let's summarize the steps we use to graph these quadratic functions. First of all, the graph of a quadratic function has the shape of a parabola. The parabola opens up if the coefficient of x squared, which we call a, is greater than 0, and down if a is less than 0. To find the x-intercepts, we set y equal to 0, or in other words, f of x equal to 0, and solve for x. To find the vertex, we can either read it off as hk if our function is in vertex form, or we can use the vertex formula and get the x-coordinate of the vertex to be negative b over 2a if our function is in standard form. To find the y-coordinate of the vertex in this case, we just plug in the x-coordinate and figure out what y is. Finally, we can always find additional points on the graph by plugging in values of x. In this video, we learned some tricks for graphing quadratic functions. In particular, we saw that the vertex can be read off as hk if our function is written in vertex form, and the x-coordinate of the vertex can be calculated as negative b over 2a if our function is in standard form. For an explanation of why this vertex formula works, please see my other video. A quadratic in standard form looks like y equals ax squared plus bx plus c, where a, b, and c are real numbers and a is not 0. A quadratic function in vertex form looks like y equals a times x minus h squared plus k, where a, h, and k are real numbers and a is not 0. When a function's in vertex form, it's easy to read off the vertex. It's just the ordered pair h, k. This video explains how to get from vertex form to standard form and vice versa. Let's start by converting this quadratic function from vertex form to standard form. That's pretty straightforward. We just have to distribute out. So if I multiply out the x minus 3 squared, I get minus 4 times x squared minus 6x plus 9 plus 1. Distributing the negative 4, I get negative 4x squared plus 24x minus 36 plus 1. So that works out to minus 4x squared plus 24x minus 35. And I have my quadratic function now in standard form. Now let's go the other direction and convert a quadratic function that's already in standard form into vertex form. That is, we want to put it in the form of g of x equals a times x minus h squared plus k, where the vertex is at hk. To do this, it's handy to use the vertex formula. The vertex formula says that the x-coordinate of the vertex is given by negative b over 2a, where a is the coefficient of x squared and b is the coefficient of x. So in this case, we get an x-coordinate of negative 8 over 2 times 2, or negative 2. To find the y-coordinate of the vertex, we just plug in the x-coordinate into our formula for g of x. So that's g of negative 2, which is 2 times negative 2 squared plus 8 times negative 2 plus 6, and that works out to be negative 2 by coincidence. So the vertex for our quadratic function has coordinates negative 2, negative 2. And if I want to write g of x in vertex form, it's going to be a times x minus negative 2 squared plus minus 2. That's because, remember, we subtract h and we add k. So that simplifies to g of x equals a times x plus 2 squared minus 2. And finally, we just need to figure out what this leading coefficient a is. But notice, if we were to distribute this out, then the coefficient of x squared would end up being a. So therefore, the coefficient of x squared here, which is a, has to be the same as the coefficient of x squared here, which we conveniently also called a. In other words, our a down here needs to be 2. So I'm going to write that as g of x equals 2 times x plus 2 squared minus 2. Lots of 2's in this problem. And that's our quadratic function in vertex form. If I want to check my answer, of course, I could just distribute out again. I'd get 2 times x squared plus 4x plus 2 minus 2. In other words, 2x squared plus 8x plus 6, which checks out to exactly what I started with. This video showed how to get from vertex form to standard form by distributing out, and how to get from standard form to vertex form by finding the vertex using the vertex formula. Suppose you have a quadratic function in the form y equals ax squared plus bx plus c, and you want to find where the vertex is when you graph it. The vertex formula says that the x-coordinate of this vertex is at negative b over 2a. This video gives a justification for where that formula comes from. Let's start with a specific example. Suppose I wanted to find the x-intercepts and the vertex for this quadratic function. To find the x-intercepts, I would set y equal to 0 and solve for x. So that's 0 equals 3x squared plus 7x minus 5. And to solve for x, I use the quadratic formula. So x is going to be negative 7 plus or minus the square root of 7 squared minus 4 times 3 times negative 5 all over 2 times 3. That simplifies to negative 7 plus or minus the square root of 109 over 6. I could also write this as negative 7/6 plus the square root of 109 over 6, or x equals negative 7/6 minus the square root of 109 over 6. Since the square root of 109 is just a little bit bigger than 10, this can be approximated by negative 7/6 plus 10/6 and negative 7/6 minus 10/6. So pretty close to, I guess, about half over here, and pretty close to about negative 3 over here. I'm just going to estimate so that I can draw a picture of the function. Since the leading coefficient 3 is positive, I know my parabola is going to be opening up, and the intercepts are somewhere around here and here. So roughly speaking, it's going to look something like this. Now the vertex is going to be somewhere in between the two x-intercepts. In fact, it's going to be, by symmetry, it'll be exactly halfway in between the two x-intercepts. Since the x-intercepts are negative 7/6 plus and minus 100 square root of 109 over 6, the number halfway in between those is going to be exactly negative 7/6, right? Because on the one hand, I have negative 7/6 plus something, and on the other hand, I have negative 7, 6 minus that same thing, so negative 7, 6 will be exactly in the middle. So my x-coordinate of my vertex will be at negative 7, 6. Notice that I got that number from the quadratic formula. More generally, if I want to find the x-intercepts for any quadratic function, I set y equal to 0 and solve for x using the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. The x-intercepts will be at these two values, but the x-coordinate of the vertex, which is exactly halfway in between the two x-intercepts, will be at negative b over 2a. That's where the vertex formula comes from. And it turns out that this formula works even when there are no x-intercepts. Even when the quadratic formula gives us no solutions, the vertex still has the x-coordinate negative b over 2a. And that's the justification of the vertex formula. This video is about polynomials and their graphs. Recall that a polynomial is a function like this one, for example, whose terms are numbers times powers of x. I'll start with some definitions. The degree of a polynomial is the largest exponent. For example, for this polynomial, the degree is 4. The leading term is the term with the largest exponent. In the same example, the leading term is 5x to the 4th. It's conventional to write the polynomial in descending order of powers of x, so that the leading term is first. But the leading term doesn't have to be the first term. If I wrote this same polynomial as y equals, say, 2 minus 17x minus 21x cubed plus 5x fourth, the leading term would still be the 5x to the 4th, even though it was last. The leading coefficient is the number in the leading term. In this example, the leading coefficient is 5. Finally, the constant term is the term with no x's in it. In our same example, the constant term is 2. Please pause the video for a moment and take a look at this next example of polynomial. Figure out what's the degree, the leading term, the leading coefficient, and the constant term. The degree is again 4, since that's the highest power we have. And the leading term is negative 7x to the 4th. The leading coefficient is negative 7, and the constant term is 18. In the graph of the polynomial shown here, the 3 marked points are called turning points, because the polynomial turns around and changes direction at those 3 points. Those same points can also be called local extreme points, or they can be called local maximum and minimum points. For this polynomial, the degree is 4, and the number of turning points is 3. Let's compare the degree and the number of turning points for these next 3 examples. For the first one, the degree is 2, and there's 1 turning point. For the second example, the degree is 3, and there's 2 turning points. And for this last example, the degree is 4, and there's 1 turning point. For this first example and the next 2, the number of turning points is exactly 1 less than the degree. So you might conjecture that this is always true. But in fact, this is not always true. In this last example, the degree is 4, but the number of turning points is 1, not 3. In fact, it turns out that while the number of turning points is not always equal to the degree minus 1, it is always less than or equal to the degree minus 1. That's a useful fact to remember when you're sketching graphs or recognizing graphs of polynomials. The end behavior of a function is how the ends of the function look as x gets bigger and bigger, heads towards infinity, or x goes through larger and larger negative numbers towards negative infinity. In this first example, the graph of the function goes down as x gets towards infinity and as x goes towards negative infinity. I can draw this with two little arrows pointing down on either side, or I can say in words that the function is falling as we head left and falling also as we head right. In this second example, the graph rises to the left and rises to the right. In the third example, the graph falls to the left but rises to the right, and in the fourth example, it rises to the left and falls to the right. If you study these examples and others, you might notice there's a relationship between the degree of the polynomial, the leading coefficients of the polynomials, and the end behavior. Specifically, these four types of end behavior are determined by whether the degree is even or odd, and by whether the leading coefficient is positive or negative. When the degree is even and the leading coefficient is positive, like in this example where the leading coefficient is 1, we have this sorts of end behavior, rising on both sides. When the degree is even and the leading coefficient is negative, like in this example, we have the end behavior that's falling on both sides. When the degree is odd and the leading coefficient is positive, that's like this example, with a degree 3 and a leading coefficient 3, then we have this sort of end behavior. And finally, when the degree is odd and the leading coefficient is negative, like in this example, we have this sort of end behavior. I like to remember this chart just by thinking of the most simple examples. Y equals x squared, y equals negative x squared, y equals x cubed, and y equals negative x cubed, because I know by heart what those four examples look like. Then I just have to remember that any polynomial with an even degree and positive leading coefficient has the same end behavior as x squared. And similarly, any polynomial with even degree and negative leading coefficient has the same end behavior as negative x squared, and similar statements for x cubed and negative x cubed. We can use facts about turning points and end behavior to say something about the equation of a polynomial just by looking at its graph. In this example, because of the end behavior, we know that the degree is odd. We know that the leading coefficient must be positive. And finally, since there are 1, 2, 3, 4 turning points, we know that the degree is greater than or equal to 5. That's because the number of turning points is less than or equal to the degree minus 1, and in this case the number of turning points we said was 4, and so solving that inequality we get the degree is bigger than or equal to 5. Putting some of that information together, we see that the degree could be 5 or 7 or 9 or any odd number greater than or equal to 5, but it couldn't be, for example, 3 or 6, because even numbers and also numbers less than 5 are right out. This video gave a lot of definitions, including the definition of degree, leading coefficients, turning points, and end behavior. We saw that knowing the degree and the leading coefficient can help you make predictions about the number of turning points and the end behavior, as well as vice versa. This video is about exponential functions and their graphs. An exponential function is a function that can be written in the form f of x equals a times b to the x, where a and b are any real numbers as long as a is not 0 and b is positive. It's important to notice that for an exponential function, the variable x is in the exponent. This is different from many other functions we've seen. For example, a quadratic function like f of x equals 3x squared has the variable in the base, so it's not an exponential function. For exponential functions, f of x equals a times b to the x, we require that a is not equal to 0 because otherwise we would have f of x equals 0 times b to the x, which just means that f of x equals 0, and this is called a constant function, not an exponential function, because f of x is always equal to 0. In an exponential function, we require that b is bigger than 0 because otherwise, for example, if b is equal to -1, say, we'd have f of x equals a times -1 to the x. Now this would make sense for a lot of values of x, but if we try to do something like f of 1/2 with our b's -1, that would be the same thing as a times the square root of -1, which is not a real number. We'd get the same problem for other values of b if the values of b were negative. And if we tried b equals 0, we'd get a kind of ridiculous thing, a times 0 to the x, which again is always 0. So that wouldn't count as an exponential either. So we can't use any negative bases and we can't use 0 bases if we want an exponential function. The number a in the expression f of x equals a times b to the x is called the initial value. And the number b is called the base. The phrase initial value comes from the fact that if we plug in x equals 0, we get a times b to the 0. Well, anything to the 0 is just 1, so this is equal to a. In other words, f of 0 equals a, so if we think of starting out when x equals 0, we get the y value of a. That's why it's called the initial value. Let's start out with this example where y equals a times b to the x, an exponential function, and we've set a equal to 1 and b equals to 2. Notice that the y-intercept, the value when x is 0, is going to be 1. If I change my a value, my initial value, the y-intercept changes. The function is stretched out. If I make the value of a go to 0 and then negative, then my initial value becomes negative and my graph flips across the x-axis. Let's go back to an a value of, say, 1 and see what happens when we change b. Right now, the b value, the base, is 2. If I increase b, my y-intercept sticks at 1, but my graph becomes steeper and steeper. If I put b back down close to 1, my graph becomes more flat. At exactly 1, my graph is just a constant. As b gets into fractional territory, 0.8, 0.7, 0.6, my graph starts to slope the other way. It's decreasing now instead of increasing. But notice that the y-intercept still hasn't changed. I can get it more and more steep as my b gets farther and farther away from 1. Of course, when b goes to negative territory, my graph doesn't make any sense. So a changes the y-intercept, and b changes the steepness of the graph so that and whether it's increasing for b values bigger than 1 and decreasing for values of b less than 1. We'll summarize all these observations on the next slide. We've seen that for an exponential function, y equals a times b to the x, the parameter, or number, a, gives the y-intercept. The parameter b tells us how the graph is increasing or decreasing. Specifically, if b is greater than 1, the graph is increasing. And if b is less than 1, the graph is decreasing. The closer b is to the number 1, the flatter the graph. So for example, if I were to graph y equals 0.25 to the x and y equals 0.4 to the x, they would both be decreasing graphs since the base for both of them is less than 1, but 0.25 is farther away from 1 and 0.4 is closer to 1, so 0.4 is going to be flatter, and 0.25 is going to be more steep. So in this picture, this red graph would correspond to 0.25 to the x, and the blue graph would correspond to 0.4 to the x. For all these exponential functions, whether the graphs are decreasing or increasing, they all have a horizontal asymptote along the x-axis. In other words, at the line y equals 0. The domain is always from negative infinity to infinity, and the range is always from 0 to infinity, because the range is always positive y values. Actually, that's true if a is greater than 0. If a is less than 0, then our graph flips over the x-axis. Our domain stays the same, but our range becomes negative infinity to 0. The most famous exponential function is f of x equals e to the x. This function is also sometimes written as f of x equals exp of x. The number e is Euler's number, and it's approximately 2.7. This function has important applications to calculus and to some compound interest problems. In this video, we looked at exponential functions, functions of the form a times b to the x, where the variable is in the exponent. We saw that they all have the same general shape, either increasing like this or decreasing like this, unless a is negative, in which case they flip over the x-axis. They all have a horizontal asymptote at y equals 0, the x-axis. In this video, we'll use exponential functions to model real-world examples. Let's suppose you're hired for a job. The starting salary is $40,000 with a guaranteed annual raise of 3% each year. How much will your salary be after 1 year, 2 years, 5 years, and in general after t years? Let me chart out the information. The left column will be the number of years since you're hired, and the right column will be your salary. When you start work, that's 0 years after you're hired, your salary will be $40,000. After 1 year, you'll have gotten a 3% raise. So your salary will be the original $40,000 plus 3% of $40,000, 0.03 times $40,000. I can think of this first number as 1 times 40,000, and I can factor out the 40,000 from both terms to get 40,000 times 1 plus 0.03. Let me rewrite this as 40,000 times 1.03. This is your original salary multiplied by a growth factor of 1.03. After 2 years, you'll get a 3% raise from your previous year's salary. Your previous year's salary was 40,000 times 1.03, but you'll add 3% of that. Again, I can think of the first number as 1 times 40,000 times 1.03, and I can factor out the common factor of 40,000 times 1.03 from both terms to get 40,000 times 1.03 times 1 plus 0.03. Let me rewrite that as 40,000 times 1.03 times 1.03, or 40,000 times 1.03 squared. We can think of this as your last year's salary multiplied by the same growth factor of 1.03. After 3 years, a similar computation will give you that your new salary is your previous year's salary times that growth factor of 1.03. That can be written as 40,000 times 1.03 cubed. And in general, if you're noticing the pattern, after t years, your salary should be 40,000 times 1.03 to the t power. In other words, your salary after t years is your original salary multiplied by the growth factor of 1.03 taken to the t power. Let me write this as a formula. S of t, where S of t is your salary, is equal to 40,000 times 1.03 to the t. This is an exponential function, that is, a function of the form a times b to the t, where your initial value, a, is 40,000, and your base, b, is 1.03. Notice that your base is the amount that your salary gets multiplied by each year. Given this formula, we can easily figure out what your salary will be after, for example, 5 years by plugging in 5 for t. I worked that out on my calculator to be $46,370.96 to the nearest cent. Exponential functions are also useful in modeling population growth. The United Nations estimated that the world population in 2010 was 6.79 billion, growing at a rate of 1.1% per year. Assuming that the growth rate stayed the same and will continue to stay the same, we'll write an equation for the population at t years after the year 2010. 1.1% written as a decimal is 0.011. So if we work out a chart as before, we see that after 0 years since 2010, we have our initial population, 6.79 billion. After 1 year, we'll take that 6.79 billion and add 1.1% of it. That is 0.011 times 6.79. This works out to 6.79 times 1 plus 0.011, or 6.79 times 1.011. Here we have our initial population of 6.79 billion and our growth factor of 1.011. That's how much the population got multiplied by in 1 year. As before, we can work out that after 2 years, our population becomes 6.79 times 1.011 squared, since it got multiplied by 1.011 twice. And after t years, it'll be 6.79 times 1.011 to the t power. So our function that models population is going to be 6.79 times 1.011 to the t. Here, t represents time in years since 2010. Just for fun, I'll plug in t equals 40. That's 40 years since 2010, so that's the year 2050, and I get 6.79 times 1.011 to the 40th power, which works out to 10.5 billion. That's the prediction based on this exponential model. The previous 2 examples were examples of exponential growth. This last example is an example of exponential decay. The drug Seroquel is metabolized and eliminated from the body at a rate of 11% per hour. If 400 milligrams are given, how much remains in the body 24 hours later? I'll chart out my information, where the left column will be time in hours since the dose was given, and the right column will be the number of milligrams of Seroquel still in the body. 0 hours after the dose is given, we have the full 400 milligrams in the body. 1 hour later, we have the 400 milligrams minus 11% of it. That's minus 0.11 times 400. If I factor out the 400 from both terms, I get 400 times 1 minus 0.11, or 400 times 0.89. The 400 represents the initial amount. The 0.89 I'll call the growth factor, even though in this case the quantity is decreasing, not growing, so really it's kind of a shrink factor. Let's see what happens after 2 hours. Now I'll have 400 times 0.89, my previous amount. It'll again get multiplied by 0.89, so that's going to be 400 times 0.89 squared. And in general, after t hours, I'll have 400 multiplied by this growth or shrinkage factor of 0.89 raised to the t power. Since each hour, the amount of Seroquel gets multiplied by 0.89, that number less than 1. I'll write my exponential decay function as f of t equals 400 times 0.89 to the t, where f of t represents the number of milligrams of Seroquel in the body, and t represents the number of hours since the dose was given. To find out how much is in the body after 24 hours, I just plug in 24 for t. This works out to about 24.4 milligrams. I hope you noticed the common form for the functions used to model all three of these examples. The functions were always in the form f of t equals a times b to the t, where a represented the initial amount and b represented the growth factor. To find the growth factor b, we started with the percent increase or decrease. We wrote it as a decimal, and then we either added it or subtracted it from 1, depending on whether the quantity was increasing or decreasing. Let me show you that as a couple examples. In the first example, we had a percent increase of 3% on the raise. As a decimal, I'll call this r, this was 0.03, and to get the growth factor, we added that to 1 to get 1.03. In the world population example, we had a 1.1% increase. We wrote this as 0.011 and added it to 1 to get 1.011. In the drug example, we had a decrease of 11%. We wrote that as a decimal, and we subtracted the 0.11 from 1 to get 0.89. In fact, you can always write the growth factor b as 1 plus the percent change written as a decimal, if you're careful to make that percent change negative when the quantity is decreasing and positive when the quantity is increasing. Since here 1 plus negative 0.11 gives us the correct growth factor of 0.89, which is less than 1. As a good check, remember that if your quantity is increasing, the base b should be bigger than 1, and if the quantity is decreasing, then b should be less than 1. Exponential functions can also be used to model bank accounts and loans with compound interest, as we'll see in another video. This video is about interpreting exponential functions. An antique car is worth $50,000 now, and its value increases by 7% each year. Let's write an equation to model its value x years from now. After 1 year, its value is the 50,000 plus 0.07 times the 50,000. That's because its value has grown by 7%, or 0.07 times 50,000. This can be written as 50,000 times 1 plus 0.07. Notice that adding 7% to the original value is the same as multiplying the original value by 1 plus 0.07, or by 1.07. After 2 years, the value will be 50,000 times 1 plus 0.07 squared, or 50,000 times 1.07 squared. That's because the previous year's value is multiplied again by 1.07. And in general, after x years, V of x, the antique car's value, will be 50,000 times 1.07 to the x. That's because the original value of 50,000 gets multiplied by 1.07 x times, one time for each year. If we dissect this equation, we see that the number 50,000 comes from the original value of the car. The 1.07, which I call the growth factor, comes from 1 plus 0.07, the 0.07 being the percent increase written as a decimal. So the form of this equation is an exponential equation, v of x equals a times b to the x, where a is the initial value and b is the growth factor. But we could also write this as a times 1 plus r to the x, where a is still the initial value, but r is the percent increase written as a decimal. This same equation will come up in the next example. Here, my Toyota Prius is worth only $3,000 now, and its value is decreasing by 5% each year. So after 1 year, its value will be 3,000 minus 0.05 times 3,000. That is 3,000 times 1 minus 0.05. I can also write that as 3,000 times 0.95. Decreasing the value by 5% is like multiplying the value by 1 minus 0.05 or by 0.95. After 2 years, the value will be multiplied by 0.95 again. So the value will be 3,000 times 0.95 squared. And after x years, the value will be 3,000 times 0.95 to the x. So my equation for the value is 3,000 times 0.95 to the x. This is again an equation of the form v of x equals a times b to the x, where here a is 3,000, the initial value, and b is 0.95. I'll still call that the growth factor, even though we're actually declining in value, not growing. Now remember where this 0.95 came from. It came from taking 1 and subtracting 0.05 because of the 5% decrease in value. So I can again write my equation in the form a times, well this time times 1 minus r to the x, where r is our 0.05, that's our percent decrease written as a decimal. Please take a moment to study this equation and the previous one. These say that when you have an exponential function, the number here is the initial value. If it's written in this form, b is your growth factor, but you can think of b as being either 1 minus r, where r is the percent decrease, or 1 plus r, where r is the percent increase. In this example, we're given a function, f of x, to model the number of bacteria in a petri dish x hours after 12 o'clock noon. We want to know what was the number of bacteria at noon and by what percent the number of bacteria is increasing every hour. We can see from the equation that the number of bacteria is increasing and not decreasing because the base of the exponential function, 1.45, is bigger than 1. Notice that our equation, f of x equals 12 times 1.45 to the x, has the form of a times b to the x, or we can think of it as a times 1 plus r to the x. Here a is 12, b is 1.45, and r is 0.45. Based on this familiar form, we can recognize that the initial amount of bacteria is going to be 12,000, since those are our units. And this value 1.45 is our growth factor, what the number of bacteria is multiplied by each hour, while R, the 0.45, is the rate of increase. In other words, a 45% increase each hour. So our answers to the questions are 12,000 and 45%. In this example, the population of salamanders is modeled by this exponential function, where x is the number of years since 2015. Notice that the number of salamanders is decreasing because the base of our exponential function, 0.78, is less than 1. So if we recognize the form of our exponential function, a times b to the x, or we can think of this as a times 1 minus r to the x, where a is our initial value and r is our percent decrease written as a decimal. Our initial value is 3,000, so that's the number of salamanders 0 years after 2015. Our growth factor b is 0.78, but if I write that as 1 minus r, I see that r has to be 1 minus 0.78, or 0.22. In other words, our population is decreasing by 22% each year. In this video, we saw that exponential functions can be written in the form f of x equals a times b to the x, where a is the initial value and b is the growth factor. We also saw that they can be written in the form a times 1 plus r to the x when the amount is increasing, and as a times 1 minus r to the x when the amount is decreasing. In this format, r is the percent increase or the percent decrease written as a decimal. So a 15% increase will be an r value of 0.15 and a growth factor b of 1.15, whereas a 12% decrease will be an r value of 0.12 and a b value of 1 minus 0.12, or 0.88. These observations help us quickly interpret exponential functions. For example, here we have an initial value of 100 and a 15% increase. And here we have an initial value of 50 and a 40% decrease. Exponential functions can be used to model compound interest for loans and bank accounts. Suppose you invest $200 in a bank account that earns 3% interest every year. If you make no deposits or withdrawals, how much money will you have accumulated after 10 years? Because 3% of the money that's in the bank is getting added each year, the money in the bank gets multiplied by 1.03 each year. So after 1 year, the amount will be 200 times 1.03. After 2 years, 200 times 1.03 squared. And after t years, 200 times 1.03 to the t power. So the function modeling the amount of money, I'll call it p of t, is given by 200 times 1.03 to the t. More generally, if you invest $, at an annual interest rate of r for t years, in the end, you'll have p of t equals a times 1 plus r to the t. Here, r needs to be written as a decimal, so 0.03 in our example for the 3% annual interest rate. Going back to our specific example, after 10 years, the amount of money is going to be P of 10, which is 200 times 1.03 to the 10, which works out to $268.78 to the nearest cent. In this problem, we've assumed that the interest accumulates once per year. But in the next few examples, we'll see what happens when the interest rate accumulates more frequently, twice a year, or every month, for example. Let's deposit $300 in an account that earns 4.5% annual interest compounded semi-annually. This means 2 times a year, or every 6 months. A 4.5% annual interest rate, compounded 2 times a year, means that we're actually getting 4.5 over 2% interest every time the interest is compounded. That is, every 6 months. That's 2.25% interest every half a year. Note that 2.25% is the same as 0.0225 as a decimal. So every time we earn interest, our money gets multiplied by 1.0225. Let me make a chart of what happens. After 0 years, which is also 0 half years, we have our original $300. After half a year, that's 1 half year, our money earns interest 1 time, so we multiply the 300 by 1.0225. After 1 year, that's 2 half years, our money earns interest 2 times, so we multiply 300 by 1.0225 squared. Continuing this way, after 1.5 years, that's 3 half years, we have 300 times 1.0225 cubed, and after 2 years, or 4 half years, we have 300 times 1.0225 to the 4th. In general, after t years, which is 2t half years, our money will grow to 300 times 1.0225 to the 2t power, because we've compounded interest 2t times. Our formula for our amount of money is P of t equals 300 times 1.0225 to the 2t, where t is the number of years. To finish the problem, after 7 years, we'll have P of $7, which is 300 times 1.0225 to the 2 times 7, or 14 power. And that works out to $409.65 to the nearest cent. In this next example, we're going to take out a loan for $1,200 at an annual interest rate of 6% compounded monthly. Although loans and bank accounts might feel different, they're mathematically the same. It's like, from the bank's point of view, they're investing money in you and getting interest on their money from you. So we can work them out with the same kind of math. 6% annual interest rate compounded monthly means you're compounding 12 times a year. So each time you compound interest, you're just going to get 6 over 12% interest. That's 0.5% interest, and as a decimal, that's 0.005. Let's chart out again what happens. Times 0, of course, you'll have the original loan amount of $1,200. After 1 year, that's 12 months, your loan has had interest added to it 12 times. So it gets multiplied by 1.005 to the 12th. After 2 years, that's 24 months, it's had interest added to it 24 times. So it gets multiplied by 1.005 to the 24th power. Similarly, after 3 years, or 36 months, your loan amount will be 1,200 times 1.005 to the 36th power. And in general, after t years, that's 12t months. So the interest will be compounded 12t times, and so we have to raise the 1.005 to the 12t power. This gives us the general formula for the money owed is P of t equals 1,200 times 1.005 to the 12t, where t is the number of years. In particular, after 3 years, we'll have to pay back a total of 1,200 times 1.005 to the 12 times 3, or 36 power, which works out to $1,436.02 to the nearest cent. These last two problems follow a general pattern. If A is the initial amount of the loan or bank account, and R is the annual interest rate, compounded n times per year, then our formula for the amount of money is going to be A times 1 plus R over n to the nt. This formula exactly matches what we did in this problem. First, we took the interest rate R, which was 6%, and divided it by the number of compounding periods each year, 12. We wrote that as a decimal and added 1 to it. That's where we got the 1.005 from. We raised this to not to the number of years, but to 12 times the number of years. That's the number of compounding periods per year times the number of years. And we multiplied all that by the initial amount of money, which was 1,200. This formula for compound interest is a good one to memorize, but it's also important to be able to reason your way through it, like we did in this chart. There's one more type of compound interest, and that's interest compounded continuously. You can think of continuous compounding as the limit of compounding more and more frequently. 10 times a year, 100 times a year, 1,000 times a year, 1,000,000 times a year. In the limit, you get continuous compounding. The formula for continuous compounding is P of t equals A times e to the RT, where P of t is the amount of money, t is the time in years, A is the initial amount of money, and R is the annual interest rate written as a decimal. So 0.025 in this problem from the 2.5% annual interest rate. E represents the famous constant, Euler's constant, which is about 2.718. So in this problem, we have P of t is 4,000 times e to the 0.025 t. And after 5 years, we'll have P of 5, which is 4,000 times e to the 0.025 times 5, which works out to $4,532.59 to the nearest cent. To summarize, if R represents the annual interest rate, written as a decimal, that is, 2% would be 0.02, and t represents the number of years, and A represents the initial amount of money, then for just simple annual interest compounded once a year, our formula is P of t is A times 1 plus R to the t. For compound interest compounded n times per year, our formula is P of t is A times 1 plus R over n to the nt. And for compound interest compounded continuously, we get P of t is A times e to the RT. In this video, we looked at 3 kinds of compound interest problems: simple annual interest, interest compounded n times per year, and continuously compounded interest. This video introduces logarithms. Logarithms are a way of writing exponents. The expression log base A of b equals c means that a to the c equals b. In other words, log base a of b is the exponent that you raise a to get b. The number a is called the base of the logarithm. It's also called the base when we write it in this exponential form. Some students find it helpful to remember this relationship. Log base a of b equals c means a to the c equals b by drawing arrows. A to the c equals b. Other students like to think of it in terms of asking a question. Log base a of b asks, what power do you raise a to in order to get b? Let's look at some examples. Log base 2 of 8 is 3 because 2 to the 3 equals 8. In general, log base 2 of y is asking you the question, what power do you have to raise 2 to get y? So for example, log base 2 of 16 is 4 because it's asking you the question, 2 to what power equals 16? And the answer is 4. Please pause the video and try some of these other examples. Log base 2 of 2 is asking, what power do you raise 2 to get 2? And the answer is 1. 2 to the 1 equals 2. Log base 2 of 1/2 is asking 2 to what power gives you 1/2? Well, to get 1/2, you need to raise 2 to a negative power. So that would be 2 to the negative 1. So the answer is negative 1. Log base 2 of 1/8 means what power do we raise 2 to in order to get 1/8? Again, since 1/8 is 1 over 2 cubed, we have to raise 2 to the negative 3 power to get 1 over 2 cubed. So our exponent is negative 3, and that's our answer to our log expression. Finally, log base 2 of 1 is asking 2 to what power equals 1? Well, anything raised to the 0 power gives us 1, so this log expression evaluates to 0. Notice that we can get positive, negative, and 0 answers for our logarithm expressions. Please pause the video and figure out what these logs evaluate to. To work out log base 10 of 1,000,000, notice that 1,000,000 is 10 to the 6th power. Now we're asking the question, what power do we raise 10 to get 1,000,000? So that is, what power do we raise 10 to get 10 to the 6th? Well, of course, the answer is going to be 6. Similarly, since 0.001 is 10 to the minus 3, this log expression is the same thing as asking what's log base 10 of 10 to the minus 3. Well, what power do you have to raise 10 to get 10 to the minus 3? Of course, the answer is negative 3. Log base 10 of 0 is asking what power do we raise 10 to get 0? Well, if you think about it, there's no way to raise 10 to an exponent and get 0. Raising 10 to a positive exponent gets us really big positive numbers. Raising 10 to a negative exponent is like 1 over 10 to a power. So that's giving us tiny fractions, but they're still positive numbers. We're never going to get 0. Even if we raise 10 to the 0 power, we'll just get 1. So there's no way to get 0, and the log base 10 of 0 does not exist. If you try it on your calculator using the log base 10 button, you'll get an error message. Same thing happens when we do log base 10 of negative 100. We're asking 10 to what power equals negative 100, and there's no exponent that will work. And more generally, it's possible to take the log of numbers that are greater than 0, but not for numbers that are less than or equal to 0. In other words, the domain of the function log base a of x, no matter what base you're using for a, the domain is going to be all positive numbers. A few notes on notation. When you see ln of x, that's called natural log, and it means the log base e of x, where e is that famous number that's about 2.718. When you see log of x with no base at all, by convention, that means log base 10 of x, and it's called the common log. Most scientific calculators have buttons for natural log and for common log. Let's practice rewriting expressions with logs in them. Log base 3 of 1/9 is -2 can be rewritten as the expression 3 to the -2 equals 1/9. Log of 13 is shorthand for log base 10 of 13, so that can be rewritten as 10 to the 1.11394 equals 13. Finally, in this last expression, ln means natural log, or log base e. So I can rewrite this equation as log base e of 1 over e equals -1. Well, that means the same thing as e to the -1 equals 1 over e, which is true. Now let's go the opposite direction. We'll start with exponential equations and rewrite them as logs. Remember that log base a of b equals c means the same thing as a to the c equals b. The base stays the same in both expressions. So for this example, the base of 3 in the exponential equation is going to be the same as the base in our log. Now I just have to figure out what's in the argument of the log and what goes on the other side of the equal sign. Remember that the answer to a log is an exponent. So the thing that goes in this box should be my exponent for my exponential equation. In other words, u. And I'll put the 9.78 as the argument of my log. This works because log base 3 of 9.78 equals u means the same thing as 3 to the u equals 9.78, which is just what we started with. In the second example, the base of my exponential equation is e. So the base of my log is going to be e. The answer to my log is an exponent, in this case the exponent 3x plus 7. And the other expression, the 4 minus y, becomes my argument of my log. Let me check. Log base e of 4 minus y equals 3x plus 7 means e to the 3x plus 7 equals 4 minus y, which is just what I started with. I can also rewrite log base e as natural log. This video introduced the idea of logs and the fact that log base a of b equals c means the same thing as a to the c equals b. So log base a of b is asking the question, what power or exponent do you raise a to in order to get b? In this video, we'll work out the graphs of some log functions and also talk about their domains. For this first example, let's graph a log function by hand by plotting some points. The function we're working with is y equals log base 2 of x. I'll make a chart of x and y values. Since we're working this out by hand, I want to pick x values for which it's easy to compute log base 2 of x. So I'll start out with the x value of 1 because log base 2 of 1 is 0. Log base anything of 1 is 0. 2 is another x value that's easy to compute. Log base 2 of 2, that's asking what power do I raise 2 to get 2? Well, and the answer is 1. Other powers of 2 are easy to work with. So for example, log base 2 of 4, that's saying what power do I raise 2 to get 4? So the answer is 2. Similarly, log base 2 of 8 is 3, and log base 2 of 16 is 4. Let me also work with some fractional values for x. If x is 1/2, then log base 2 of 1/2, that's saying what power do I raise 2 to get 1/2? Well, that needs a power of -1. It's also easy to compute by hand the log base 2 of 1/4 and 1/8. Log base 2 of 1/4 is negative 2, since 2 to the negative 2 is 1/4, and similarly log base 2 of 1/8 is negative 3. I'll put some tick marks on my x and y axes. Please pause the video and take a moment to plot these points. Let's see, I have the point 1, 0, that's here, 2, 1, that's here, 4, 2, that is here, and then 8, 3, which is here. And the fractional x values, 1/2 goes with negative 1, and 1/4 with negative 2, 1/8 with negative 3. And if I connect the dots, I get a graph that looks something like this. If I had smaller and smaller fractions, I would keep getting more and more negative answers when I took log base 2 of them. So my graph is getting more and more negative. My y values are getting more and more negative as x is getting close to 0. Now, I didn't draw any parts of the graph over here with negative x values, and I didn't put any negative x values in my chart. That omission is no accident, because if you try to take the log base 2 or base anything of a negative number, like say negative 4 or something, there's no answer. This doesn't exist because there's no power that you can raise 2 to get a negative number. So there are no points on the graph for negative x values, and similarly there are no points on the graph where x is 0, because you can't take log base 2 of 0. There's no power you can raise 2 to get 0. I want to observe some key features of this graph. First of all, the domain is x values greater than 0. In interval notation, I can write that as a round bracket, because I don't want to include 0, to infinity. The range is going to be the y values. Well, they go all the way down into the far reach of the negative numbers, and the graph gradually increases, y values getting bigger and bigger, so the range is actually all real numbers, or in interval notation, negative infinity to infinity. Finally, I want to point out that this graph has a vertical asymptote at the y-axis, that is, at the line x equals 0. I'll draw that on my graph with a dotted line. A vertical asymptote is a line that our function's graph gets closer and closer to. So this is the graph of y equals log base 2 of x. But if I wanted to graph, say, y equals log base 10 of x, it would look very similar. It would still have a domain of x values greater than 0, a range of all real numbers, and a vertical asymptote at the y-axis. It would still go through the point 1, 0, but it would go through the point 10, 1 instead, because log base 10 of 10 is 1. It would look pretty much the same, just a lot flatter over here. But even though it doesn't look like it with the way I've drawn it, it still gradually goes up to and towards infinity. In fact, the graph of y equals log base any a of x for a bigger than 1 looks pretty much the same and has these same 3 properties. Now that we know what the basic log graph looks like, we can plot at least rough graphs of other log functions without plotting points. Here we have the graph of natural log of x plus 5. And again, I'm just going to draw a rough graph. If I did want to do a more accurate graph, I probably would want to plot some points. But I know that roughly a log graph, if it was just like y equals ln of x, that would look something like this, and it would go through the point 1, 0, with a vertical asymptote along the y-axis. Now if I want to graph ln of x plus 5, that just shifts our graph up by 5 units. It'll still have the same vertical asymptote, since a vertical line shifted up by 5 units is still a vertical line, but instead of going through 1, 0, it'll go through the point 1, 5. So I'll draw a rough sketch here. Let's compare our starting function y equals ln x, and the transformed version, y equals ln x plus 5, in terms of the domain, the range, and the vertical asymptote. Our original function, y equals ln x, had a domain of 0 to infinity. Since adding 5 on the outside affects the y values, and the domain is the x values, this transformation doesn't change the domain. So the domain is still from 0 to infinity. Now the range of our original y equals ln x was from negative infinity to infinity. Shifting up by 5 does affect the y values, and the range is talking about the y values, but since the original range was all real numbers, if you add 5 to a set of all real numbers, you still get the set of all real numbers. So in this case, the range doesn't change either. And finally, we already saw that the original vertical asymptote of the y-axis, x equals 0, when we shift that up by 5 units, it's still the vertical line, x equals 0. In this next example, we're starting with a log base 10 function. And since the plus 2 is on the inside, that means we shift that graph left by 2. So I'll draw our basic log function. Here's our basic log function, so I'll think of that as y equals log of x, going through the point 1, 0. Here's its vertical asymptote. Now I need to shift everything left by 2. So my vertical asymptote shifts left, and now it's at the line x equals negative 2 instead of at x equals 0. And my graph, well, let's see, my point 1, 0 gets shifted to, let's see, negative 1, 0, since I'm subtracting 2 from the x's. And here's a rough sketch of the resulting graph. Let's compare the features of the two graphs drawn here. We're talking about domains. The original had a domain of from 0 to infinity, but now I've shifted that left, so I've subtracted 2 from all my x values, and here's my new domain, which I can also verify just by looking at the picture. My range was originally from negative infinity to infinity. Well, shifting left only affects the x value, so it doesn't even affect the range, so my range is still negative infinity to infinity. My vertical asymptote was originally at x equals 0, and since I subtract 2 from all my x values, that shifts it to x equals negative 2. In this last problem, I'm not going to worry about drawing this graph. I'll just use algebra to compute its domain. So let's think about what's the issue when you're taking the logs of things. Well, you can't take the log of a negative number or 0, so whatever's inside the argument of a log function, whatever's being fed into log, had better be greater than 0. So I'll write that down. We need 2 minus 3x to be greater than 0. Now it's a matter of solving an inequality. 2 has got to be greater than 3x, so 2/3 is greater than x. In other words, x has to be less than 2/3, so our domain is all the x values from negative infinity to 2/3, not including 2/3. It's a good idea to memorize the basic shape of the graph of a log function. It looks something like this, goes through the point 1, 0, and has a vertical asymptote on the y-axis. Also, if you remember that you can't take the log of a negative number or 0, then that helps you quickly compute domains for log functions. Whatever's inside the log function, you set that greater than 0 and solve. This video is about combining logs and exponents. Please pause the video and take a moment to use your calculator to evaluate the following 4 expressions. Remember that log base 10 on your calculator is the log button, while log base E on your calculator is the natural log button. You should find that the log base 10 of 10 cubed is 3. The log base E of e to the 4.2 is 4.2. 10 to the log base 10 of 1,000 is 1,000, and e to the log base e of 9.6 is 9.6. In each case, the log and the exponential function with the same base undo each other, and we're left with the exponent. In fact, it's true that for any base a, the log base a of a to the x is equal to x. The same sort of cancellation happens if we do the exponential function and the log function with the same base in the opposite order. For example, when we take 10 to the power of log base 10 of 1,000, the 10 to the power and the log base 10 undo each other, and we're left with the 1,000. This happens for any base a. A to the log base a of x is equal to x. We can describe this by saying that an exponential function and a log function with the same base undo each other. If you're familiar with the language of inverse functions, the exponential function and the log function are inverses. Let's see why these rules hold. For the first log rule, log base a of a to the x is asking the question, what power do we raise a to in order to get a to the x? In other words, a to what power is a to the x? Well, the answer is clearly x, and that's why log base a of a to the x equals x. For the second log rule, notice that the log base a of x means the power we raise a to get x. But this expression is saying that we're supposed to raise a to that power. If we raise a to the power we need to raise a to get x, then we'll certainly get x. Now let's use these two rules in some examples. If we want to find 3 to the log base 3 of 1.4, 3 to the power and log base 3 undo each other, so we're left with 1.4. If we want to find ln of e to the x, remember that ln means log base e. So we're taking log base e of e to the x. Well, those functions undo each other, and we're left with x. If we want to take 10 to the log of 3z, remember that log without a base written implies that the base is 10. So really we want to take 10 to the log base 10 of 3z. Well, 10 to a power and log base 10 undo each other, so we're left with the 3z. Finally, does this last statement hold? Is ln of 10 to the x equal to x? Well, ln means log base e. So we're taking log base e of 10 to the x. Notice that the base of the log and the base of the exponential function are not the same. So they don't undo each other. And in fact, log base e of 10 to the x is not usually equal to x. We can check with one example. Say if x equals 1, then log base e of 10 to the 1, that's log base e of 10, and we can check on the calculator, that's equal to 2.3 and some more decimals, which is not the same thing as 1. So this statement is false. It does not hold. We need the bases to be the same for logs and exponents to undo each other. In this video, we saw that logs and exponents with the same base undo each other. Specifically, log base a of a to the x is equal to x, and a to the log base a of x is also equal to x for any values of x and any base a. This video is about rules or properties of logs. The log rules are closely related to the exponent rules, so let's start by reviewing some of the exponent rules. To keep things simple, we'll write everything down with a base of 2, even though the exponent rules hold for any base. We know that if we raise 2 to the 0 power, we get 1. We have a product rule for exponents, which says that 2 to the m times 2 to the n is equal to 2 to the m plus n. In other words, if we multiply two numbers, then we add the exponents. We also have a quotient rule that says that 2 to the m divided by 2 to the n is equal to 2 to the m minus n. In words, this says that if we divide two numbers, then we subtract the exponents. Finally, we have a power rule that says if we take a power to a power, then we multiply the exponents. Each of these exponent rules can be rewritten as a log rule. The first rule, 2 to the 0 equals 1, can be rewritten in terms of logs as log base 2 of 1 equals 0. That's because log base 2 of 1 equals 0 means 2 to the 0 equals 1. The second rule, the product rule, can be rewritten in terms of logs by saying log of x times y equals log of x plus log of y. I'll make these base 2 to agree with my base that I'm using for my exponent rules. In words, this says the log of the product is the sum of the logs. Since logs really represent exponents, this is saying that when you multiply two numbers together, you add their exponents, which is just what we said for the exponent version. The quotient rule for exponents can be rewritten in terms of logs by saying the log of x divided by y is equal to the log of x minus the log of y. In words, we can say that the log of the quotient is equal to the difference of the logs. Since logs are really exponents, another way of saying the same thing is that when you divide two numbers, you subtract their exponents. That's how we described the exponent rule above. Finally, the power rule for exponents can be rewritten in terms of logs by saying the log of x to the n is equal to n times log of x. Sometimes people describe this rule by saying when you take the log of an expression with an exponent, you can bring down the exponent and multiply. If we think of x as being some power of 2, this is really saying when we take a power to a power, we multiply their exponents. That's exactly how we describe the power rule above. It doesn't really matter if you multiply this exponent on the left side or on the right side, but it's more traditional to multiply it on the left side. I've given these rules with the base of 2, but they actually work for any base. To help you remember them, please take a moment to write out the log rules using a base of a. You should get the following chart. Let's use the log rules to rewrite the following expressions as a sum or difference of logs. In the first expression, we have a log base 10 of a quotient, so we can rewrite the log of the quotient as the difference of the logs. Now we still have the log of a product. I can rewrite the log of a product as the sum of the logs. So that is log of y plus log of z. When I put things together, I have to be careful because here I'm subtracting the entire log expression. So I need to subtract both terms of this sum. I'll make sure I do that by putting them in parentheses. Now I can simplify a little bit by distributing the negative sign. And here's my final answer. In my next expression, I have the log of a product, so I can rewrite that as the sum of two logs. I can also use my power rule to bring down the exponent t and multiply it in the front. That gives me the final expression, log of 5 plus t times log of 2. One common mistake on this problem is to rewrite this expression as t times log of 5 times 2. In fact, those two expressions are not equal. Because the t only applies to the 2, not to the whole 5 times 2, we can't just bring it down in front using the power rule. After all, the power rule only applies to a single expression raised to an exponent, and not to a product like this. In these next examples, we're going to go the other direction. Here we're given sums and differences of logs, and we want to wrap them up into a single log expression. If I look at the first two pieces, that's a difference of logs. So I know I can rewrite it as the log of a quotient. Now I have the sum of two logs, so I can rewrite that as the log of a product. I'll clean that up a little bit and rewrite it as log base 5 of a times c over b. In my second example, I can rewrite the sum of my logs as the log of a product. Now I would like to rewrite this difference of logs as the log of a quotient, but I can't do it yet because of that factor of 2 multiplied in front. But I can use the power rule backwards to put that 2 back up in the exponent. So I'll do that first. So I will copy down the ln of x plus 1 times x minus 1 and rewrite this second term as ln of x squared minus 1 squared. Now I have a straightforward difference of 2 logs, which I can rewrite as the log of a quotient. I can actually simplify this some more. Since x plus 1 times x minus 1 is the same thing as x squared minus 1, I can cancel factors to get ln of 1 over x squared minus 1. In this video, we saw 4 rules for logs that are related to exponent rules. First, we saw that the log with any base of 1 is equal to 0. Second, we saw the product rule, the log of a product, is equal to the sum of the logs. We saw the quotient rule, the log of a quotient is the difference of the logs. And we saw the power rule. When you take a log of an expression with an exponent in it, you can bring down the exponent and multiply it. It's worth noticing that there's no log rule that helps you split up the log of a sum. In particular, the log of a sum is not equal to the sum of the logs. If you think about logs and exponent rules going together, this kind of makes sense, because there's also no rule for rewriting the sum of 2 exponential expressions. Log rules will be super handy as we start to solve equations using logs. Anytime you have an equation, like this one, that has variables in the exponent, logs are the tool of choice for getting those variables down where you can solve for them. In this video, I'll do a few examples of solving equations with variables in the exponents. For our first example, let's solve for x, the equation 5 times 2 to the x plus 1 equals 17. As my first step, I'm going to isolate the difficult spot, the part that has the variables in the exponent. In this example, I can do that by dividing both sides by 5. That gives me 2 to the x plus 1 equals 17 over 5. Next, I'm going to take the log of both sides. It's possible to take the log with any base, but I prefer to take the log base 10 or the log base e for the simple reason that my calculator has buttons for those logs. So in this example, I'll just take the log base 10. So I can omit the base because base 10 is implied here. And that gives me this expression. As my next step, I'm going to use log rules to bring down my exponent and multiply it on the front. It's important to use parentheses here because the entire x plus 1 needs to get multiplied by log 2. So that was my third step using the log rules. Now all my variables are down from the exponent where I can work with them, but I still need to solve for x. Right now x is trapped in the parentheses, so I'm going to free it from the parentheses by distributing. So I get x log 2 plus log 2 equals log of 17/5. Now I will try to isolate x by moving all my terms with x's in them to one side and all my terms without x's in them to the other side. Finally, I factor out my x, well, it's already kind of factored out, and I divide to isolate it. So I'll write out what I did so far. I distributed, I moved all the x terms on one side and the terms without x's on the other side, and then I isolated the x by factoring out and dividing. We have an exact solution for x. This is correct, but maybe not so useful if you want a decimal answer. At this point, you can type in everything into your calculator using parentheses liberally, to get a decimal answer of about 0.765. It's always a good idea to check your work by typing in this decimal answer and seeing if the equation checks out. This next example is trickier because there are variables in the exponent in two places with two different bases. Our first step is normally to clean things up and simplify by isolating the tricky stuff. But in this example, there's nothing really to clean up or simplify or no way to isolate anything more than it already is. So we'll go ahead to the next step and take the log of both sides. Again, I'll go ahead and use log base 10, but we could use log base e instead. Next, we can use log rules to bring down the exponents. This gives me 2x minus 3 in parentheses, log 2 equals x minus 2 log 5. Now I'm going to distribute things out to free the x's from the parentheses. That gives me 2x log 2 minus 3 log 2 equals x log 5 minus 2 log 5. Now I need to group the x terms on one side and the other terms that don't involve x on the other side. So I'll keep the 2x log 2 on the left, put the minus log x log 5 on the left, and that gives me the minus 2 log 5 that stays on the right and a plus 3 log 2 on the right. Finally, I need to isolate x by factoring and dividing. By factoring, I just mean I factor out the x from all the terms on the left. So that gives me x times the quantity 2 log 2 minus log 5, and that equals this mess on the right. Now I can divide the right side by the quantity on the left side. When you type this into your calculator, I encourage you to type the whole thing in rather than type bits and pieces in, because if you round off, you'll get a less accurate answer than if you type the whole thing in at once. In this example, when I type it in, I get a final answer of about 5.106. In this equation, we have the variable t in the exponent in two places. The letter e is not a variable. It represents the number e, whose decimal approximation is about 2.7. Because there's already an e in the expression, it's going to be handy to use natural log in this problem instead of log base 10. But before we take the log of both sides, let's clean things up by isolating the tricky parts. We could at least divide both sides by 5, and that will give us e to the negative 0.05t is equal to 3/5 e to 0.2t. One way to proceed would now be to clean things up further by dividing both sides by e to the 0.2t, but I'm going to take a different approach and go ahead and take the natural log of both sides. So that gives me ln of e to the minus 0.05t is equal to ln of 3/5 e to the 0.2t. Now on the left side, I can immediately use my log rule to bring down my exponent and get minus 0.05t ln e. But on the right side, I can't bring down the exponent yet because this e to the 0.2t is multiplied by 3/5. So before I can bring down the exponent, I need to split up this product using the product rule. So I can rewrite this as ln of 3/5 plus ln e to the 0.2t, and now I can bring down the exponent. So that third step was using log rules to ultimately bring down my exponents. Now, ln of e is a really nice expression. ln of e means log base e of e, so that's asking what power do I raise e to in order to get e? And the answer is 1. So anytime I have ln of e, I can just replace that with 1. That's why using natural log is a little bit handier here than using log base 10. You can make that simplification. Next, I'm ready to solve for t. So I don't need to distribute here, but I do need to bring my t terms to one side and my t terms without t to the other side. So let's see, I'll put my t terms on the left and my terms without t on the right. And finally, I'm going to isolate t by factoring and dividing. So by factoring, I mean I factor out my t. And now I can divide. Using my calculator, I can get a decimal answer of 2.0433. This video gave some examples of solving equations with variables in the exponent. And the key idea was to take the log of both sides and use the log properties to bring the exponents down. This video gives some examples of equations with logs in them, like this one. In order to solve equations like this one, we have to free the variable from the log, and we'll do that using exponential functions. My first step in solving pretty much any kind of equation is to simplify it and isolate the tricky part. In this case, the tricky part is the part with the log in it. So I can isolate it by first adding 3 to both sides. That gives me 2 ln 2x plus 5 equals 4, and then I can divide both sides by 2. Now that I've isolated the tricky part, I still need to solve for x, but x is trapped inside the log function. To free it, I need to somehow undo the log function. Well, log functions and exponential functions undo each other. And since this is a log base e, I need to use the exponential function base e also. So I'm going to take e to the power of both sides. In other words, I'll take e to the ln 2x plus 5, and that's going to equal e to the power of 2. Now e to the ln of anything, I'll just write a for anything. That means e to the log base e of a. The e to the power and log base e undo each other, so we just get a. I'm going to use that principle over here. E to the ln of 2x plus 5, the e and the log base e undo each other, and we're left with 2x plus 5 on the left side. So 2x plus 5 is equal to e squared, and from there it's easy to finish the problem and solve for x by subtracting 5 from both sides and then dividing by 2. So I'll just write the third step here is I'll just say finish solving for x. There's one last step we need to do when solving equations with logs in them, and that's to check our answers because we may get extraneous solutions. An extraneous solution is a solution that comes out of the solving process but doesn't actually satisfy the original equation. And those can happen for equations with logs in them because we might get a solution that makes the argument of the log negative or 0, and we can't take the log of a negative number or 0. So let's check and plug in the solution of e squared minus 5 over 2. We'll plug that in for x in our original equation and see if that works. So let's see, the 2's cancel here. So I get 2 ln e squared minus 5 plus 5 minus 3. I want that to equal 1. Well, now my 5's cancel. And so I have 2 ln e squared minus 3 that I want to equal 1. Well, I think this is going to work out because, let's see, ln is log base e. And log base e of e squared, that's asking the question, what power do I raise e to get e squared? Well, I have to raise it to the power of 2 to get e squared. So this becomes 2 times 2 minus 3. And does that equal 1? 4 minus 3 does equal 1. So that all checks out. And we didn't have any problem with taking the log of a negative number or 0. We didn't get any extraneous solutions, so this is our solution. This second equation is a little bit trickier because there's a log in 2 places. Now notice that this is a log where there's no base written, so a base 10 is implied. So I'm already thinking, in order to undo a log base 10, I'm going to want to take a 10 to the power of both sides. Of course, it's still a good idea to isolate the tricky part, but there's nothing really to isolate here. So I'm going to say can't do it here. So we'll just jump right to straight step 2 and take 10 to the power of both sides. Okay, so that's going to give me 10 to the whole thing log x plus 3 plus log x. That whole thing is in the exponent equals 10 to the 1 power. Well, I know what to do with the right side. 10 to the 1 is just 10. But what do I do with the 10 to these two things added up? Well, remembering my exponent rules, I know that when you add up the exponent, that's what happens when you multiply two things. So this is the same thing as 10 to the log x plus 3 times 10 to the log x, right? Because when you multiply two things, you add the exponents. So these are the same. Okay, now we're in business because 10 to the log base 10, those undo each other. And so this whole expression here simplifies to x plus 3. Similarly, 10 to the log base 10 of x is just x. So I'm multiplying x plus 3 by x, that's equal to 10. Now I have an equation I can deal with. It's a quadratic, so I'm going to first multiply out to make it look more like a quadratic, get everything to one side, so it's equal to 0, and now I can either factor or use the quadratic formula. I think this one factors. It looks like x plus 5 times x minus 2. So I'm going to get x is negative 5 or x is 2. So that was all the third step to finish solving for x. Finally, we need to check our solutions to make sure we haven't gotten some extraneous ones. So let's see, if x equals negative 5, if I plug that into my original equation, that says I'm checking that log of negative 5 plus 3 plus log of negative 5, checking that's equal to 1. Well, this is giving me a queasy feeling, and I hope it's giving you a queasy feeling too, because log of negative 2 does not exist, right? You can't take the log of a negative number. Same thing with log of negative 5. So x equals negative 5 is an extraneous solution. It doesn't actually solve our original equation. Let's check the other solution, x equals 2. So now we're checking to see if log of 2 plus 3 plus log of 2 is equal to 1. Since there's no problem with taking logs of negative numbers or 0 here, this should work out fine. And just to finish checking, we can see, let's see, this is log of 5 plus log of 2. We want that to equal 1. But using my log rules, the sum of two logs is the log of the product. So log of 5 times 2, we want that to equal 1. And that's just log base 10 of 10. And that definitely equals 1 because log base 10 of 10 says what power do I raise 10 to get 10, and that power is 1. So the second solution, x equals 2, does check out, and that's our final answer. Before I leave this problem, I do want to mention that some people have an alternative approach. Some people like to start with the original equation and then use log rules to combine everything into one log expression. So since we have the sum of two logs, we know that's the same as the log of a product, right? So we can rewrite the left side as log of x plus 3 times x. That equals 1. Then we do the same trick of taking 10 to the power of both sides. And as before, the 10 to the power and the log base 10 undo each other, and we get x plus 3 times x equals 10, just like we did before. In the first solution, we ended up using exponent rules to rewrite things. In the second alternative method, we used log rules to rewrite things. So the methods are really pretty similar, pretty equivalent, and they certainly will get us to the same answer. So we've seen a couple examples of equations with logs in them and how to solve them. And the key step is to use exponential functions to undo the log. In other words, take e to the power of both sides to undo natural log, and take 10 to the power of both sides to undo log base 10. In this video, we'll use exponential equations in some real-life applications, like population growth and radioactive decay. I'll also introduce the ideas of half-life and doubling time. In this first example, let's suppose we invest $1,600 in a bank account that earns 6.5% annual interest, compounded once a year. How many years will it take until the account has $2,000 in it, if we don't make any further deposits or withdrawals? Since our money is earning 6.5% interest each year, that means that every year the money gets multiplied by 1.065. So after t years, my 1,600 gets multiplied by 1.065 to the t power. I'll write this in function notation as f of t equals 1,600 times 1.065 to the t, where f of t is the amount of money after t years. Now we're trying to figure out how long it will take to get $2,000. $2,000 is an amount of money, so that's an amount for f of t. And we're trying to solve for t, the amount of time. So let me write out my equation and make a note that I'm solving for t. Now to solve for t, I want to first isolate the tricky part. So the tricky part is the part with the exponential in it. So I'm going to divide both sides by 1,600. So that gives me 2,000 over 1,600 equals 1.065 to the t. I can simplify this a little bit further as 5/4. Now that I've isolated the tricky part, my next step is going to be to take the log of both sides. That's because I have a variable in the exponent, and I know that if I take the log of both sides, I can use log rules to bring that exponent down where I can solve for it. So I think I'll use log base e this time. So I have ln 5/4 equals ln of 1.065 to the t. Now by the power rule for logs, on the right side, I can bring that exponent t down and multiply it in the front. Now it's easy to isolate t just by dividing both sides by ln of 1.065. Typing that into my calculator, I get that t is approximately 3.54 years. In the next example, we have a population of bacteria that initially contains 1.5 million bacteria, and it's growing by 12% per day. We want to find the doubling time. The doubling time means the amount of time it takes for a quantity to double in size. For example, the amount of time it takes to get from the initial 1.5 million bacteria to 3 million bacteria would be the doubling time. Let's start by writing an equation for the amount of bacteria. So if, say, p of t represents the number of bacteria in millions, then my equation, and t represents time in days, then p of t is going to be given by the initial amount of bacteria times the growth factor 1.12 to the t. That's because my population of bacteria is growing by 12% per day. That means the number of bacteria gets multiplied by 1.12. Since we're looking for the doubling time, we're looking for the t value when p of d will be twice as big. So I can set p of t to be 3 and solve for t. As before, I'll start by isolating the tricky part, taking the log, bringing the t down, and finally solving for t. Let's see, 3 over 1.5 is 2, so I can write this as ln 2 over ln 1.12. Using my calculator, that's about 6.12 days. It's an interesting fact that doubling time only depends on the growth rate, that 12% growth, not the initial population. In fact, I could have figured out the doubling time without even knowing how many bacteria were in my initial population. Let me show you how that would work. If I didn't know how many I started with, I could still write P of t equals A times 1.12 to the t, where A is our initial population that I don't know what it is. Then if I want to figure out how long it takes for my population to double, well, if I start with A and double that, I get 2A. So I'll set my population equal to 2A, and I'll solve for t. Notice that my a's cancel, and so when I take the log of both sides and bring the t down and solve for t, I get the exact same thing as before. It didn't matter what the initial population was. I didn't even have to know what it was. In this next example, we're told the initial population and we're told the doubling time. We're not told by what percent the population increases each minute or by what number we're supposed to multiply the population by each minute. So we're going to have to solve for that. I do know that I want to use an equation of the form y equals a times b to the t, where t is going to be the number of minutes and y is going to be the number of bacteria. And I know that my initial amount A is 350, so I can really write y equals 350 times b to the t. Now the doubling time tells me that when 15 minutes have elapsed, my population is going to be twice as big, or 700. Plugging that into my equation, I have 700 equals 350 times b to the 15. Now I need to solve for b. Let me clean this up a little bit by dividing both sides by 350. That gives me 700 over 350 equals b to the 15th. In other words, 2 equals b to the 15th. To solve for b, I don't have to actually use logs here because my variable is in the base, not in the exponent, so I don't need to bring that exponent down. Instead, the easiest way to solve this is just by taking the 15th root of both sides, or equivalently, the 1/15th power. That's because if I take b to the 15th to the 1/15th, I multiply my exponents. That gives me b to the 1 is equal to 2 to the 1/15th. In other words, b is 2 to the 1/15th, which as a decimal is approximately 1.047294. I like to use a lot of decimals if I'm doing a decimal approximation in these kind of problems to increase accuracy, but of course the most accurate thing is just to leave b as it is, and I'll do that and rewrite my equation as y equals 350 times 2 to the 1/15th to the t. Now I'd like to work this problem one more time, and this time I'm going to use the form of the equation y equals a times e to the RT. This is called a continuous growth model. It looks different, but it's actually an equivalent form to this growth model over here. And I'll say more about why these two forms are equivalent at the end. I can use the same general ideas to solve in this form. So I know that my initial amount is 350. I now know, again, that when t is 15, my y is 700. So I plug in 700 here, 350 e to the r times 15, and I solve for r. Again, I'm going to simplify things by dividing both sides by 350. That gives me 2 equals e to the r times 15. This time, my variable does end up being in the exponent, so I do want to take the log of both sides. I'm going to use natural log because I already have an e in my problem, so natural log and e are kind of more harmonious together than common log with base 10 and e. So I take the log of both sides. Now I can pull the exponent down, so that's r times 15 times ln of e. Well, ln of e is just 1. Right? Because ln of e is asking what power do I raise e to get e. That's just 1. And so I get 15r equals ln2, so r is equal to ln2 divided by 15. Let me plug that back in to my original equation. That's e to the ln2 over 15 times t. Now I claimed that these two equations were actually the same thing, just looking different. And the way to see that is if I start with this equation and I rewrite as e to the ln2 over 15 like that to the t, well, I claim that this quantity right here is the same thing as my 2 to the 1/15th. And in fact, one way to see that is e to the ln2, I'll write it to the 1/15th, right? That's the same because every time I take a power to a power, I multiply exponents. But what's e to the ln2? E and ln undo each other. So that's just 350 times 2 to the 1/15th to the t. Ta-da! The equations are really the same. And these, you'll always be able to find two different versions of an exponential equation. Sort of the standard one, a times b to the t, or the continuous growth one, a times e to the rt. In this last example, we're going to work with half-life. Half-life is pretty much like doubling time. It just means the amount of time that it takes for a quantity to decrease to half as much as originally started with. We're told that the half-life of radioactive carbon-14 is 5,750 years. So that means it takes that long for a quantity of radioactive carbon-14s to decay so that you just have half as much left, and the rest is non-radioactive form. So we're told a sample of bone that originally contained 200 grams of radioactive carbon-14 now contains only 40 grams. We're supposed to find out how old the sample is. This is called carbon dating. Let's use the continuous growth model this time. So our final amount, so this is our amount of radioactive C14, is going to be the initial amount times e to the rt. We could have used the other model too. We could have used f of t equals a times b to the t, but I just want to use the continuous model for practice. So we know that our half-life is 5,750. So what that means is when t is 5,750, our amount is going to be 1/2 of what we started with. Let me see if I can plug that into my equation and use that to figure out what r is. R is called the continuous growth rate. So I plug in 1/2 a for the final amount. A is still the initial amount, e to the r, and I have 5,750. I can cancel my a's, and now I want to solve for r. R is in my exponent, so I do need to take the log of both sides to solve for it. I'm going to use log base e since I already have an e in my problem. Log base e is more compatible with e than log base 10 is. Okay, now on the left side I still have log of 1/2, a natural log of 1/2. On the right side, ln and e to a power, those undo each other. So I'm left with r times 5,750. Now I can solve for r. It's ln 1/2 over 5,750. I could work that as a decimal, but it's actually more accurate just to keep it in exact form. So now I can rewrite my equation. I have f of t equals a times e to the ln 1/2 over 5,750 t. Now I can use that to figure out my problem. In my problem, the bone originally contained 200 grams. That's my A. I want to figure out when it's going to contain only 40 grams. That's my final amount. And so I need to solve for T. I'll clean things up by dividing both sides by 200. Let's say 40 over 200 is 1/5. Now I'm going to take the ln of both sides, and ln and e to the power undo each other. So I'm left with ln of 1/5 equals ln of 1/2 divided by 5,750 t, and finally I can solve for t. That's super messy, but careful use of my calculator gives me an answer of 13,351 years approximately. That kind of makes sense in terms of the half-life, because to get from 200 to 40, you have to decrease by half a little more than 2 times, right? Decreasing by half once would get you to 100, decreasing to half again would get you to 50, a little more than 40. And 2 half-lives is getting pretty close to 13,000 years. This video introduced a lot of new things. It introduced a continuous growth model, which is another equivalent way of writing an exponential function. The relationship is that the b in this example is the same thing as e to the r in that version. It also introduced the ideas of doubling time and half-life, the amount of time it takes a quantity to double or decrease to half in an exponential growth model. Recall that a linear equation is an equation like, for example, 2x minus y equals 1. It's an equation without any x squareds or y squareds in it, something that could be rewritten in the form y equals mx plus b, the equation for a line. A system of linear equations is a collection of 2 or more linear equations. For example, I could have these 2 equations. A solution to a system of equations is an x value and a y value that satisfy both of the equations. For example, the ordered pair 2, 3, that means x equals 2, y equals 3, is a solution to this system, because if I plug in x equals 2 and y equals 3 into the first equation, it checks out, since 2 times 2 minus 3 is equal to 1. And if I plug in x equals 2 and y equals 3 into the second equation, it also checks out. 2 plus 3 equals 5. However, the ordered pair 1, 4, that is, x equals 1, y equals 4, is not a solution to the system. Even though this x and y value work in the second equation, since 1 plus 4 does equal 5, it doesn't work in the first equation, because 2 times 1 minus 4 is not equal to 1. In this video, we'll use systematic methods to find the solutions to systems of linear equations. In this first example, we want to solve this system of equations. There are 2 main methods we could use. We could use the method of substitution, or we could use the method of elimination. If we use the method of substitution, the main idea is to isolate one variable in one equation and then substitute it in to the other equation. For example, we can start with the first equation, 3x minus 2y equals 4, and isolate the x by adding 2y to both sides and then dividing both sides by 3. I think I'll rewrite that a little bit by breaking up the fraction into 2 fractions, 4/3 plus 2/3 y. Now I'm going to copy down the second equation, 5x plus 6y equals 2, and I'm going to substitute in my expression for x. That gives me 5 times 4/3 plus 2/3 y plus 6y equals 2, and now I've got an equation with only one variable in it, y, so I can solve for y as a number. First, I'm going to distribute the 5, so that gives me 20/3 plus 10/3 y plus 6y equals 2. And now I'm going to keep all my y terms, my terms with y's in them, on the left side, but I'll move all my terms without y's in them to the right side. At this point, I could just add up all my fractions and solve for y, but since I don't really like working with fractions, I think I'll do the trick of clearing the denominators here. So I'm going to actually multiply both sides by my common denominator of 3 just to get rid of the denominators and not have to work with fractions. So let me write that down. Distributing the 3, I get 10y plus 18y equals 6 minus 20. Now I'll add things together. So that's 28y equals negative 14. So that means that y is going to be negative 14 over 28, which is negative 1/2. So I've solved for y, And now I can go back and plug y into either of my equations to solve for x. I'll plug it into my first equation. So I'm plugging in negative 1/2 for y. That gives me 3x plus 1 equals 4. So 3x equals 3, which means that x is equal to 1. I've solved my system of equations and gotten x equals 1, y equals minus 1/2. I can also write that as an ordered pair, 1, negative 1/2, for my solution. Now let's go back and solve the same system, but use a different method, the method of elimination. The key idea to the method of elimination is to multiply each equation by a constant to make the coefficients of one variable match. Let me start by copying down my two equations. Say I'm trying to make the coefficient of x match. One way to do that is to multiply the first equation by 5 and the second equation by 3. That way, the coefficient of x will be 15 for both equations. So let me do that. So for the first equation, I'm going to multiply both sides by 5, and for the second equation, I'm going to multiply both sides by 3. That gives me, for the first equation, 15x minus 10y equals 20, and for the second equation, 15x plus 18y is equal to 6. Notice that the coefficients of x match, so if I subtract the second equation from the first, the x term will completely go away. It'll be 0 times x. And I'll be left with, let's see, negative 10y minus 18y is going to give me minus 28y. And if I do 20 minus 6, that's going to give me 14. Solving for y, I get y is 14 over minus 28, which is minus 1/2, just like before. Now we can continue, like we did in the previous solution, and substitute that value of y into either one of the equations. I'll put it again in here, and my solution proceeds as before. So once again, I get the solution that x equals 1 and y equals minus 1/2. Before we go on to the next problem, let me show you graphically what this means. Here I've graphed the equations 3x minus 2y equals 4 and 5x plus 6y equals 2, and we can see that these two lines intersect in the point with coordinates 1, negative 1/2, just like we predicted by solving the equations algebraically. Let's take a look at another system of equations. I'm going to rewrite the first equation so that the x term is on the left side with the y term, and the constant term stays on the right. And I'll rewrite or copy down the second equation. Since the coefficient of x in the first equation is minus 4 and the second equation is 3, I'm going to try using the method of elimination and multiply the first equation by 3 and the second equation by 4. That'll give me a coefficient of x of negative 12 in the first equation and 12 in the second equation. Those are equal and opposite, right? So I'll be able to add together my equations to cancel out x's. So let's do that. My first equation becomes negative 12x plus 24y equals 3. I multiplied everything by 3. And my second equation, I'll multiply everything by 4. So that's 12x minus 24y equals 8. Now something kind of funny has happened here. Not only do the x coefficients match with opposite signs, but the y coefficients do also. So if I add together my two equations in order to cancel out the x term, I'm also going to cancel out the y term, and I'll just get 0 plus 0 is equal to 3 plus 8 is 11. Well, that's a contradiction. We can't have 0 equal to 11. And that shows that these two equations actually have no solution. Let's look at this situation graphically. If we graph our two equations, we see that they're parallel lines with the same slope. This might be more clear if I isolate y in each equation. the first equation, I'd get y equals, let's see, dividing by 8, that's the same thing as 4/8 or 1/2 x plus 1/8. And the second equation, if I isolate y, let's see, minus 6y equals minus 3x plus 2, divided by minus 6, that's y equals 1/2 x minus 1/3. So indeed they have the same slope, and so they're parallel with different intercepts, and so they can have no intersection, and so it makes sense that we have no solution to our system of linear equations. This kind of system that has no solution is called an inconsistent system. In this third example, yet a third behavior happens. This time, I think I'm going to solve by substitution because I already have x with a coefficient of 1, so it's really easy to just isolate x in the first equation and then plug in to the second equation to get 3 times 6 minus 5y plus 15y equals 18. If I distribute out, I get the strange phenomenon that the 15y's cancel, and I just get 18 equals 18, which is always true. This is what's called a dependent system of linear equations. If you look more closely, you can see that the second equation is really just a constant multiple of the first equation. It's just 3 times. Every term is 3 times as big as the corresponding term in the first equation. So there's no new information in the second equation. Any x and y values that satisfy the first one will satisfy the second one. So this system of equations has infinitely many solutions. Any ordered pair x, y, where x plus 5y equals 6, or in other words, x is minus 5y plus 6, will satisfy this system of equations. That would include a y value of 0 corresponding to x value of 6, or a y value of 1 corresponding to an x value of 1, or a y value of 1/3 corresponding to an x value of 13/3, just by plugging into this equation will work. Graphically, if I graph both of these equations, the lines will just be on top of each other, so I'll just see one line. In this video, we've solved systems of linear equations using the method of substitution and the method of elimination. We've seen that systems of linear equations can have one solution when the lines that the equations represent intersect in one point. They can be inconsistent and have no solutions, that corresponds to parallel lines, or they can be dependent and have infinitely many solutions, that corresponds to the lines lying on top of each other. In this video, I'll work through a problem involving distance, rate, and time. The key relationship to keep in mind is that the rate of travel is the distance traveled divided by the time it takes to travel it in. For example, if you're driving 60 miles an hour, that's your rate, and that's because you're going a distance of 60 miles in 1 hour. Sometimes it's handy to rewrite that relationship by multiplying both sides by t, time, and that gives us that r times t is equal to d. In other words, distance is equal to rate times time. There's one more important principle to keep in mind, and that's the idea that rates add. For example, if you normally walk at 3 miles per hour, but you're walking on a moving sidewalk that's going at a rate of 2 miles per hour, then your total speed of travel with respect to something stationary is going to be 3 plus 2, or 5 miles per hour. I'll write that as a formula as R1, or the first rate plus the second rate, is equal to the total rate. Let's use those two key ideas, distance equals rate times time, and rates add, in the following problem. Elsa's boat has a top speed of 6 miles per hour in still water. While traveling on a river at top speed, she went 10 miles upstream in the same amount of time she went 30 miles downstream. We're supposed to find the rate of the river current. I'm going to organize the information in this problem into a chart. During the course of Elsa's stay, there were 2 situations we need to keep in mind. For one period of time, she was going upstream, and for another period of time, she was going downstream. For each of those, I'm going to chart out the distance she traveled, the rate she went at, and the time it took. When she was going upstream, she went a total distance of 10 miles. When she was going downstream, she went a longer distance of 30 miles. But the times to travel those two distances were the same. Since I don't know what that time was, I'll just give it a variable. I'll call it t. Now let's think about her rate of travel. The rate she traveled upstream was slower because she was going against the current, and faster when she was going downstream with the current. We don't know what the speed of the current is. That's what we're trying to figure out. So maybe I'll give it a variable, r. But we do know that in still water, Elsa can go 6 miles per hour. And when she's going downstream, since she's going with the direction of the current, rates should add. And her rate downstream should be 6 plus r. That's her rate in still water plus the rate of the current. On the other hand, when she's going upstream, then she's going against the current. So her rate of 6 miles per hour, we need to subtract the rate of the current from that. Now that we've charted out our information, we can turn it into equations using the fact that distance equals rate times time. We actually have two equations. 10 equals 6 minus r times t, and 30 is equal to 6 plus r times t. Now that we've converted our situation into a system of equations, our next job is to solve the system of equations. In this example, I think the easiest way to proceed is to isolate t in each of the two equations. So in the first equation, I'll divide both sides by 6 minus r, and in the second equation, I'll divide by 6 plus r. That gives me 10 over 6 minus r equals t, and 30 over 6 plus r equals t. Now if I set my t variables equal to each other, I get 10 over 6 minus r is equal to 30 over 6 plus r. I'm making progress because now I have a single equation with a single variable that I need to solve. Since the variable r is trapped in the denominator, I'm going to proceed by clearing the denominator. So I'm going to multiply both sides by the least common denominator, that is 6 minus r times 6 plus r. Once I cancel things out, I get that 6 plus r times 10 is equal to 30 times 6 minus r. If I distribute, I'm going to get 60 plus 10r equals 180 minus 30r, which I can now solve. Let's see, that's going to be 40r is equal to 120, so r, the speed of my current, is going to be 3 miles per hour. This is all that the problem asked for, the speed of the current. If I also wanted to solve for the other unknown, time, I could do so by plugging in r into one of my equations and solving for t. In this video, I solved a distance, rate, and time problem by charting out my information for the two situations in my problem, using the fact that rates add to fill in some of my boxes, and then using the formula distance equals rate times time to build a system of equations. In this video, I'll do a standard mixture problem in which we have to figure out what quantity of two solutions to mix together. Household bleach contains 6% sodium hypochlorite. The other 94% is water. How much household bleach should be combined with 70 liters of a weaker 1% hypochlorite solution in order to form a solution that's 2.5% sodium hypochlorite? I want to turn this problem into a system of equations. So I'm asking myself, what quantities are going to be equal to each other? Well, the total amount of sodium hypochlorite, that has symbol NaClO, before mixing, it should equal the total amount of sodium hypochlorite after mixing. Also, the total amount of water before mixing should equal the total amount of water after. And finally, just the total amount of solution in my two jugs, sodium hypochlorite together with water, should equal the total amount of solution after. That gives me a hint for what I'm looking for, but before I start writing out equations, I find it very helpful to chart out my quantities. So I've got the 6% solution, the household bleach. I've got the 1% solution, and I've got my desired ending 2.5% solution. Now in each of those solutions, I've got a certain volume of sodium hypochlorite. I've also got a volume of water, and I've got a total volume of solution. Let me see which of these boxes I can actually fill in. I know that I'm adding 70 liters of the 1% solution, so I can put a 70 in the total volume of solution here. I don't know what volume of the household bleach I want to add. That's what I'm trying to find out. So I'm going to just call that volume X. Now, since my 2.5% solution is made by combining my other two solutions, I know its volume is going to be the sum of these two volumes. So I'll write 70 plus X in this box. Now the 6% solution means that whatever the volume of solution is, 6% of that is the sodium hypochlorite. So the volume of the sodium hypochlorite is going to be 0.06 times X. The volume of water in that solution is whatever's left, so that's going to be X minus 0.06X, or 0.94 times X. Following the same reasoning, for the 1% solution, 1% of the 70 liters is the sodium hypochlorite, so that's going to be 0.01 times 70, or 0.7. The volume of water in that solution is going to be 99%, or 0.99 times 70. That works out to 69.3. Finally, for the 2.5% solution, the volume of the sodium hypochlorite is going to be 0.025 times the volume of solution, 70 plus X. And the volume of water is going to be the remainder, so that's 0.975 times 70 plus X. Now I've already used the fact that the volume of solutions before added up is the volume of solution after in writing a 70 plus X in this box. But I haven't yet used the fact that the volume of the sodium hypochlorite is preserved before and after. So I can write that down as an equation. So that means 0.06x plus 0.7 is equal to 0.025 times 70 plus x. Now I've got an equation with a variable. I'll try to solve it. Since I don't like all these decimals, I'm going to multiply both sides of my equation by, let's see, 1,000 should get rid of all the decimals. After distributing, I get 60x plus 700 equals 25 times 70 plus x. Distributing some more, I get 60x plus 700 is equal to 1750 plus 25x. So let's see, 60 minus 25 is 35x is equal to 1050, which gives me that x equals 30 liters of the household bleach. Notice that I never actually had to use the fact that the quantity of water before mixing is equal to the quantity of water after. That is, I never used the information in this column. In fact, that information is redundant. Once I know that the quantities of sodium hypochlorite add up and the total volumes of solutions add up, the fact that the volume of waters add up is just redundant information. The techniques to use to solve this equation involving solutions can be used to solve many, many other equations involving mixtures of items. My favorite method is to first make a chart involving the types of mixtures and the types of items in your mixture, fill in as many boxes as I can, and then use the fact that the quantities add. This video is about rational functions and their graphs. Recall that a rational function is a function that can be written as a ratio or quotient of two polynomials. Here's an example. The simpler function f of x equals 1 over x is also considered a rational function. You can think of 1 and x as very simple polynomials. The graph of this rational function is shown here. This graph looks different from the graph of a polynomial. For one thing, its end behavior is different. The end behavior of a function is the way the graph looks when x goes through really large positive or really large negative numbers. We've seen that the end behavior of a polynomial always looks like one of these cases. That is, y marches off to infinity or maybe negative infinity as x gets really big or really negative. But this rational function has a different type of end behavior. Notice as x gets really big, the y values are leveling off at about a y value of 3. And similarly, as x values get really negative, our graph is leveling off near the line y equals 3. I'll draw that line, y equals 3, on my graph. That line is called a horizontal asymptote. A horizontal asymptote is a horizontal line that our graph gets closer and closer to as x goes to infinity or as x goes to negative infinity, or both. There's something else that's different about this graph from a polynomial graph. Look at what happens as x gets close to negative 5. As we approach negative 5 with x values on the right, our y values are going down towards negative infinity. And as we approach the x value of negative 5 from the left, our y values are going up towards positive infinity. We say that this graph has a vertical asymptote at x equals negative 5. A vertical asymptote is a vertical line that the graph gets closer and closer to. Finally, there's something really weird going on at x equals 2. There's a little open circle there, like the value at x equals 2 is dug out. That's called a hole. A hole is a place along the curve of the graph where the function doesn't exist. Now that we've identified some of the features of our rational functions graph, I want to look back at the equation and see how we could have predicted those features just by looking at the equation. To find horizontal asymptotes, we need to look at what our function is doing when x goes through really big positive or really big negative numbers. Looking at our equation for our function, the numerator is going to be dominated by the 3x squared term when x is really big, right? Because 3 times x squared is going to be absolutely enormous compared to this negative 12 if x is a big positive or negative number. In the denominator will be dominated by the x squared term again. If x is a really big positive or negative number, like a million squared will be much, much bigger than 3 times a million, or negative 10. For that reason, to find the end behavior, or the horizontal asymptote, for our function, we just need to look at the term on the numerator and the term on the denominator that have the highest exponent. Those are the ones that dominate the expression in size. So as x gets really big, our function's y values are going to be approximately 3x squared over x squared, which is 3. That's why we have a horizontal asymptote at y equals 3. Now our vertical asymptotes, those tend to occur where our denominator of our function is 0. That's because the function doesn't exist when our denominator is 0, and when we get close to that place where our denominator is 0, we're going to be dividing by tiny, tiny numbers, which will make our y values really big in magnitude. So to check where our denominator is 0, let's factor our function. In fact, I'm going to go ahead and factor the numerator and the denominator. So the numerator factors, let's see, pull out the 3, I get x squared minus 4. Factoring the denominator, that factors into x plus 5 times x minus 2. I can factor the numerator a little further. That's 3 times x minus 2 times x plus 2 over x plus 5, x minus 2. Now, when x is equal to negative 5, my denominator will be 0, but my numerator will not be 0. That's what gives me the vertical asymptote at x equals negative 5. Notice that when x equals 2, the denominator is 0, but the numerator is also 0. In fact, if I canceled the x minus 2 factor from the numerator and denominator, I'd get a simplified form for my function that agrees with my original function as long as x is not equal to 2. That's because when x equals 2, this simplified function exists, but the original function does not. It's 0 over 0. It's undefined. But for every other x value, including x values near x equals 2, our original function is just the same as this function. And that's why our function only has a vertical asymptote at x equals negative 5, not one at x equals 2, because the x minus 2 factor is no longer in the function after simplifying. It does have a hole at x equals 2 because the original function is not defined there, even though the simplified version is. If we want to find the y value of our hole, we can just plug in x equals 2 into our simplified version of our function. That gives a y value of 3 times 2 plus 2 over 2 plus 7, or 12/9, which simplifies to 4/3. So our hole is at 2 4/3. Now that we've been through one example in detail, let's summarize our findings. We find the vertical asymptotes and the holes by looking where the denominator is 0. The holes happen where the denominator and numerator are both 0 and those factors cancel out. The vertical asymptotes are all other x values where the denominator is 0. We find the horizontal asymptotes by considering the highest power term on the numerator and the denominator. I'll explain this process in more detail in 3 examples. In the first example, if we circle the highest power terms, that simplifies to 5x over 3x squared, which is 5 over 3x. As x gets really big, the denominator is going to be huge. So I'm going to be dividing 5 by a huger and huger number. That's going to be going very close to 0. And therefore, we have a horizontal asymptote at y equals 0. In the second example, the highest power terms, 2x cubed over 3x cubed, simplify to 2/3. So as x gets really big, we're going to be heading towards 2/3, and we have a horizontal asymptote at y equals 2/3. In the third example, the highest power terms, x squared over 2x, simplifies to x over 2. As x gets really big, x over 2 is getting really big, and therefore we don't have a horizontal asymptote at all. This is going to infinity when x goes through big positive numbers, and is going to negative infinity when x goes through big negative numbers. So in this case, the end behavior is kind of like that of a polynomial, and there's no horizontal asymptote. In general, when the degree of the numerator is smaller than the degree of the denominator, we're in this first case, where the denominator gets really big compared to the numerator and we go to 0. In this second case, where the degree of the numerator and the degree of the denominator are equal, things cancel out, and so we get a horizontal asymptote at the y value that's equal to the ratio of the leading coefficients. Finally, in the third case, when the degree of the numerator is bigger than the degree of the denominator, then the numerator is getting really big compared to the denominator, so we end up with no horizontal asymptote. Finally, let's apply all these observations to one more example. Please pause the video and take a moment to find the vertical asymptotes, horizontal asymptotes, and holes for this rational function. To find the vertical asymptotes and holes, we need to look at where the denominator is 0. In fact, it's going to be handy to factor both the numerator and the denominator, since if there are any common factors, we might have a hole instead of a vertical asymptote. The numerator is pretty easy to factor. Let's see, that's 3x times x plus 1. For the denominator, I'll first factor out an x, and then I'll factor some more using a guess and check method. I know that I'll need a 2x and an x to multiply together to the 2x squared, and I'll need a 3 and a minus 1, or else a minus 3 and a 1. Let's see if that works. If I multiply out 2x minus 1 times x plus 3, that does give me back my 2x squared plus 5x minus 3, so that checks out. Now I notice that I have a common factor of x in both the numerator and the denominator, so that's telling me I'm going to have a whole at x equals 0. In fact, I could rewrite my rational function by canceling out that common factor, and that's equivalent as long as x is not equal to 0. So the y value of my whole is what I get when I plug 0 into my simplified version. That would be 3 times 0 plus 1 over 2 times 0 minus 1 times 0 plus 3, which is 3 over negative 3 or minus 1. So my whole is at 0 minus 1. Now all the remaining places in my denominator that make my denominator 0 will give me vertical asymptotes. So I'll have a vertical asymptote when 2x minus 1 times x plus 3 equals 0. That is, when 2x minus 1 is 0 or x plus 3 is 0. In other words, when x is 1/2 or x equals negative 3. Finally, to find my horizontal asymptotes, I just need to consider the highest power term in the numerator and the denominator. That simplifies to 3 over 2x, which is bottom heavy, right? When x gets really big, this expression is going to 0. And that means that we have a horizontal asymptote at y equals 0. So we found the major features of our graph, the whole, the vertical asymptotes, and the horizontal asymptotes. Together, this would give us a framework for what the graph of our function looks like. Horizontal asymptote at y equals 0, vertical asymptotes at x equals 1/2 and x equals minus 3, and a whole at the point 0, minus 1. Plotting a few more points, or using a graphing calculator or graphing program, we can see that our actual function will look something like this. Notice that the x-intercept, when x is negative 1, corresponds to where the numerator of our rational function, or reduced rational function, is equal to 0. That's because a 0 on the numerator, that doesn't make the denominator 0, makes the whole function 0. And an x-intercept is where the y value of the whole function is 0. In this video, we learned how to find horizontal asymptotes of rational functions by looking at the highest power terms. We learned to find the vertical asymptotes and wholes by looking at the factored version of the functions. The wholes correspond to the x values that make the numerator and denominator 0, whose corresponding factors cancel. The vertical asymptotes correspond to the x values that make the denominator 0, even after factoring any common factors in the numerator and denominator. This video is about combining functions by adding them, subtracting them, multiplying them, and dividing them. Suppose we have two functions, f of x equals x plus 1 and g of x equals x squared. One way to combine them is by adding them together. This notation, f plus g of x, means the function defined by taking f of x and adding it to g of x. So for our functions, that means we take x plus 1 and add x squared. I can rearrange that as the function x squared plus x plus 1. So f plus g evaluated on x means x squared plus x plus 1. And if I wanted to evaluate f plus g on the number 2, that would be 2 squared plus 2 plus 1, or 7. Similarly, the notation f minus g of x means the function we get by taking f of x and subtracting g of x. So that would be x plus 1 minus x squared. And if I wanted to take f minus g evaluated at 1, that would be 1 plus 1 minus 1 squared, or 1. The notation f dot g of x, which is sometimes also written just as fg of x, that means we take f of x times g of x. In other words, x plus 1 times x squared, which could be simplified as x cubed plus x squared. The notation f divided by g of x means I take f of x and divide it by g of x. So that would be x plus 1 divided by x squared. In this figure, the blue graph represents h of x, and the red graph represents the function p of x. We're asked to find h minus p of 0. We don't have any equations to work with, but that's okay. We know that for any x, h minus p of x is defined as h of x minus p of x. So for x equals 0, h minus p of 0 is going to be h of 0 minus p of 0. Using the graph, we can find h of 0 by finding the value of 0 on the x-axis and finding the corresponding y value for the function h of x. So that's about 1.8. Now p of 0 we can find similarly by looking for 0 on the x-axis and finding the corresponding y value for the function p of x, and that's a y value of 1. 1.8 minus 1 is 0.8, so that's our approximate value for h minus p of 0. If we want to find p times h of negative 3, again we can rewrite that as p of negative 3 times h of negative 3. And using the graphs, we see that for an x value of negative 3, the y value for p is 2, and the x value of negative 3 corresponds to a y value of negative 2 for h. 2 times negative 2 is negative 4, so that's our value for p times h of negative 3. In this video, we saw how to add two functions, subtract two functions, multiply two functions, and divide two functions in the following way. When you compose two functions, you apply the first function, and then you apply the second function to the output of the first function. For example, the first function might compute population size from time in years. So its input would be time in years since a certain date, and its output would be number of people in the population. The second function, g, might compute healthcare costs as a function of population size. So it will take population size as input, and its output will be healthcare costs. If you put these functions together, that is, compose them, then you'll go all the way from time in years to healthcare costs. This is your composition, g composed with f. The composition of two functions, written g with a little circle, f of x, is defined as follows. G composed with f of x is g evaluated on f of x. We can think of it schematically in this diagram. F acts on a number x and produces a number f of x. Then g takes that output f of x and produces a new number, g of f of x. Our composition of functions, g composed with f, is the function that goes all the way from x to g of f of x. Let's work out some examples where our functions are defined by tables of values. If we want to find g composed with f of 4, by definition, this means g of f of 4. To evaluate this expression, we always work from the inside out. So we start with the x value of 4, and we find f of 4 using the table of values for f of x. when x equals 4, f of x is 7. So we can replace f of 4 with the number 7. Now we need to evaluate g of 7. 7 becomes our new x value in our table of values for g. The x value of 7 corresponds to the g of x value of 10, so g of 7 is equal to 10. We found that g composed with f of 4 is equal to 10. If instead we want to find f composed with g of 4, well, we can rewrite that as f of g of 4, and again work from the inside out. Now we're trying to find g of 4, so 4 is our x value, and we use our table of values for g to see that g of 4 is 1. So we replace g of 4 by 1, and now we need to evaluate f of 1. Using our table for f values, f of 1 is 8. Notice that when we've computed g of f of 4, we got a different answer than when we computed f of g of 4. And in general, g composed with f is not the same thing as f composed with g. Please pause the video and take a moment to compute the next two examples. We can replace f composed with f of 2 by the equivalent expression f of 2. Working from the inside out, we know that f of 2 is 3 and f of 3 is 6. If we want to find f composed with g of 6, rewrite that as f of g of 6. Using the table for g of 6 is 8, but f of 8 is not on the table as an x value for the f function, and so there is no f of 8. This does not exist. We can say that 6 is not in the domain for f composed with g. Even though it was in the domain of g, we couldn't follow all the way through and get a value for f composed with g of 6. Next, let's turn our attention to the composition of functions that are given by equations. P of x is x squared plus x, and q of x is negative 2x. We want to find q composed with p of 1. As usual, I can rewrite this as q of p of 1 and work from the inside out. P of 1 is 1 squared plus 1, so that's 2. So this is the same thing as q of 2. But q of 2 is negative 2 times 2, or negative 4. So this evaluates to negative 4. In this next example, we want to find q composed with p of some arbitrary x. I'll rewrite it as usual as q of p of x and work from the inside out. Well, p of x, we know the formula for that. That's x squared plus x. So I can replace my p of x with that expression. Now, I'm stuck with evaluating q on x squared plus x. Well, q of anything is negative 2 times that thing. So q of x squared plus x is going to be negative 2 times the quantity x squared plus x. What I've done is I've substituted in the whole expression x squared plus x, where I saw the x in this formula for q of x. It's important to use the parentheses here so that we'll be multiplying negative 2 by the whole expression and not just by the first piece. I can simplify this a bit as negative 2x squared minus 2x, and that's my expression for q composed with p of x. Notice that if I wanted to compute q composed with p of 1, which I already did in the first problem, I could just use this expression now. Negative 2 times 1 squared minus 2, and I get negative 4, just like I did before. Let's try another one. Let's try p composed with q of x. First, I rewrite this, p of q of x. Working from the inside out, I can replace q of x with negative 2x. So I need to compute p of negative 2x. Here's my formula for p. To compute p of this expression, I need to plug in this expression everywhere I see an x in the formula for p. So that means negative 2x squared plus negative 2x. Again, being careful to use parentheses to make sure I plug in the entire expression in for x. Let me simplify. This is 4x squared minus 2x. Notice that I got different expressions for q of p of x and for p of q of x. Once again, we see that q composed with p is not necessarily equal to p composed with q. Please pause the video and try this last example yourself. Rewriting and working from the inside out, we can replace p of x with its expression x squared plus x, and then we need to evaluate p on x squared plus x. That means we plug in x squared plus x everywhere we see an x in this formula. So that's x squared plus x quantity squared plus x squared plus x. Once again, I can simplify by distributing out. That gives me x to the fourth plus 2x cubed plus x squared plus x, or x to the fourth plus 2x cubed plus 2x squared plus x. In this last set of examples, we're asked to go backwards. We're given a formula for a function of h of x, but we're supposed to rewrite h of x as a composition of two functions, f and g. Let's think for a minute which of these two functions gets applied first. F composed with g of x, let's see, that means f of g of x. And since we evaluate these expressions from the inside out, we must be applying g first and then f. In order to figure out what f and g could be, I like to draw a box around something inside my expression for h. So I'm going to draw a box around x squared plus 7. Then whatever's inside the box, that'll be my function g of x, the first function that gets applied. Whatever happens to the box, in this case taking the square root sign, that becomes my outside function, my second function, f. So here we're going to say g of x is equal to x squared plus 7, and f of x is equal to the square root of x. Let's just check and make sure that this works. So I need to check that when I take the composition f composed with g, I need to get the same thing as my original h. So let's see. If I do f composed with g of x, well, by definition that's f of g of x. Working from the inside out, I can replace g of x with its formula, x squared plus 7. So I need to evaluate f of x squared plus 7. That means I plug in x squared plus 7 into the formula for f. So that becomes the square root of x squared plus 7. Ta-da! It works because it matches my original equation. So we found a correct answer, a correct way of breaking h down as a composition of two functions. But I do want to point out this is not the only correct answer. I'll write down my formula for h of x again, and this time I'll put the box in a different place. I'll just box the x squared. If I did that, then my inside function, my first function, g of x, would be x squared. And my second function is what happens to the box. So my f of x is what happens to the box, and the box gets added 7 to it and taken the square root. So in other words, f of x is going to be the square root of x plus 7. Again, I can check that this works. If I do f composed with g of x, that's f of g of x. So now g of x is x squared, so I'm taking f of x squared. When I plug in x squared for x, I do in fact get the square root of x squared plus 7. So this is an alternative correct solution. In this video, we learned to evaluate the composition of functions by rewriting it and working from the inside out. We also learned to break apart a complicated function into a composition of two functions by boxing one piece of the function and letting the first function applied in the composition let that be the inside of the box, and the second function applied in the composition be whatever happens to the box. The inverse of a function undoes what the function does. So the inverse of tying your shoes would be to untie them. And the inverse of the function that adds 2 to a number would be the function that subtracts 2 from a number. This video introduces inverses and their properties. Suppose f of x is the function defined by this chart. In other words, f of 2 is 3, f of 3 is 5, f of 4 is 6, and f of 5 is 1. The inverse function for f, written f superscript -1x, undoes what f does. Since f takes 2 to 3, f inverse takes 3 back to 2. So we write this, f superscript -1 of 3 is 2. Similarly, since f takes 3 to 5, f inverse takes 5 to 3. And since f takes 4 to 6, f inverse of 6 is 4. And since f takes 5 to 1, f inverse of 1 is 5. I'll use these numbers to fill in the chart. Notice that the chart of values when y equals f of x and the chart of values when y equals f inverse of x are closely related. They share the same numbers, but the x values for f of x correspond to the y values for f inverse of x, and the y values for f of x correspond to the x values for f inverse of x. That leads us to the first key fact. Inverse functions reverse the roles of y and x. I'm going to plot the points for y equals f of x in blue. Next, I'll plot the points for y equals f inverse of x in red. Pause the video for a moment and see what kind of symmetry you observe in this graph. How are the blue points related to the red points? You might have noticed that the blue points and the red points are mirror images. Over the mirror line, y equals x. So our second key fact is that the graph of y equals f inverse of x can be obtained from the graph of y equals f of x by reflecting over the line y equals x. This makes sense because inverses reverse the roles of y and x. In this same example, let's compute f inverse of f of 2. This open circle means composition. In other words, we're computing f inverse of f of 2. We compute this from the inside out, so that's f inverse of 3, since f of 2 is 3, and f inverse of 3 we see as 2. Similarly, we can compute f of f inverse of 3, and that means we take f of f inverse of 3. Since f inverse of 3 is 2, that's the same thing as computing f of 2, which is 3. Please pause the video for a moment and compute these other compositions. You should have found that in every case, if you take f inverse of f of a number, you get back to the very same number you started with. And similarly, if you take f of f inverse of any number, you get back to the same number you started with. So in general, f inverse of f of x is equal to x, and f of f inverse of x is also equal to x. This is the mathematical way of saying that f and f inverse undo each other. Let's look at a different example. Suppose that f of x is x cubed. Pause the video for a moment and guess what the inverse of f should be. Remember, f inverse undoes the work that f does. You might have guessed that f inverse of x is going to be the cube root function. And we can check that this is true by looking at f of f inverse of x. That's f of the cube root of function, which means the cube root function cubed, which gets us back to x. Similarly, if we compute f inverse of f of x, That's the cube root of x cubed, and we get back to x again. So the cube root function really is the inverse of the cubing function. When we compose the two functions, we get back to the number that we started with. It'd be nice to have a more systematic way of finding inverses of functions besides guessing and checking. One method uses the fact that inverses reverse the roles of y and x. So if we want to find the inverse of the function f of x equals 5 minus x over 3x, we can write it as y equals 5 minus x over 3x, reverse the roles of y and x to get x equals 5 minus y over 3y, and then solve for y. To solve for y, let's multiply both sides by 3y, bring all terms with y's in them to the left side, and all terms without y's in them to the right side, factor out the y, and divide to isolate y. This gives us f inverse of x as 5 over 3x plus 1. Notice that our original function, f, and our inverse function, f inverse, are both rational functions, but they're not the reciprocals of each other. And in general, f inverse of x is not usually equal to 1 over f of x. This can be confusing because when we write 2 to the minus 1, that does mean 1 over 2, but f to the minus 1 of x means the inverse function and not the reciprocal. It's natural to ask if all functions have inverse functions. That is, for any function you might encounter, is there always a function that is its inverse? In fact, the answer is no. See if you can come up with an example of a function that does not have an inverse function. The word function here is key. Remember that a function is a relationship between x values and y values such that for each x value in the domain, there's only one corresponding y value. One example of a function that does not have an inverse function is the function f of x equals x squared. To see that the inverse of this function is not a function, note that for the x squared function, the number 2 and the number negative 2 both go to the number 4. So if I had an inverse, it would have to send 4 to both 2 and negative 2. The inverse would not be a function. It might be easier to understand the problem when you look at a graph of y equals x squared. Recall that inverse functions reverse the roles of y and x and flip the graph over the line y equals x. But when I flip the green graph over the line y equals x, I get this red graph. This red graph is not the graph of a function because it violates the vertical line test. The reason it violates the vertical line test is because the original green function violates the horizontal line test and has two x values with the same y value. In general, a function f has an inverse function if and only if the graph of f satisfies the horizontal line test, i.e. every horizontal line intersects the graph in at most one point. Pause the video for a moment and see which of these four graphs satisfy the horizontal line test. In other words, which of the four corresponding functions would have an inverse function. You may have found that graphs A and B violate the horizontal line test, so their functions would not have inverse functions. But graphs C and D satisfy the horizontal line test, so these graphs represent functions that do have inverses. Functions that satisfy the horizontal line test are sometimes called one-to-one functions. Equivalently, a function is one-to-one if for any two different x values, x1 and x2, the y values f of x1 and f of x2 are different numbers. Sometimes this is said f is 1 to 1 if whenever f of x1 is equal to f of x2, then x1 has to equal x2. As our last example, let's try to find p inverse of x, where p of x is the square root of x minus 2, drawn here. If we graph p inverse on the same axis as p of x, we get the following graph, simply by flipping over the line y equals x. If we try to solve the problem algebraically, we can write y equal to square root of x minus 2, reverse the roles of y and x, and solve for y by squaring both sides and adding 2. Now if we were to graph y equals x squared plus 2, that would look like a parabola. It would look like the red graph we've already drawn together with another arm on the left side. But we know that our actual inverse function consists only of this right arm. We can specify this algebraically by making the restriction that x has to be bigger than or equal to 0. This corresponds to the fact that on the original graph for the square root of x, y was only greater than or equal to 0. Looking more closely at the domain and range of p and p inverse, we know that the domain of p is all values of x such that x minus 2 is greater than or equal to 0, since we can't take the square root of a negative number. This corresponds to x values being greater than or equal to 2, or in interval notation, the interval from 2 to infinity. The range of p, we can see from the graph, is all y values greater than or equal to 0, or the interval from 0 to infinity. Similarly, based on the graph, we see the domain of p inverse is x values greater than or equal to 0, the interval from 0 to infinity, and the range of p inverse is y values greater than or equal to 2, or the interval from 2 to infinity. If you look closely at these domains and ranges, you'll notice that the domain of p corresponds exactly to the range of p inverse, and the range of p corresponds to the domain of p inverse. This makes sense because inverse functions reverse the roles of y and x. The domain of f inverse of x is the x values for f inverse, which corresponds to the y values, or the range of f. The range of f inverse is the y values for f inverse, which correspond to the x values, or the domain of f. In this video, we discussed 5 key properties of inverse functions. Inverse functions reverse the roles of y and x. The graph of y equals f inverse of x is the graph of y equals f of x reflected over the line y equals x. When we compose f with f inverse, we get the identity function y equals x, and similarly, when we compose f inverse with f, that brings x to x. In other words, f and f inverse undo each other. The function f of x has an inverse function if and only if the graph of y equals f of x satisfies the horizontal line test. And finally, the domain of f is the range of f inverse, and the range of f is the domain of f inverse. These properties of inverse functions will be important when we study exponential functions and their inverses, logarithmic functions.